Okay. All right, good morning, and welcome to the, we don't have let's get a screen up here. That makes more sense than that. Welcome to the session on crystals that grow. I'm Jim Diorio. I'm from Pacific Northwest National Lab and the University of Washington. And my co-chair?
Hi, everyone. I'm Saba Qasemlu from Radboud University, and I have the chance to be the co-chair of this session today.
We're going to do things just a little bit differently than in the past. I'll give an overview to set the context, but it's going to be a little shorter than normal. And then Saba has an introduction for each speaker that will disperse throughout. So the first talk will start a little sooner than what the schedule says, and we'll be on schedule at the end. Okay, so let's see if I can get myself a pointer of some kind here. That's not going to do it for me. I'm in a mode that I don't know how to find my laser pointer, so I'm going to use this cursor instead. So crystallization is a pervasive phenomenon in both the technological and natural world. In this particular meeting, many work on the problem of how to grow and control the polymorph of pharmaceuticals. But of course, in technology, crystallization has many other kinds of impacts. It's the basis of all of the microchips that are allowing me to present this talk to you today, for example, through the growth of silicon and the doping of that material. In more recent years, it's, of course, become very important in the area of nanomaterials. But crystallization is a key part of what goes on in the environment. It has a huge impact on climate, in fact, on the process of mineralization by organisms is the reason we have oxygen in our atmosphere to begin with. And it's also an important aspect of biology, both in terms of the soft parts of organisms. Here, for example, is the crystalline outer membrane of a microbe. So almost all archaea and many bacteria have crystalline protein membranes, not lipid membranes. And here is an example of the hard parts of an organism. This is a phytoplankton called the coccolithophorid that produces this beautiful structure of calcium carbonate in the form of calcite. Well, crystallization has two distinct parts to it. One is nucleation and one is growth. We all know this, right? And they really are distinct because, of course, in nucleation you have to get over a free energy barrier, and growth is a downhill process. So I want to talk a little bit about, set the context for some talks you're going to hear by talking about some fundamentals to get us all on the same page. In classical nucleation theory, crystallization begins with unstable density fluctuations that overcome a free energy barrier. So we have free ions, say, let's just talk about solution crystallization, but this applies to vapor growth or melt growth as well. Imagine free ions in solution come together to form a nucleus, a cluster, and that's got to be a downhill drop overall in free energy for this process to go forward. But there's both a negative term that drives this process, and that's the delta mu term, dg dn times delta n, that's delta mu, change in free energy with number. And so that's a negative term that drives the process. But we have to create an interface, and when we calculate delta mu, we're overcounting by pretending all the atoms and ions that go into the particle have the same environment, but the ones on the surface don't have all their neighboring bonds. And so in a thermodynamic sense, we can think of that as an energy penalty. In a statistical mechanical sense, it just means their off rates are high. And so we have to get to a certain size before those things balance out. And that is known as the critical size. And you can see that if you plot these two terms. One of these, of course, it depends on n, the number that goes in here, so it's not a volume term. So it's cubic, and it's a negative term. But the other one, it depends on the interface, which is an area term, so it's quadratic, and it's a positive term, and when you add these, you end up with a barrier, free energy barrier. So the system has to go uphill in free energy before it can grow spontaneously. This critical size is critical only in the sense that, on average, half of clusters that size will go backwards and half of them will go forward, okay? All right, so here's a movie, an Institute TM movie of gold showing this process. You can see in the circles are some examples of particles that fluctuate in size and eventually disappear, demonstrating the fact that these are unstable density fluctuations that are responsible for growth or for nucleation. That allows us to write down nucleation rate equations. So the rate of nucleation has two Boltzmann factors involved. One of them is an exponential in this free energy barrier, which is, what is a free energy barrier? What is the free energy, right? It's the fact that the system is exploring all the possible configurations it can be in. And the configuration that consists of ions that are large enough to be over the critical size is small. And so that's what the barrier represents. It's, one of a very large number of configurations, or some subset of a very large number of configurations that will bring it to a point where it's downhill in free energy. And then there's a second Boltzmann factor because, of course, in the absence of a free energy barrier, there's still chemical kinetics. And chemical kinetics are always limited by thermal activation over some barrier, whether it's desolvation of ions or a binding of an ion to a cluster. And so we can write, and then finally we can write this free energy barrier in terms of the fundamental parameters, the interfacial free energy alpha, and the chemical potential delta mu. Often this is replaced with the supersaturation, which is just delta mu over kT. All right, so those are the two creep. The last point I want to make, and this is very important to realize, is that this model of nucleation just assumes that the ions come together to form a structure that is a baby version of the large crystal. In other words, it has the same structure. And that's not the case in many, many cases. All right, and that takes me to the point that we now know that nucleation in many systems follows what I'll refer to as indirect, but are often called non-classical pathways. And this happens for sort of four general reasons. The first one is because it's often the case that you can't separate nucleation from chemical reaction. So the species that go into the first nuclei don't have the right stoichiometry to be part of that nucleus. And so they undergo chemical reactions. This happens to be an example in the calcium phosphate case where we have these calcium triphosphate, I'm sorry, my superscripts have somehow turned into non-superscripts, but we have these tricalcium triphosphate ions that have to undergo chemical reactions to become the first amorphous clusters, and those have to go under more chemical reactions to make the first crystal. And those chemical reaction pathways aren't included in classical nucleation theory. The second one is that size can have an impact on stability. So you can imagine there are special configurations, like if you take, say, a platinum island on a surface, right? A hexamer is the most stable of those clusters. If you go to a 5-mer or an 8-mer, it's less stable because you don't have as many bonds in a nice configuration. And that's true in solution growth as well. So there's this beautiful work showing that in making indium phosphide quantum dots, that there's a magic size. Or I know where every atom is and every ligand is, and it's a particularly stable configuration, even though it's not the most stable configuration, which is the quantum dot. And the third one is one in which even the entities that go into the cluster are not monomeric, but they're complex oligomeric species. That was proposed for the calcium carbonate system. It's still controversial in that system, but it certainly is the case in things like silicates and iron oxides, and actually in a number of organic systems as well. And then finally, a process that was discovered by Peter Vekoloff, our first speaker, although I don't think he's going to speak about this today, is that systems can undergo an initial transition through liquid-liquid phase separation. However, I want to make a point here. There's nothing non-classical about liquid-liquid phase separation. That's called a spinodal. However, in a spinodal, the dense liquid is more stable than the solution, right? So it's a spontaneous separation into an ion-rich liquid and ion-poor liquid, and then you can crystallize from there. However, in this version, in this model, there's a dense liquid phase that's buried below the solid liquid line that is less stable than the solution or the solid. So those dense liquid droplets can only exist microscopically. They are unstable entities relative to either endpoint. They're metastable relative to their neighbors, but they may represent the lowest energy pathway, and this is an important thing to realize. There are phases that will not appear on a phase diagram, but still may lie in the pathway to the crystal. All right, so the same picture applies in crystal growth. That is, there is a classical version and a realization that non-classical pathways can dominate. The classical model, which is, I think, we can attribute a lot of this to Sir Charles Frank, has to do with the attachment of ions to kink sites on steps. And the realization of Frank was that you could only explain crystal growth rates by recognizing that you can't avoid dislocations in crystals. Dislocations generate steps so that you don't have to nucleate new islands. That removes the problem of the nucleation barrier. But there's still, well, I don't want to get into the details of the controls here. That's not the point. The only point I want to make here is that, as in the classical nucleation theory, there is a clear quantitative description of this process. And we can relate the controls on nucleation, on growth, to two parameters which are, you'll notice, are essentially the same parameters as the ones that show up in nucleation. Now, I say that take that with a grain of salt, because of course the activation barrier may relate to some slightly different processes. But surely desolvation, for example, which is one of the largest barriers to crystallization, is happening in nucleation as well as growth. And the interfacial free energy here, I've lost my cursor. Where are you? Here we go. Is essentially the same one as you see in nucleation. However, growth by repeated attachment of primary nucleated particles is now seen as a common pathway in a wide range of materials: oxides, semiconductors, metals, peptides and proteins, and even biominerals. The system makes lots of particles. Those particles have no inherent thermodynamic status, I'll call it, and they interact with one another. And the system evolves then by the assembly of those particles, and often in a process known as oriented attachment, where they attach only on light crystallographic phases. The point is that we now understand, after about 2 decades, that the formation of crystal materials follows a diverse set of pathways. Yes, there is the classical pathway, and it does work in a number of systems, but there's a huge number of systems for which the system is driven through these other pathways. In many cases, it's because we drive systems to high chemical potential, high supersaturation, because of course otherwise it would take us a week to do something, and we need to do something before we go home at 5 p.m. And so now by driving it to high chemical potential, there are lots of pathways open to the system, and it takes those pathways. All right, so why? So the indirect pathways arise from complexities in the free energy landscape and kinetic factors. So this is the simple picture of Gibbs, and it's, what's wrong with it? How can this be wrong? All it says is that delta G is equal to the change in chemical potential plus some energy penalty, right? Well, the problem is that the energy penalty is assumed to just be given by the bulk surface tension, and it doesn't apply at small size. And so the picture that emerges is that you have indirect pathways because of complexities in the free energy landscape, either because there are phases on the phase diagram that are less stable than the stable phase, but still may be easier to form, and that's what gives rise to the so-called Ostwald rule of stages. Okay? The metastable forms appear first because they're easier to form, and the supersaturation is high enough to allow that to happen. But it can also occur because there are unstable structures. They're locally stable in the sense that they're more stable than the neighboring configuration, so they're long-lived. But they're unstable relative to either the solution or the crystal. But nonetheless, they may represent the lowest energy pathway to the stable state. And then finally, you can have these indirect pathways because of the influence of dynamics, just kinetic reasons. For example, I create a very high supersaturation and I make, a mole of nanoparticles or clusters. Those are going to interact with one another, and then you'll have these indirect pathways because this part of the solution doesn't know it shouldn't have nucleated because one over here already did. And the system only wants to have one big particle with minimum surface energy. And then the other dynamic reason is because the system can just get stuck. So it turns out the amorphous phase gets made, but then the dynamics are so slow that it stays there. And we don't ever get a crystal. Or you get stuck in a gel, which is even worse, because that's not even a minimum in the diagram. So complex pathways can arise for both thermodynamic and kinetic reasons, and the challenge is to determine in which systems it happens and for what reasons. All right, so There are three factors that add complexities to this already complex picture of crystallization. The first is that we're rarely free of interfaces, and interfaces can completely change things. And it can happen because you get heterogeneous nucleation, and I've noted two quite different examples here, right? One is scale formation in oil pipes, and the other is the formation of bone within collagen. Both are interfacially driven, all right? I showed this movie at the bottom because one of the points I want to make, you can see the new particles that form in this system are not attached to the old ones. They form in the interfacial region. And it's important to realize when we talk about an interface, it doesn't just include the surface, because the solution nearby is structured, has chemical gradients, and that changes all the chemistry of nucleation. The second complexity is conformation, and that's very important, as we heard from Aurora this week. In the organic world, it's extremely important in the protein world. Here's an example of the so-called S-layer membranes, and these are S-layer proteins nucleating on lipids. And you'll notice as they start, they don't have any structure. And that's because they're not folded, and it's only through their interaction with their neighbors that they find the folded state. And then that allows them to grow rapidly by adding on new units. And then the third example is electric fields. So I want to point out that we think of electric fields as something that we apply, but surfaces are charged. They have their own electric fields. And those E fields put in a capacitive term in the free energy, which can completely alter the process of nucleation. I happen to be showing an example of a gibbsite film that forms on mica. It will only form a monolayer. It will never cover the surface completely because it's all a matter of balancing charge of electrostatics. And I think that what you'll hear today reflects both these fundamental aspects that I discussed, as well as the role of surfaces, the problem of conformation of proteins, and then finally the role of electric fields. And let's see, so hopefully Peter is prepared to start. I'm going to do an introduction for you, Peter, so don't begin yet. Peter Vekelov is our first speaker. He's going to talk about the elementary reactions for incorporation into crystals. Peter is the John and Rebecca Morris Professor of Chemical Engineering at the University of Houston in the Chemical Engineering Department. And he's the winner of last year's American Association for Crystal Growth Award. He has been working in the field of crystal growth fundamentals since he was a graduate student with Alex Chernoff at Moscow State University and the Institute for Crystallography, if I'm remembering correctly.
Yes.
Yes, Peter, right. It's been a long time since you were there, or since Alex was there. A lot of his work is focused on how steps propagate, how they interact with the kinetics of steps interplay with the mass transport. But in recent years, he made a very important discovery that he's worked on for quite a while now, which is this two-step process nucleation via these unstable dense liquid droplets. I don't think that's the topic he's going to talk about today based on the title. But I'm sure we'll enjoy whatever it is. Peter, we're going to turn it over to you.
Thank you.
Sir, do you hear us?
I can hear you, yes.
You can start. You can start.
I can still hear an echo, and you have a way to remove the echo.
Okay, okay, sir.
Sarah knew how to do it when we practiced an hour ago.
Go средихме, да. We can arrange that, sir, and you can start.
Yes. So you want me to share my screen, I guess.
Yes.
Can you see my screen?
Yes, sir.
All
Yes, sir.
right. So folks, I cannot see you. You can probably see a little icon of my face. I apologize profusely for not being able to join you, but on Saturday morning, just as I was about to get into my rental car and drive myself to Ohrid, I tested positive for COVID. Not only that, I was really sick. I'm almost recovered, but I still think that you are lucky that I'm not among you spreading the coronavirus. So let's think of this as the best possible version under the circumstances. So I will talk. Another thing that I want to say is that I want to congratulate Panche on an exquisitely organized meeting. I looked at the list of speakers and the list of topics, and it's outstanding. So I'll be looking forward to watching this online. I learned a lot from watching the session on flexible crystals yesterday. And also the location is outstanding. I understand that the credit for choosing the location goes not to Panche, but to his parents, because he was actually born in Ohrid. So still an amazing city, and I wish I could have visited it. So with that, let us move on and start talking about the elementary reactions or incorporation into crystals. And folks, this is what we'll talk about. So crystals grow because molecules approach kinks, and how they approach this issue of diffusion and convection. So these issues are mostly understood. They've been understood for about 20 years. But then what is the chemical reaction at the kink? Let me choose my pointer. We want a highlighter. No. We want a laser pointer. There we go. So once the molecules approaches the kink, a chemical reaction occurs in which bonds are broken between the solvent and the molecule, and new bonds between the solute and the solute in the crystal are created. So this is the issue that we will discuss. How does this reaction happen? And you heard the word solvent, which means that we'll be talking about solution growth. And all these crystals that you saw yesterday to twist and to twirl and to dance, they're grown in solution. Well, when the general public thinks about crystals, it doesn't think about these crystals. It actually thinks of crystals like that you can put in a golden setting and wear on a finger, or put on the finger of a lady of your choice. So these are diamonds. Well, just so you know, diamonds grow from solution, and it's a solution, of course, in molten iron, but the processes of growth of diamond crystals are very similar to the process of growth that we will discuss. There is steps, and the steps interact, and the carbon atoms have to join the steps, and there is activation pairs and all of that. So the world market of diamonds is about $42 billion a year. So it's a very good contribution to the overall market of crystals in the world. Now, the biggest market of crystals are pharmaceuticals. These are very humble compounds, small, not very conspicuous, not very pretty. Now, the world market happens to be $1.3 trillion a year, which is about 1.5% of the world's GDP. So this is a very serious contribution. And that's why we are focusing. Now, most pharmaceuticals are organic compounds, and that's where we're looking at how organic compounds form crystals in solution. So, of course, solution crystallization has been with humans since before the dawn of civilization. This is a picture from the first book on material science, Terra Metallica, on the production of metals. And this is book 12. It was published by Georg Agricola, or Georg Bauer, in 1556, and for about 3 centuries, it was the most popular book on material science. So look what we have. We have a crystallizer here, and then we have the source, which is seawater, which is flown into our reactor, and then we have the heat source, which is the sun. And then I find it fascinating that we have the tools of how to collect the ready crystals. We have this rake, and we have the shovel. So, you know, the whole production process is this one diagram. And Agricola writes that the history of salt making in salt banks and so on goes further back than human records. So this is older than, probably as old as civilization. Human records start about 5,000 years ago. Civilization started about 10,000 years ago. So you do the math. Excellent. So let us now begin to talk about how crystals grow. Contrary to the general belief in the broad scientific community, crystals do not grow by molecules attaching to flat crystal faces. Molecules may attach to flat crystal faces. They have very high probability of detaching back into the solution. They may diffuse along the crystal faces until they reach a site which is suitable for incorporation. And this site has been identified in the 1920s by a German scientist named Kossel and a Bulgarian scientist working in Germany named Stransky. And they said that not only do you need a step, but you need a kink on the step in which a molecule may incorporate, and they define the uniqueness of this site both from thermodynamic and kinetic points of view. And now there is this caveat. Kossel and Stransky were thinking about crystals made of cubes, the so-called Kossel crystals, and then the crystals for them were going out of vacuum, which may be a distant equivalent for growth from a gaseous phase. So they didn't really think about activation barriers and kinetic coefficients. So those considerations came a little bit later. And if so this is what brings us to the introduction by Jim. So what we'll be talking about is what determines this activation barrier here, the activation barrier for incorporation of molecules into kinks. And see, the problem is that in order to discuss the elementary reactions that occur at the kinks, we need to focus on the scale of about fractions of a nanometer, because the molecular size is about 1 nanometer. So everything happens somewhere here as the molecule approaches the kink. Then there are very few kinks on the surface of the crystal. The density of kinks is 10 to the negative 3 or less. So it means that out of all the molecules at the top layer of a crystal, only 1 in every 1,000 is a kink. So then the kinks are dynamic. So actually when a molecule joins, the kink moves. So if you're looking with a high resolution technique, you wouldn't know where to focus. You have very short time to deduce what the reaction is. So this is extremely difficult to deduce. So to observe directly, so what we decided to do is to employ the chemical approach. And I think this is very appropriate to report at this meeting, because this is the meeting of the chemistry of the organic solid state. So how do we use the chemical approach? Well, we use 4 different solvents. So we use DMSO, which is a small molecule with 2 methyl groups. We use butanol, which has 3 methyl groups and 1 methyl group. Hexanol, which has a little bit more CH2 and CH2 groups, and octanol, which is even longer alkane chain. And by recording the differences in the dynamics between these 4 solvents, we'll try to deduce how the molecule enters the kink and what are the elementary reactions. And of course, we will supplement all the conclusions. We will test the conclusions that we make from this chemical approach with all item MD. And well, fortunately, the conclusions from both methods coincide. So in the end, we'll have a pretty complete story about what happens at the kinks. All right, so this is our test system. This is the molecule of a thioporphyrin 1. It contains a porphyrin ring, which is about 1.5 nanometers in size. There is delocalized electron density, which renders it some very favorable optical electronic properties. But very importantly, there is 4 side chains which have conformational and rotational degrees of freedom. There is 4 methyl groups and 4 ethyl groups. And these degrees of freedom lead to significant asymmetry of the crystals, such that the crystal has only translational symmetry. The space group is P1, and this actually increases very much its value as an opticoelectronic material. This is how normally a crystal looks. And today I'll only be talking at processes that occur on the 010 phase. This is most often it shows up in the atomic force microscope as the basal phase. Here you see the structure of the crystal. It has stacks of ethyl-porphyrin molecules, and that's it. So these stacks are roughly in the 101 direction along the crystal. So this is ethyl-porphyrin. And then, as I said, the porphyrin ring and the disordered side chains determine its electronic properties. So we used atomic force microscopy to study how the crystals grow. All these experiments were carried out by Rajshri Chakraborty, who graduated last year and now has an extremely successful career in the pharmaceutical industry. So this is what we see. We see a dislocation outcrop. This is at the beginning of this arrow. And this dislocation produces spiral steps. And of course, because the crystal is highly asymmetric, the steps in different directions move with extremely divergent velocities. So they move extremely fast in the A direction, positive A direction, and very slow in the negative A direction, and roughly similar velocity in the positive and negative C directions. And now if we monitor the step along the positive A direction, we can see that the step gets progressively further from the dislocation outcrop point, and we can actually measure these distances. And here is the distance between the step and the dislocation outcrop point as a function of time, and this is at several different values of the concentration. And as you can see, all of these data show that the steps move at a steady rate, pretty much always. And then we can define the velocity of the steps as the slope of the correlations between the step displacement and the time. So that's excellent. So then we have the step velocity, and the step velocity will be our main criterion to judge about how the chemical reaction occurs, because clearly the step velocities need to scale with the rate of the chemical reaction at the kinks. All right. So here are the step velocities as a function of the concentration of ethyl-porphyrin in the solution in 4 solvents: butanol, DMSO, hexanol, and octanol. We have highlighted DMSO in red because it's the only one that is not an organic alcohol. And we have scaled the concentration with the solubility. Now, remarkably, the solubility in the 4 solvents is different, but the driving force for the reversible reaction, this is just elementary chemical kinetics, should be proportional to this difference and not to the concentration in itself. As we said, this is elementary chemical reaction. So then, as we said, we have a chemical reaction between the molecule and in the solution and the kink. And in this case here, we choose to model this as a bimolecular reaction between the solids and the kinks. And then we can write this very simple equation that the step velocity is equal to bimolecular rate constant Ka times this difference in concentration. And A is the distance that the step propagates when one molecule joins the step. So it's about 1 nanometer. And of course, in order for this Ka to be constant, we need to have constant kink density, because as we said, it's a bimolecular reaction between kinks and steps. And so only in the kink density is constant, Ka will be, we will include this kink density into the chemical rate constant Ka, and we get the constant. Now, Jim's introduction referred to a step kinetic coefficient beta. So normally the step velocity can also be written in this way. So we have omega, where omega is the volume that the molecule occupies in the crystal, times beta times the same difference C minus CE. And if you compare these two relations, clearly this product is equal to this product. And very simply, we get that beta would be about 10 to the negative 4 meters per second, or about 100 microns per second, which is comparable to many small molecule systems. So, so far, nothing weird about etaporphyrin 1. You will see the advantage of using this formulation as I speak further down the road. All right, so let us see what are the values of Ka that appear from this approach, and here they are. So here they are. So we have gradually decreasing bimolecular rate constants with increasing length of the alcohol, of the solvent alcohol, and then DMSO is somewhere between butanol and hexanol. But of course, we know that all reactions in solution, their rate scales with reciprocal viscosity, and these are the viscosities of the four solvents from materials constant databases. And then if we use the product of Ka times the viscosity, this is something that contains intrinsic reactions at the kink, we get that the four alcohols have constant product, Ka times eta, whereas DMSO is about factor of 2 lower. So this is something that we have to think about. We'll have to explain why would DMSO be slower than the other two solvents. So let us see what may be the reason for that. And for there, we'll try to deduce the processes and parameters that govern the bimolecular rate constant for the reaction between molecules and kinks. So, well, before we dive into this analysis, it's very important to answer the questions, how do molecules reach the kinks? So there is, because the kinetics that we measure would be affected by that pathway. And if we want to really discuss the intrinsic chemical rate constants, we need to know that we have eliminated all transport issues of access to the kinks. So there are two pathways by which molecules can reach the kinks: direct incorporation, which was mostly developed by Alex Chernov, although there was a suggestion in the PCF paper that this should be the preferred mode of growth from solution. And then there is the surface diffusion, which for solution was suggested in this paper by Gilmer, Gies, and Cabrera from 71, and before that by Professor Pete Venema. So here is how we're going to discern between these two pathways. We are going to monitor the growth of steps of single and double height. So single height steps are 1 lattice parameter high, and double height steps are 2 lattice parameters high. And, and then as a second independent test, we're going to look at the dependence of the step velocity on step separation L. And there are analytical expressions developed in these two papers that show that in the case of direct incorporation, the effects of H and L are scaled with this parameter here. As a result, they become very small. So their effect becomes about 1% at normal values of step velocities and diffusion lengths. And essentially, in the case of direct incorporation, the step velocity should not depend on the step height and the step separation, whereas in the case of surface diffusion mechanism, the step velocity should scale reciprocally with the step height and depend very strongly on the step separation. If the step separation is more than a certain critical value, as we will see here. So what does etaporphyrin do? Well, here we have on the surface double height steps like this one highlighted with the green arrow, and single height steps, and we can see how they move. And these are actually the profiles of the steps extracted from these 4 images. And this is time 0, and this is time 68 seconds. And as you can see, it seems the double height steps move as fast as single height steps. And this is true for 3 of the solvents that we study. There is about 30 different steps of each height in each of these bar plots. So folks, there is no doubt that single and double height steps grow with similar velocities. And then we go to the distance, to the correlation between step separation and step velocities. And the horizontal error bars actually highlight the ranges of step separation at which the measurements were made. As you can see, we go all the way to steps which are about 10 nanometers apart or 20 nanometers apart. And no matter how close the steps are, they move with the same velocity as steps which are as far away as 1 micron apart. So clearly, the step velocity is independent of step separation in all of the 4 studied solvents, and surface diffusion is not the mechanism by which the crystals grow, and we have direct incorporation. Now, this is actually excellent, folks. This makes our problem so much easier because now we know exactly what the bimolecular rate constant is. It's the true rate of the reaction between the molecule and the kink. All right, so here is that reaction. We have the kink, and we have the molecules approaching. And if this is the reaction, such reactions have been modeled with the following expression, where the pre-exponential factor K0 is the diffusion limit of the rate constant, and this diffusion limit has been defined by Smoluchowski in 1918. We've modified slightly the Smoluchowski's expression because the kinks recruit molecules only from half the space, and then the kinks are immobile, so we don't include their diffusivity here. And then we have to include the kink density, which is probably about 1/3. As we alluded there, we'll discuss the constancy of the kink density. And then we have the diffusivity in a diporphyrin solvent. So this diffusivity scales with the viscosity, and as we saw, the viscosity is kind of serious. So overall, we get that K0 is of order of 10 to the 8 per mole per second. This is slightly slower than what you normally get for small molecules in aqueous solutions, but we explained why we have this lower value of the diffusion limit. But regardless of this, folks, look, our rate constants that we measured were about 10 to the 4th. The diffusion limit is 10, this should be 10 to the positive 8. I apologize for the typo. So clearly, the reaction is much slower than the diffusion limit. So the reaction is not diffusion limited, and delta G double dagger, which is the free energy barrier for incorporation into kinks, is substantial. It is very serious. So then we have to explain where does this delta G double dagger comes from. And to do this, we have to turn to the classics. So in order to answer the question, what factors determine delta G double dagger, we turn to the classics. And Chernoff was the first one to address this issue, and many people believe that this is his greatest scientific achievement. So this is what he wrote, and I'll be translating from Russian. It says here that at the crystal solution interface, the solvate shell forms and decays, and this requires significant greater activation energies. So Chernoff says that the activation energy is due to the interaction between the solvate shell. So the solvate shell needs to decay so that a solid molecule can enter the kink. Very good. So we actually can test that statement right away. There is the solid molecule, there is the kink, and there is a solid shell here. So we can test how the strength of the solid-solvent interactions and see whether the activation barrier correlates with the strength of the solid-solvent interactions. How are we going to do that? We're going to use the free energy for crystallization, which in turn we can measure by measuring the solubility and the temperature dependence of the solubility. And here is the logic. So the free energy of crystallization is the difference between the free energy level in the solution and the free energy level in the crystal. And there is one caveat, and this is that the free energy level in the crystal needs to be the same in all solvents. And here are XRD spectra of crystals of a diporphyrin grown from all solvents. You can see that they're identical, so we know that this level is the same. And by using delta G for crystallization for all 4 solvents, we can determine both delta S, the thermodynamic delta S for crystallization, thermodynamic delta H for crystallization, and delta G for crystallization. And look, folks, what we see. We see that there is 3 solvents which show pretty much the same values of delta G and delta S. but these three solvents do not exclude DMSO. Actually, DMSO is among these three solvents. The odd one out is butanol. And this is not how the activation free energies work. So this suggests that this picture may not be right. And so here is the picture suggested by that concept of the strength of the solid-solvent interactions. So if the interactions between the solid and the solvent are weaker, this would be butanol here, then butanol would have the lowest activation barrier, so butanol should grow fastest. Whereas the other three solvents, hexanol, DMSO, and octanol, should have slightly bigger free energy barriers for interaction. The crystal should grow slower and equally fast. Well, both of these predictions are false. So it means that this is not the picture of how the molecules incorporate into kinks. And the only way to reconcile the observations with the possibility the solvent is involved in the determination of the activation barrier is to assume that we have an intermediate state. So there must be an intermediate state which is most stable for DMSO, about equally stable for these three solvents. And in this way, DMSO has the highest activation barrier. The other three solvents have weaker activation barriers, and that's why growth from DMSO is the slowest. So here is the DMSO with the highest activation barrier, about 14.3, and then kilojoules per mole. And then here are the activation barriers for the other solvents. So how do we test that? What is the nature of this intermediate state? We're going to use MD simulations. Before that, we have to identify the growth unit. Folks, in the interest of time, I will skip the identification of the growth unit. I will just tell you that the growth unit is a monomer. We tested the possibility whether it can be a dimer. It is not a dimer. We actually wrote a paper about it, which we will be publishing in the further discussions volume. So you can check it out there. The growth unit is a monomer. So we're free to continue with MD simulations with the growth unit as the monomer. And here is one trajectory of the growth unit. You can see a diporphyrin monomer enter a kink. So we have highlighted the last molecule in the kink here. Let the movie replay. Do you see here that there is this molecule, before it enters the kink, it gets stuck at an intermediate state? Now, this is very unusual. This is highly unexpected. So it appears that the molecule doesn't just slide into the kink as one would expect, but the molecule actually stops exactly at this intermediate state that our experimental results suggested. And here are other data from these simulations. This is the dependence of the height of the molecule as a function of time. You can see that the molecule is far away from the kink, and then it enters this intermediate state, and then it enters the kink. And then here is something very interesting. So clearly, the solvents affect the intermediate state because the number of solvent molecules, this is DMSO, but still in the intermediate state, the number of solvent molecules is less than in the kink, but more than in the kink, but less than in the solution bulk. So that's how the solvent molecules participate in the stability of this state. So let us look at more generalized ways to look at these MD simulations. What you see here is the free energy relief of a molecule approaching a kink as a function of the separation from the kink and the number of solvent molecules, because we saw that the number of solvent molecules is important. So we have one global minimum, which is right here. And this is clearly the molecules in the kink. It's already part of the crystal, so nothing to do with it. The interesting part is we have another local minimum. Here is the local minimum. So this local minimum is about 0.4 nanometers higher than the global minimum, than the position at the kink. And whereas at the kink, this etaporphyrin molecule is associated with one solvent molecule. In this local minimum, the molecule associates two solvent molecules. So this is the kink, and this is the local minimum before the kink, and these are the number of solvent molecules that correspond to that system. So these simulations are the simulations in DMSO. Let us see what happens in the other solvents and what do they tell us about the activation barrier. So the activation barrier delta G double dagger, we extracted from the projection of this 2D plot onto the z-axis, and this is what we see. Now these plots for the 4 different solvents were shifted such that the minimum, the local minimum coincides, so that we can more visualize the value of the delta G double dagger. And what you see is delta G double dagger is slightly higher for the MSO and about the same for the 3 alcohols, exactly in correspondence with the experiments. And then the question is, why is the barrier for incorporation in the MSO higher than in the alcohols? And here is the answer. The answer is that the number of solvents in the intermediate state changes. So we have the difference between the intermediate state and the global minimum. We have 2 molecules of DMSO. We have 1 molecule of butanol. We have about 2/3 of a molecule of hexanol, and we have half a molecule of octanol. Now, all of these whole molecules and fractional molecules, they contain 4 CH3 or CH2 groups. This is normal, so that's how much fit in the gap when the molecule is intermediate state. But the interesting part is that with DMSO, we have 2 molecules. With butanol, we have 1 molecule. Here we have fractions of molecules. And which means that DMSO, the molecules can adjust better. They can fit themselves better with the configuration of the solute, both the incoming and the one in the crystal. And that's why DMSO stabilizes the intermediate state during growth for DMSO is the most stable. So this is all because of greater conformational freedom of the 2 DMSO molecules in this gap. All right, folks, so these are my conclusions. Crystal growth kinetics, complemented by molecular simulations, reveals the elementary motions that comprise the chemical reactions in the kinks. Etaporphyrin 1 incorporation into kinks passes to a metastable intermediate state, in contrast to classical theories. Solvent dynamics in the intermediate state determine the height of the incorporation barrier. And it's very important that I do not miss thanking the people who did this work. So Rajshri did all the AFM work. Lakshman, who is a student co-advised by Jeremy Palmer, my colleague in my department, and me, did all the NV simulations. Viktor Hadjiev helped Rajshri with identifying the crystal growth unit, which was a very important part of the project. This is my group at U of H, and they all, of course, helped with different aspects of the experiment and the simulations. And this work was generously funded by NSF, a little bit by NIH, and the simulations part funded by the Walsh Foundation of Texas. So thank you very much for your kind attention, and I'll be happy to answer any questions you may have.
Thank you so much for your interesting talk. So please, if there is any questions, raise your hand and introduce yourself.
I'm Maggie Lingenfelder from EPFL. Thank you very much, Peter, for the wonderful talk. I have a general question, because it seems the more we look into the nanoscale and the more we can identify the nuclei, the more we see examples of non-classical nucleation pathways. So my question is more like, if you were to guess, or with information you have, it looks like non-classical is actually more common than classical, at least in the organic world, right? What is your...
Folks, I cannot hear what is going on there.
Maybe Jim can also comment.
It seems that you're muted on Zoom.
Or now?
Now I can hear it.
Hi, Peter. I'm Maggie Lingenfelder from EPFL. I was asking you because my take here is that the more we look into the nanoscale and the more we are able to identify nuclei, the more we see examples on non-classical nucleation pathways. And my question to you is like, is really the non-classical nucleation pathway, now that we can get more into the nanoscale, really the most common one compared to classical nucleation pathways, maybe from the inorganic world? What is your appreciation on this?
So this does not relate to what I talked about today, but the statement kind of corresponds to what my observation is, that the most of the recent papers have been on non-classical mechanisms, but then it's possible that people get excited when they detect non-classical nucleation, and that's why those papers got published, those cases got published, and they get prominence. I'm not sure that non-classical nucleation will be the overwhelmingly general mechanism. I still think that in every case we need to look carefully, no matter how annoying it is. We have to do the due diligence and determine the mechanism of nucleation, because it's possible that sometimes we will have classical nucleation. And that's what I think.
Hi, I'm Chagai Cohen from the Weizmann in Israel. It looked like that the terrace width was pretty regular, pretty uniform in the examples you showed. And on the other hand, the L value was relatively large. So I wonder if you can give a kind of a qualitative insight into what determines this. The L value.
Which is the L? What L do you mean?
The terrace width.
Oh, the terrace width. So the terrace width, it's determined, it's not a parameter of growth. It's one of the growth characteristics. So at low supersaturations, in general, it's high. At high supersaturations, in general, it's low. But it depends on how the layers are generated, on how fast they move. It depends on the line tension of these layers. It depends on the step width, because the step is not straight, the step meanders, and so it has a finite width. So there are many, many factors that determine L. So that's why, as you saw in our experiments, it varied from a few nanometers to 1 and 1.5 microns. If you're asking how can we control it, we don't. We just record it. I mean, we look for steps that are far away and we measure their velocity, and so we look for steps that are close by and we measure their velocity.
Excuse me.
Apologize for that.
But why was it so uniform? Was it a general observation or just the pictures that you gave? So it looked like a uniform width of the terraces. And I wonder about the...
No, it wasn't. It was by no means uniform. The terraces were highly anisotropic. So we have twin steps and single steps, even in the one direction. I guess we're looking at a relatively narrow window there, and it may have appeared that it's uniform because we're only looking at 3 or 4 steps, and there is numerous steps following one another.
Okay,
So no,
thanks.
it would be misleading to assume that the separation between steps is uniform.
Peter, I have a question for you about the simulations. First of all, it was a beautiful talk. Thank you. It's really great.
Yeah.
I have a question about the simulations. You must have chosen a variable along which to sample the pathway. It looked like the molecules came in with a certain orientation. Of course, they could come in with any orientation. So how did you decide on the bias sampling?
So we ran simulations with three control parameters. One was the separation, the other one was the number of solar molecules, the third one was the orientations. So you saw simulations at the very last steps when the orientation of the molecules were already affected by the kink. And of course, close to the kink, the molecule orients close to parallel to the other molecule which preceded it. So that's why it may assume that it's misleading, but no, the orientation of the molecules was not constrained.
I see. Okay.
Most certainly not.
All right. Thanks. I guess the second question is more general. You've made the argument for many years, and I guess many of us have, that it's really getting rid of solvent that is the main barrier to getting molecules into a kink. And so is there a general lesson here about crystallization, or do you think that everything is system specific? In other words, in this case, there's an intermediate state where you're partially solvated. Should we expect that generally, to have intermediate states with partial solvation?
We should expect it generally. There is one exception if you have spherical ions or molecules, like for instance sodium chloride. It's possible there won't be an intermediate state. So they should be spherical and they should be about the same size as the solvent. So sodium chloride from water, the chloride ion is about 2 nanometers, water is about 2 nanometers. So it's possible that there will not be an intermediate state there. But anything different, so even if you have spherical molecules which are larger than the solvent molecules, you will have an intermediate state because the solvent molecules will not be detaching all simultaneously. They'll be detaching one by one. And especially if you have asymmetric molecules, non-spherical molecules, like most of the molecules that we're interested in, definitely there will be an intermediate state. I'll go further than that. There may be more than one intermediate state. So we're very lucky that we only had a single dimple in the free energy landscape. It's possible there will be several dimples going there. So, to go back to your question, the depth of these dimples depends on the solvent. It's just that the solvent effects are much more elaborate than what initially was assumed. That it just depends on the interactions between the solvent and the solute, and we have one activated state in which the bonds with the solvent are broken and the bonds with the solute are not yet established. No, it's more complex than that, that this is what our results reveal.
Okay. Thank you.
If there is no question, I think we can thank Peter Fakilov for the second time for his very interesting talk. And
thank you, folks.
Thank you so much for joining us remotely.
Thank you.
And we all hope that you completely recover very soon.
I hope so too. Thank you.
Thank you. I think we can now proceed with the second speaker of this session, Dr. Magali Lingenfelder. I would like to give a very brief introduction over her. She is the head of the Max Planck EPFL Laboratory for Molecular Nanoscience in Lausanne. Her work combines interfacial chemistry, surface physics, and biomimetics for the design of nanostructured materials. She studied physical and biological chemistry at the National University of Cordoba in Argentina. She continued with her doctoral studies in Germany and received the Otto Hahn Medal of the Max Planck Society for the microscopic understanding of the chiral recognition process with submolecular resolution. She advocates for problem-oriented interdisciplinary research, and today she will show us a case study that goes from the fundamental understanding of protein surface interactions to the design of antimicrobial surfaces for biomedical applications.
Maybe because, well, it's okay. Yeah. Okay. Thank you very much for the introduction. It's a pleasure to be here. It's my first time in this conference, so thank you very much for the organization and for the opportunity to share a bit of our work, which focus on two-dimensional crystals, so focus really at the interface. And before I go into the topic of today, I would like to introduce you to my group because As you've just heard, we use concepts from interfacial chemistry, from surface physics, and from biomimicry, because our goal is to mimic the functionality of biological systems for different applications, but using a much simpler system. So we go into the nanoscale where we can use a reduced number of materials and avoid all the complexity of the biological structures, focusing just on the function. And then we aim to mimic that function, but as I said, using much simpler system. That's why we go into the nanoscale. And in my group, we look at many different processes where crystallization plays and growth plays an important role, and especially the dynamics of these nucleation and growth processes. So the applications we are looking at include host-guest switches, chiral recognition, also artificial photosynthesis, so two-dimensional layers which are catalytic for energy conversion. And today I would like to describe only one of these systems, which is the use of two-dimensional systems for the creation of antimicrobial surfaces. And the inspiration here again comes from nature. So if you look at the structure of dragonfly wings, for example, you will find that that the nanostructure of the wings of this insect has some pillars which act as antimicrobial system without using an antibiotics. So because the bacteria can interact at this interface, and then these pillars will penetrate into the cell wall and kill the bacteria. So people have tried to reproduce this property with artificial systems, for example, using silicon pillars. And this is one of the inspirations we have to study nanostructure interfaces for antimicrobial properties. And what are the different approaches that one can use to achieve this functionality? Well, one is, as I said, just putting the antibiotic directly on the surface so that you can release the antibiotic, or you can use this contact kill surface where, as I said, act with these pillars, penetrating the cell wall, as it happens in the case of dragonfly wings, or you can also use antifouling surfaces, where you just try to either by steric repulsion or electrostatic repulsion, or just having surfaces with low surface energy, that the bacteria does not interact directly with the surface. So in one case, you kill the bacteria, in the other case, you just avoid the interaction of the bacteria with the surfaces. I cannot translate from Russian, but I was in the library the other day, and I think I can translate from French now. And this is really the big picture of the problem. So this is to give you an overview of the magnitude of the problem. So if you look at this history of Earth, and these guys over here are the bacteria. You can see these lines crossing so unfortunately, I cannot really use this pointer well, sorry. I don't know if you see here. So these lines crossing here are massive extinction events in the history of Earth. And you can see how bacteria are still happy there, and we are a point somewhere over here. So in the long scale of things, of course, bacteria will win, right? But keeping that in mind, so the bacteria were here long before us, and they will evolve, and they'll probably be here long before we are gone. But that doesn't mean that in this moment of time and space, we have a problem in fighting antibacterial resistance. So bacterial resistance to antibiotics, because that's the way we have in this moment of time as history to fight bacteria. Because bacteria are beneficial in many places. So bacteria are everywhere and not necessarily are bad for us. So for example, in our guts, they are good. But in some places, like in your teeth, they can form this, what is called biofilm, which is like bacteria grow,
or on the surface of biomedical devices, as catheters, for example, they form these biofilms. And the problem when the bacteria are attached to a surface is that they are much more resistant to antibiotics because they start to communicate with each other and form these nice films, so they segregate this extra polymeric substance that make them much more resistant to antibiotic. So I think it's like they are 1,000 times more resistant when they are forming this biofilm than when they are just alone in the like floating state. So that means that when bacteria colonize these biomedical devices, they not only are more difficult to kill, but they are also promoting new drug-resistant strains of bacteria. So if you look at the predictions, and I think now in the middle of the pandemics, people are more sensitive to talk about these case fatality rates and all these numbers, right? Because we are used to hear like how many people are dying from just a tiny nanovirus, and now we are more sensitive to think of how, for example, the prediction says that by 2050 we will have extra 10 million deaths a year due to antimicrobial resistance because our antibiotics are not working anymore and the bacteria are becoming more and more resistant. And there are two main strains that are top priority of the World Health Organization. One is Staphylococcus aureus, that is methicillin resistant, and the other one is Klebsiella pneumonia, which is a multi-resistant bacteria, and this is in Europe, but this is already in 2011, they were becoming more and more resistant. And now, if you look at places where it's particularly a problem, as I said, is on the surface of biomedical devices. So just an example, 50% of patients with cardiovascular devices are having infections. And then in healthcare-associated infections that start, for example, at the surfaces of catheters. Catheters are a direct way for bacteria to enter our body and to start an infection because the medical doctors have to change the catheter many times, and that gives a direct way. So, of course, at the beginning I showed you that one way to create surfaces that are antibacterial is to control the hydrophilicity of the surface. But you have to think that when you are going to design a material that will be in contact with your body, so the bacteria will not see the material you are exposing, but they will see this material covered by a layer of plasmatic protein, for example, in the case of a catheter that goes in contact with blood. And you have to take that into account, of course, because you cannot put a superhydrophobic surface inside your body. You will have thrombosis and other effects, right? Or the formation of clots in your body. So one has to go first into the fundamentals and look at protein surface interactions, because that's the first step that you will have when you have the catheter, for example, in your blood, is that it will be covered by this plasmatic protein. So today I want to show you a story that goes from these very fundamental studies of protein surface interaction and crystal growth on surfaces to a real application. So in this first part, I gave you some magnitude of the problem, and now I'm going to go into the details, talking a little bit more about protein surface interactions, then how can we control the assembly of proteins at the interface, and then how we can use these basic concepts to design new antimicrobial surfaces. So let's first start with a model system. Of course, we want to go to simple models where we can understand protein surface interactions. And this is a model, it was already introduced by Jim, and we took this model from his studies. This is what is the model of the S-layer protein, the superficial layer protein. And this is a beautiful model for us because, of course, First is very general, so bacterial surface layers are two-dimensional crystals that form the outer layer of many archaean bacteria. It's really interesting to see that they are the most abundant protein in the related organism. So you can see here this micrograph that shows how these bacteria are covered by this beautiful two-dimensional crystal. Depending on the organism, you can have different crystal structures. But it's also a really beautiful, and I have to say, they are both present in gram-positive and gram-negative bacteria. And they are beautiful nanoscale templates for us, because one good property of this protein is that you can extract it from the organism, and then you can recrystallize it on different solid surfaces, and you can conserve the crystal cell, so the same crystal structure that you have in the organism. And that makes them perfect model systems for us. And Bart was a PhD student, so apart from taking this model system from Berkeley, the other good thing that happened to me is that when I was in Berkeley, I met Bart. He was a bachelor student at the time, and he moved with me from Berkeley to Lausanne to continue first with his master's studies and then with the PhD. And he was the guy setting up this system here, where we can do continuous flow atomic force microscopy in situ. And by combining this high-speed atomic force microscopy with continuous flow condition, we could resolve the dynamics of this interaction of protein with surfaces from several seconds to multiple hours by keeping the concentration constant, because we are flowing the solution of the protein. So doing that, we can look at how is the process on a solid surface to end up with this beautiful two-dimensional crystal of the S-layer protein. So I'm going to show you a video here that you will see from the starting. So we start to put the protein on the surface. You will see that it starts nucleating and growing, and that you have two different areas. So one is a lower islands that look darker in the AFM image, and a brighter zone. This is a different conformer on the surface. And if you look at this here on top, you can see the time scale, and I'm going to play it again so that you could see, you can identify the different processes taking place from the monomer absorption to the condensation into an amorphous cluster. This is, again, a non-classical nucleation pathway that will then relax and grow and have this conformational change. So we start with the protein on the surface. And as you can see, it's growing, and you will see some of these darker areas converting into these brighter areas, which is just a different conformer. And if you zoom in the structure, you will find the crystalline structure of the S-layer protein. So by counting the number of islands and the coverage over time, we can learn a lot about the system. We can identify 3 different regimes. By the way, this is an AFM picture of 500 by 500 nanometer. And that means that we can identify, as I said, 3 different regimes. We can go more into details here. So I show you the first phase, which is the regime where you see the assembly of the protein on the surface, then the nucleation, and then the growth, and then followed by this conformational change where you can interconvert from one conformer of the protein to the other. And you can work out the equations that describe all these different regimes that I'm showing you here. You can see, for example, the blue curve that shows the low conformer, and then at certain points they go over by this high conformation, which is the green curve. So that's also a way to see that they are interconverting. But I'm not going to go into the details of the equation itself. It's just for you to keep in mind that we have these 3 different regimes where we go from nucleation, growth, and conformational change, and we can describe that by looking at the processes really happening at the nanoscale. So using atomic force microscopy allows you to identify, as we saw also in previous talks, the mechanism that we have at play for these two-dimensional crystals. Now that we look into the growth of these two-dimensional layers on a surface, let's have a look at how we can control them. And this goes back to the system itself, how we can control protein crystallization on surfaces, but also to a very basic question. When you have a surface, you will have certain chemistry, you will have certain symmetry, and then you will have also certain topography. So what is the relative weight for the protein when it goes to crystallize on a surface of all these factors? You will, of course, be influenced by the chemistry of the surface, by the symmetry, but also by the topography. So we wanted to understand, in the case of protein crystallization, which were the factors which were more determined for our system. So for that, we used a system which is called block copolymer thin films. We thought this was the perfect system because our collaborator, Ilya, could synthesize these two-dimensional films where you have basically the block copolymer is just one hydrophobic polymer covalently bound to a hydrophilic polymer, and then you can spin coat them on a surface, and then you end up, depending on the volume fraction of the blocks, and of course you can choose also blocks with different lengths and different mass and different annealing procedures, but then at the end you end up with a certain pattern that grows over the whole surface. So it's really nice. You can pattern even a whole wafer with them if you want. And what was interesting for us is that we can now tune very precisely the distance between the hydrophobic and the hydrophilic domains. So we have a surface where we have a very well-defined hydrophilic domains, but overall, the surface is wettable, so we can fully wet the surface, but when you go into the nanoscale, you do have different information about the hydrophilicity. And that, it's a way that we can use to order the proteins on the surface. So just to show you a comparison before we get into the results, if you have an isotropic surface like mica, you can see that you have all these different domains of the protein. If you just have polystyrene, you will see that the protein still assembles on the surface, but it has much smaller domains. And then on polyethylene oxide, which is the hydrophilic part of the surface, the molecules don't really want to nucleate, so it's very difficult to see proteins on this part of the surface. So we put these together, and another thing is that here, in these block copolymer films, you can have an area, which is, as I said, hydrophobic, hydrophilic, hydrophobic, hydrophilic at the same distance. And I can push them with the tip of the AFM, so I can see exactly the same area, so I can identify where is the protein going, and I can see that it keeps the same crystal structure, and it goes really into the PS areas only. So I can guide the protein just by using this non-specific chemistry to crystallize only on the PS areas. And this is also, of course, a comparison here is just an example of this confinement of the protein, but there is also a factor in the alignment of the protein, because if you plot here the number of crystals versus the orientation with respect to the main axis of your pattern, you will see that most crystals go aligned with the pattern. And it's not only about the size of the crystal, so this comparison with the mica, because here we don't have any preferential alignment, and also with the PS, again, we don't have any preferential alignment, but we see it when we have this line of the PSPO, and this is not only about the preferential orientation along the line, but also the fact that you have larger crystals along these lines. So if we look again at the kinetics of the process now on the block of polymer thin film, then we can see, again, this non-classical nucleation pathway where we go from an amorphous nuclei that then restructures into this order crystalline domain, and they're trying to avoid the areas where the PO and it are growing around these areas. And there is not only the fact that they are going to this PS area, but if you look at the growth rate, both for nucleation and growth are significantly increased when you have the block of polymer film as compared to when you have the PS or the PO alone. And this is, we think, because you can, the surface have both information, not only that you have areas of high interfacial energy where the molecule doesn't want to go, close to areas with low interfacial energy, so you're kind of concentrating the molecules around that areas, and then you can see this enhanced nucleation and growth of the protein on the PS areas, yes. So what about, I told you that it's really interesting to use these patterns, not only to study nucleation and growth on these nano pattern systems, but also to be able to differentiate if we now have two surfaces where they have the same topography but different chemistry. So on the first example, I show you hydrophobic, hydrophilic, hydrophobic, hydrophilic. Now I show you the same similar topography, but now I prepare it using another polymer in a way that I have the same chemistry exposed over the whole pattern, and I repeat similar experiments, and what we found is that if you only have topography, that's not enough to guide the assembly of the protein. You still have some effect on the directionality of the crystals, but that's not enough to fully guide the assembly to one particular area. So this is the summary of what I'm showing you here, is that when you have these isotropic surfaces, then crystal can grow in every direction and at the same speed. But if you confine this system with this chemistry also and topography, then you see really an enhanced nucleation and growth along the main direction. And if you just have the topography but not the chemical information, well, not the hydrophobic, hydrophilic information, then you will see enhanced growth in one direction, but you will still be able, in a slower growth mode, but you still be able to cross these lines. This example is for proteins that are really beautiful, as I said, two-dimensional crystal, a great system for surface scientists because you can really go into the structure and see the nucleation and growth. What about more flexible molecules? We wanted to see if this block of polymer could also guide more flexible molecules, and for that we use collagen. So here I show you how collagen organizes on mica when you have low and high concentration, and they form these beautiful bundles. But now if we do the same study on the PSPO, you see you can guide the assembly of the collagen again, following the underlying pattern. So that means this contrasting chemistry of the block of polymer thin films can be used to direct the self-assembly of beautiful crystals, but also on proteins that are much more flexible. They still will feel the presence of the pattern. And now, in this second part, I want to show you how these simple concepts that we learn by looking at how proteins grow on surfaces can be applied then for the design of antimicrobial surfaces. And this is a collaboration we started with Claudia Reitman. She's a medical doctor. So we met in a conference and we were discussing this thing of the problem of the catheter infections and so on. And then she was looking for surfaces that we can use to try to avoid this problem. And that's why we started trying if we could use the same concept now, but of using these block copolymers, but to organize plasmatic proteins. And we did many experiments with different plasmatic proteins, and we saw that basically our model could be used there also, because we did see the segregation of the plasmatic proteins into these block copolymer films. And then, as I said, she's a medical doctor, so she could isolate directly the multi-resistant bacteria from the catheter, or from the tip of the catheter of a patient who had major bloodstream infection due to initiated at the catheter. And this is interesting because, of course, you can do experiments of antimicrobial resistance with a reference line, but it's not the same because the biofilms that this multi-resistant protein grow are much more difficult to kill, let's say, when they are from real bacteria, from real infection, as compared to the labile films that are grown from references strains. So she isolated, as I said, this bacteria for the catheter, from the catheter. And then she made this susceptibility testing, just to show here, this is the way they can test and how effective are from this exclusion zone here. They can know, this is tabulated, how resistant is the bacteria to all these different antibiotics. So first she isolated the bacteria and then demonstrated that it's really resistant to all these antibiotics. In fact, the person who had this infection died from the infection because none of the antibiotics they were using could be effective against the infection. And then we tested how effective are our surfaces in comparison to other models for these antibacterial properties. So here I'm showing you the biofilm on the polyurethane material of the catheter compared to flat silicone. So these are without any topography or any chemistry information. And then I show you how the bacteria looks like on our surfaces. And you can see immediately that on the TPU catheter, you form this really thick, unstable biofilm. And when you go to the flat silicone, you still see this secretion of the EPS. So bacteria is still quite healthy. But when the bacteria are in contact with our surfaces, they are basically very few attaching, but the ones that do, they die because they look all like deflated. And we think this is because we increase, so we leak this cytoplasmic material from the bacteria, and that's why they look all like deflated. The way to really quantify this is to look at the number of colony-forming units on these different materials at a certain moment in time. And then you can see, so this is the TPU, the glass, the flat silicone, compared to nanostructure interfaces. And nanostructure interfaces where we use this controlled protein absorption, which is this block of polymer films, where we can really guide the assembly of the plasmatic protein. And there you see that we have a reduction in the number of colony-forming units. So that means that the surface is quite effective in killing the bacteria. So, but then we started to think, okay, how can we apply this, right? And then we needed to go into materials that are directly used for these biomedical devices, and one is the chirurgical TPU. So we went to contact Claudia Simao. She's an expert on plastic materials, and she was using this nanoimprint lithography to transfer from the solid surface, like from silicone patterns, into these plastic surfaces, so that we could also test the effect of the micropatterning on the antimicrobial activity. So we did this, again, for Klebsiella pneumonia. We're looking at the number of viable bacteria, of colony-forming units, and we tested different configurations, and we found out that the pillars of around 1 micrometer on this TPU material were the ideal for the antimicrobial activity. And this is because you are basically imposing a physical barrier for bacteria to communicate, so they cannot form this biofilm. But still, here, you are not having information for the protein, so this is effective for killing the bacteria, but not really a good system when you're going to be in contact with proteins. So after many experiments, what we did was to combine these two systems. So using the micro pattern that we can directly print on the catheter material, and then covering it with this block of polymer thin film in a way that at the nanoscale we can control the positioning of the proteins and therefore the local points, and then the bacteria will interact at certain local points where it could attach, but the size of the micropattern is around the size of the bacteria, so that then in this way you stretch the bacteria and you activate these mechanosensitive channels, and therefore by controlling the interaction of the protein with the surface, then you use this nanopattern to control the interaction of the protein with the bacteria in a way that it stretches mechanically and it dies just based on chemistry and very simple interactions, so you don't have to put any antibiotics there. Just to show you how does this compare with some other approaches in the literature, we got a reduction in the number of, in the colony-forming units, which is to show the antibacterial properties of 4 to 5 logs in the reduction, which is much better than even the natural system where you have these dragonfly wings or the replica of the dragonfly wings with silicone. And the advantage is that you can now do it also on plastic surfaces, so you don't need to do it on silicone, but you can really do it on materials which are more compatible with what are the materials already used in biomedical devices. And this is just a comparison of similar method using pillars, but activated with magnetic fields and so on, which are more complex systems, but which are not necessary if you just use, as I like to say, the power of chemistry. And then, so to summarize all this part, we really started this project looking at nucleational growth of crystals on surfaces. But when we learned about how we could control this process using this confinement at the nanoscale, then we could even use it in a realistic system. So I like to take this, to tell this story here, and I took this example because I think it's a very beautiful example of how starting with very simple concepts, you can do something which is applicable, and you can, if you're really open to collaborate with all the different actors, right, and all the different expertise. And I want to pass on this message because I see nowadays science going very much into the individualistic, right, and in the superstar people and how, like, you publish 120 papers or whatever. And I think for the students, the message here is, like, you have to keep your eye open and really focus on the science and what you want to do and what you want to achieve, and you cannot do that alone. You have to look for collaborations. You have to think about the problems together. It's much more fun than being a lonely star. So, and with that, I would like to thank all the people that make this work possible. As I said, I'm having a lot of fun in my group because we have this medical doctor close to an ultra-high vacuum machine doing antimicrobial experiments, where other one is measuring atomic interfaces for catalysis. And this is, I think, for me, a privilege because I work with all these amazing people. I learn a lot from them. And also, I had some funding that people had given us for supporting our crazy ideas that sometimes work, sometimes don't, but at least we could try. And then, in general, I show you, as I said, I choose only one example that I like particularly because it shows this transfer from really very fundamental to very applied. But in general, I think the growth and looking at the dynamics of nanostructural systems will have a huge implication in many different areas, because if you look at surface science, traditionally it was a field that evolved from ultra-high vacuum, from really very well-controlled environments. But nowadays, we do have the tools to get into very detailed studies also at the solid-liquid interface. And at the solid-liquid interface, it opens up a huge range of possibilities, not only for these biointerfaces I just shown you now, but you can think about reconfigurable, adaptable interfaces, how to control them with magnetic fields, with electric fields, how to explore these functionalities of nature, but really using much simpler systems. The same applies, for example, in catalytic systems, where by controlling the interface and the active sites, and we can now even identify the precise location of the active sites. So I think this field is going to evolve a lot using a surface science tool at the solid-liquid interface in the next year, and we will go really from these very fundamental studies to more applied systems. That's at least my perspective, and I wanted to share it with you here. And with that, thank you very much for your attention.
Thank you so much. Very nice talk about protein self-assembly and design of this antimicrobial agents. So I think we have just room for one or two questions. So if there is any questions, please. Yes.
Thank you. Very beautiful talk. Igor Sokolov from Tufts University, United States. My question about these systems is like, you probably heard already several times, because of these crevices in realistic systems where you have a lot of proteins, these crevices should be like filled pretty quickly, usually. And then bacteria probably should start growing as usual. Secondly, bacteria, when they start forming films, they typically produce first extracellular matrix, which also would fill this stuff. So, like probably might be delayed rather than exterminate bacteria, delay the growth.
Yes, that's a very good question. Yeah, but what I can comment is from the studies we have so far, we inhibit the EPS segregation on these patterns. So that's why we kill the bacteria at the end, because, I mean, you don't, when the bacteria interact with the surface, it cannot just absorb everywhere, right? And then, once they cannot communicate, in fact, maybe I can show you, I have it probably here. Let me just look one image here. So they try to, so if you look at the system, you do not see this is not working, no? Okay, but just look at the one in 2C, where you see that the bacteria are deflated, right? So we don't see the secretion of the EPS and the formation of the biofilm. And I think that's key to avoid the biofilm formation. Yes, if they will form and will start to form the biofilm and secrete EPS, then I agree with you, it's too late. But we stop the process before that.
You mentioned the two-dimensional crystals in the earlier part of your talk and the conformational change thereof. There are 17 two-dimensional space groups. Were you able to assign them? And when you look at that conformational change, do you see a change in the space group?
Oh, that's a very beautiful question. I hope we will be able to do that, but the honest answer is no, we cannot do that. Because in AFM, you have you can see the crystalline structure, but you cannot see you don't have information, submolecular information about the structure itself. So I know that there are two different conformers because I see a tiny difference in the height, but I don't have like crystallographic information to assign those to a particular group, no.
Is there any other questions? So if not, I would like to ask also a question. So according to what I understood, the surface can influence the kinetics of the self-assembly and also the flexibility of the protein. So is there any other properties which is influenced by the type of the surface that you use?
Sorry, which other properties you mean apart from?
Yeah, for example, the crystal that you will obtain in the end and other properties related to the crystal that you will have.
Of course, when you have any crystallization process or self-assembly process, not doesn't necessarily need to be crystallization on a surface, you have to take into account three main factors. One is the interaction, so the symmetry and the chemistry of your surface, interaction molecule-surface, then interaction molecule-molecule to form a certain crystal, how commensurate or not is that crystal with the surface, and how strong are the interaction between the crystal and the surface, and also crystal, in the case of solid liquid, with the solvent. So what your final polymorphic outcome depends on all these factors. So yes, it's difficult to predict, but of course, if you have a very strongly interacting surface, you will be able to affect the crystal structure of what is crystallizing on the surface. But if this interaction is just a guide, as I show here, but not too strong as to distort the crystal structure, then you will be able to conserve the native form.
Thank you very much. So now is the time for a coffee break, but please be back at 11 because we still have 3 more interesting talks. So see you back at 11.
button. Yes.
Does it? Okay. Great. So welcome back to the second round of Crystals That Growth session. I would like to introduce you the third speaker, Dr. Asaf Gal. He did his graduate studies under the supervision of Leah Adadi from the Weizmann Institute of Science in Israel. Now at the same institute, he is a research leader at the Department of Plant and Environmental Sciences. His group is studying biomineralization, which is related to the ability of organisms to form complex inorganic materials at ambient physiological conditions. These intracellular processes proceed under strict biological control, giving rise to spectacular morphologies that are superior to any man-made material. They strive to understand the biological and chemical toolbox that cells use in order to form these extraordinary structures. In his talk, he will discuss mechanisms of biological control over crystals morphologies. Please.
For the opportunity to present here. It's also my first time, and I will continue on the lines that we heard and go even deeper into the realm of biology and talk about organisms and how they control the productions of crystals. What I would like to emphasize in the talk is that we already learned a lot about crystallization from biology, but we still have a lot to learn. And I will start with an example for what biology can do with crystals and with crystallization. And these are all examples for crystals of guanine, which is a simple molecule that is abundant in any cell, in any organism from all the kingdoms of life. And these organisms are using guanine to form crystals. And these are not just crystals, these are functional crystals that can have a function for the organisms. And what you see here in these examples are many different kinds of organisms, from spiders to fish to chameleons, that produce these guanine crystals, and they pack them in configurations that make an optical function. So when the crystals are just scattered like that, they give a white matte color, but then the fish can arrange them in orientations that give iridescence and even specific colors. And when they control the packing of the crystals, this color can also be adapted and changed. And in order to achieve this degree of functionality of the crystals, it is clear that the organism needs to control any aspect of this crystallization. And you can see in these high magnification images how the crystals look like. So they take the same guanine crystal, and in one species, they pack it into these square light arrays that function as the mirrors. And in another organism, they pack it in this hexagonal packaging that is functional for creating the color. So it looks like they can do almost anything they want with this simple crystal. And what I like about biology, that if you want to go to the most sophisticated examples of crystal engineers, you can go to the most simple organisms. Because it so happens that unicellular organisms are, in my subjective opinion, the perfect masters of controlling crystallization. And what you are looking at here are examples for two groups that create minerals. These are not organic, these are inorganic minerals. Some of them are not even crystalline, but it seems that they can do whatever they want with these inorganic minerals. So these are diatoms. These are unicellular photosynthetic algae that are present everywhere. And in the first evening, we heard from Panche that we even have endemic species that are living also only here in this lake. And they make a cell wall that is made out of silica. And the group that I will be focusing here in this talk are the coccolithophores that are covering their cells with specific scales that are covered with crystals of calcite, calcium carbonate. And maybe not all of you heard about these two groups before, but they are vastly important for many different aspects in the world, because they are so abundant in the marine environment, and because both of them are photosynthetic, they are responsible for about 30% of the production of oxygen from the marine environment. And because the coccolithophores that are producing these calcium carbonate scales, when the cells die, the calcium carbonate sink to the bottom of the ocean. And over the geological time scale, they accumulated and gave rise to this chalk formation. This is a very famous chalky formations from the shores of England, but they stretch all below the European continent from England to the Middle East. So you see, this is responsible even today to 50% of the sequestration of carbon to deep sea sediments in the form of these calcium carbonate particles. So today people are very interested in understanding how these physiological processes will be affected by the anthropogenic changes that we are introducing into the marine environment. Because we are putting CO2 into the atmosphere, and this CO2 is going back to the ocean, and now there is a big question: what will happen to these organisms? On the one hand, they will, the additional CO2 is helpful for photosynthesis. But on the other hand, they are producing calcium carbonate, and calcium carbonate is more soluble when you are reducing the pH. So which one will be more affected, and how this will affect the entire processes, ecology, environmental geochemical cycles that are happening in the ocean. Now, in order to answer or to address these kind of questions, we need to zoom in from this big ball of the Earth to a much smaller ball, which is the cell. And here in this movie, you can see the formation of these calcified scales. We call each scale a coccolith. This is what these cells are doing. And you can see that the cell is producing the crystals inside the cell. This is an intracellular process. And only when the calcite scale is mature and it is ready, it is exocytosed outside to the surface of the cell when it is accumulated until the cell has completed the entire shell. And this characteristic of the process, we are talking about crystallization process, inorganic crystallization process, but it is happening inside an organelle, membrane-bound organelle that is located inside the cell. So how to combine the chemical process with the biological context was a real challenge for many, many years, because usually we cannot really study chemistry inside the biological context. So for many years, what we used to think is to take the concept and the principles that we know from chemistry, from crystallization, and to assume that they hold to what is happening inside these organelles within the cell. So for example, the rate at which the crystals are going is maybe related to the supersaturation levels inside the organelle. And how the nucleation of the crystals is regulated, this is probably caused by epitaxy from a surface that I will show you in a minute. And stereochemical interactions are probably important for the regulation of the growth and the nice shapes that we see, and so on. So we were taking concepts and the ideas that we know from solution chemistry and applying them for what is happening in biology. And the one message that I hope they will be able to convey in this talk is that it's not just as simple. Because one very important thing is that inside the cell, we don't really have a bulk solution in the sense that we used to think about it when we think about crystallization. Because everything is very, very, very confined. And it's not changing the basic principles of chemistry and physics, but it is changing the rules of what is important and what is not. So by studying for many years the extracellular minerals, people have a very good characterizations of what are the components of these coccoliths. And this is what I want to show you here in this slide. So there are three important components that give rise to this structure. First are the crystals. The crystals of calcium carbonate, it's in a radial array of crystals, and they are arranged in an interlocking array because there are two different kinds of crystal units. What you see here in dark blue and in light blue. And these units don't only have a specific morphology and specific shape, they have a specific orientation. One of them has the C-axis of the calcite lattice vertical to the plane of the structure, and one of them has its radial to the side of the crystal. So everything about the crystals is controlled and oriented, but the crystals themselves are quite boring. They are very clean, just calcium carbonate. On the outside of the crystals, we have a sheath of soluble organic macromolecules. It's very thin, and it's covering each one of the crystals. And the third component is an insoluble organic scale. We call it the base plate, and this is an elliptical scale that it's like giving the baseline for the architecture of the coccolith. So taking these components and the conceptual toolbox that we had, 30 years ago, Steve Mann and Jeremy Young proposed a general model to explain how coccoliths are regulated and formed by the cell, and it was termed the VR model due to the vertical and radial orientation of the different crystal units. And what they suggested is that there is a common theme throughout all the species, and this theme is that we have an alternating array of V and R units of the coccoliths. What is responsible for this oriented nucleation of the V and R units is this organic scale, the base plate, which is the surface. For some, by some mechanism, it is inducing epitaxially the nucleation of the crystal in the right orientation. And then later on, what is happening is that the crystals are growing and assuming this species-specific morphology because there are specific interactions with proteins or other polymers that are interacting with the calcite crystals to expose different crystallographic facets that will give rise to the specific morphologies. And this is a concept that we are using for 30 years. But it's a conceptual model. We don't have any proof for any part of that because it was so difficult. Now, luckily, in the recent years, there is a surge of development of technologies that now allow us to try and tackle the process in situ, the formation process, and see what is true, what we can learn, what are the new things that we can learn from biology. And main tool that we are using in my group is electron microscopy, and specifically cryo-electron microscopy and tomography, which is now becoming a very powerful tool in order to understand many different kinds of biological reactions inside the cell. So how it is happening? We are growing the cells, and it's very easy to grow them. We don't need the lake, we don't need the ocean. We only need 50 milliliters of seawater, and the unicellular algae, they grow very fast. And then we take the cells, as they are forming the crystals, we just put a droplet of the cell on a transmission electron microscope grid, and we vitrify it by plunging it into liquid ethane. Vitrification is very important because the cooling is so fast that even the water molecules, they don't have the time to rearrange into ice crystals. So everything is locked, is frozen in its native state. We don't use any fixation, any staining, and then we can take it into the electron microscope and just look at things as they were when the cells was alive and calcifying. Of course, entire cells are too thick for a transmission electron microscope, so we need to have another preparatory step, which is to remove some of the material with a focused ion beam, and what we are left with is a very thin lamella, about 200 nanometers in width, in the middle of the cell, and over there we can collect the microscopy data. So this is how this lamella looks under the transmission electron microscope, and we're doing the tomography. Tomography, basically, it's like a CT scan. We are tilting the sample, collecting many images, and then we can reconstruct in 3D the volume that was in this 200 nanometers lamellae. And this we can do with very high resolution and to gather a lot of details. For example, what you can see here is a snapshot from a very small area inside the cell that we can see the membranes, we can see the crystals in the blue shades. In purple, you see over here the fibers of the organic scale, and we can have a very good resolution of what is happening inside. So what we did is to collect many, many data sets like that, and because this is a growth process of the crystals, we can assemble a putative timeline of what is happening throughout the development of the process. And this is a schematic. This is how the stages roughly look in the real data. And one message that I want to convey, that it's very complicated. It looks nothing like crystals that is growing from a homogeneous bulk solution. What you're looking at each one of these time points is just the edge of the organelle in which the coccolith, the crystals, are forming. So we see the membrane. This is a lipid bilayer that is enveloping the organelle, limiting the space. We see this base plate. This is the organic scale in these shades of purple, which is a very complicated organic template. We see in red, these are very dense calcium-rich particles, which are polymers that are complexing in calcium ions. And then we see the crystals growing and developing and morphing. And this is a very data-rich images. So what I would like to do is to highlight some of the lessons that we learned from going through many, many of these data sets. So the first is about the initial steps of nucleation. Because what we saw is that in the periphery of these scales where the crystals are nucleating, initially what we see is a very dense substance that later on give rise to the crystals. And this opposes the view that there was some epitaxial recognition between the baseplate and the crystals. So when we look on different base plates from different species that give rise to very different crystal morphologies, the base plates are very similar. Basically, this is a very flexible organic structure that gives the overall elliptical structure. But the nucleation of the crystal is not really happening by a heterogeneous nucleation from a solution that is in contact with the base plate. Instead, what we constantly see is that on the right places where the crystals are going to grow, we first see the formation of a dense phase that is rich in calcium. This is calcium polymer-rich phase. And this is like a detour that biology takes in order to direct the nucleation to the right place. Because what biology does is to create an intermediate phase that is very rich in calcium. This is one important ingredient for the nucleation of the calcium carbonate, and is directing it into the right place. And this polymer ion complex, which we call coacervation, is something that is specific to the surface. Because calcium and negatively charged polymers will anyway form aggregates and nucleate. And when we put a high concentration of both of them, we see the formation of this dense phase on the base plate, but also everywhere. And this is a problem for a cell, because then the crystals will go everywhere. But if we are choosing the right concentration of calcium and polymer, then we can get a specific targeting of this dense phase to the right place. And we think that this is what is happening in the cell. The cell is first forming or advancing the nucleation of a specific dense phase on the right place, and only later nucleation will start and will happen wherever the calcium is most abundant and concentrated. Now, when we start to think about dense ion phases, we start to see them everywhere. Here you can see a different kind of microscopy. Here the resolution is much lower, but we can see the entire cell. And with this kind of microscopy, we can also identify where we can see high calcium-rich phases inside the cell. And you can see that it's not only the blue things, which are the coccolith that I was showing you. There are storage organelles that are different. This is not where the crystals are going, but they are packed with these red balls that are, again, calcium-rich phases. So we need to think that when we leave seawater, seawater is a solution. Not very dilute, but in seawater we have soluble ion. When these ions are getting into the cell, we need to stop thinking about solutions. Because inside the cell, what is happening is that these ions are moving from one dense ion phase to another one, until the final one, which is the crystal. This is where the cell wants them to be. But in order to understand these processes, we need to think about dense phases and how ions can move between one to the other, changing the chemistry, changing the stoichiometry, until they reach the final destination, which is the formation of the crystal. Another interesting thing is to think about the degree of confinement in which these crystals are going. And this is just a nice anecdote, a back of the envelope calculation. Because from the electron microscopy data, we know what is the volume in which the crystals are forming, and we know how much of that can be an aqueous solution that is not occupied by crystals, dense phases, organic molecules, and etc. And what we saw when we are doing these calculations is that if we are putting into this volume 2 protons, we are normally changing the pH from an initial pH of 8.2 to a final pH of 7.8. And this is the expected ocean acidification at the end of the century if we will continue to put all the CO2 into the atmosphere. And this ocean acidification is going to affect extensively many marine organisms, specifically calcifying organisms. But inside the organelle, there is no physical meaning for one proton getting in or getting out, because just the flux of calcium carbonate, ion transport inside, is so much larger. So if we want to understand what is the effect of ocean acidification or crystallization inside the cell, we cannot just take the kinetic factors and do extrapolation from solution that will be affected by pH to what is happening there. Because the nominal pH value is no longer the important factor, because it is reducing to 1 proton here or 1 proton there. So how do the crystals grow? Well, they grow differently than how they are growing inside a solution. And one thing that we constantly see is that in such a confined environment, the membranes that are molding, they are just there like a barrier, can imprint their shape into the crystals. You can see that throughout the growth of the crystals, the membrane are very, very close to the crystals, and I'm talking about a few tens of nanometers. And when they are so close, they are stronger than the tendency of the crystals to grow, and just thus molding their shape into the crystals. But on the other hand, there are places that we see crystallographic facets and crystals that are going as crystals should be. And at this stage, this was quite a surprise that when a crystal grows crystallographically, it's grows very similar to what we used to think about ion by ion addition to a crystal, like we just heard. So we see all this crowded environment, and we see these dense calcium-rich granules. But as we go closer and closer to the surface of the crystal, these granules diminish in size. And this is what we interpret, these intermediate particles dissolve. And eventually, when the crystals are going, they are going ion by ion. When they came, they will form crystallographic habit. When there is a membrane, they will just stop because it's there. But the process, in this case, is quite simple when you go to the basic mechanism. And now in the second part of the talk, I will focus on a specific work that we finished recently, made by Emmanuel Avrahami here, a great PhD student in the group. And what he wanted to do is to try and dive even more deeper to this question and understand the morphological evolution of the crystal, like mechanistically, how one morphology is going within a specific species. Or in other words, this is like an intermediate stage of the crystal. You see it's complicated, you see the crystals. How the final morphology is going to be like this. So this is a specific species. I'm going to describe a work that we did on that, even though it is a general concept. And you can see that also in this species, we have this alternating array of R units and crystal unit. And this is the final morphology that this species attain. So the first step that Emmanuel did is to take cells and to extract from them intracellular coccolith. So coccoliths that are at intermediate stages. And because this is, again, a growth process, we can put them along a putative timeline and see how this morphological evolution is going from this very initial ring of crystals until the final morphology. And what I would like to see from this time sequence is that even though there are surfaces that are clearly a mold of the membranes and they are not crystallographic, there are many other surfaces that are crystallographic in nature. This is where crystallography is playing a role in dictating the morphology. But this is not the simple crystallography of calcite, so we want to understand how this is coming into place. And in order to have a better look into that, Emmanuel didn't settle only for the two-dimensional SEM images, but he, again, collected electron tomography, which will be able to give us the three-dimensional architecture and organization of the crystals. So from each one of these growth stages, he went to the microscope, collected the electron tomography data, and then segmented in 3D 4 crystals. And the resolution is good enough that now we can see the entire shape, how they're interlocked, and how they change with time. And again, by collecting several data sets, what we saw is the morphological development of the crystals from the very initial stages to the final stages. This is how one unit looks like, this is how the other one looks like, and this is how the two of them are forming this ring that is going to be the coccolith. And again here, there are places that this is clearly molding of a membrane, but clearly you see the crystallographic flat places of the crystals. And then we went and asked the questions of, okay, so what are these crystallographic planes? Because we were expecting to see very different crystallographic facets that are going and giving this convoluted morphology. And playing with the three-dimensional data, what we saw is that when you are looking on these very initial crystals, they resemble the rhombohedron of calcite, which is what we are expecting to see for this lattice. So this is the C-axis, and here you see the three rhombohedral facet. Some of them are not complete because there are other crystals that are going one into the other, but it's more or less what we would expect. When we compare it to the mature stage of the crystal, Actually, what we see is very similar. This is the C-axis, and here you see the free rhombic facet. Now, these are the same facet, but what you see is that their growth was very uneven, anisotropic. This yellow facet was going very slow. This is why it is so elongated, while this purple facet was going fast, 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 and this is why it is so small. So looking at this data, we saw two things. We saw, from the one hand, that only the stable crystallographic facet of calcites are the facets that are expressed crystallography in the crystals. What we also saw is that these symmetry-related facets are going anisotropically. One of them is going fast, the other one is going slow. And then, of course, when we realized that, we were a little bit shocked, because these two things that I just said, they are impossible to be together, because symmetry-related facets are identical. Nothing can differentiate between symmetry-related facets. And this is an important point. This is why I want to linger a little bit about it. This is a crystal, and when this crystal will go isotropically, we will see just a bigger morph of this crystal. And this is okay. This is the simple way that we are thinking about crystal growth. But you can say, okay, this is old. We know how to engineer crystals. We know how to introduce anisotropy to crystal. And okay, but usually the way that we are doing it is that we are taking a crystal and we are letting it grow in the presence of some other molecule or additive that will interact with a new crystallographic facet, make it grow slower, therefore to express it, and then you will get an anisotropic growth of the crystal. And this is okay, and by extrapolating this, you can get to a very different shapes of the same crystal. But what we saw here was different. We saw that this crystal is going in this way. The same crystallographic facets are going anisotropically. And again, this is impossible because they are identical. And it took us a little while to understand what is the problem, because of course this is possible. This is what we see in nature. And we understood that what we are doing is wrong, because it is true that it is impossible that the intrinsic properties of the crystal will give rise to this anisotropic growth, because the crystal intrinsically is identical for all this symmetry, and nothing can interact with that. But what biology can do is to play with the environment, which usually we just think, okay, the environment is isotropic, it is diffusion, the diffusion is making the bulk solution very isotropic. But like I showed you, inside the cell, this is not the case, because these crystals are going in a very confined environment, which is confined by the membranes of the vesicle. And what we propose is that this is the toolbox or the playground by which biology can play and sculpt the crystals. Because when you think about it, if you have this confined environment, and confinement is about 10, 20 nanometers, then diffusion can no longer be a factor that is homogenizing everything. And if you have, let's say here, many ion pumps that are transporting the building blocks through this location, then you can form gradients inside the environment. And gradients that are forming heterogeneous environment can give rise to heterogeneous growth of the crystal, even though the facets are symmetry related. And we went back to the data, and we were looking for examples if we can really see that this is the mechanism that is at place. And from some cases, we see this kind of behavior. You are starting with an isotropic crystal, and this initial crystal that is somewhere here is going anisotropically towards a preferred direction. And this explanation is kind of nice how to explain. Why? Because here we have the source of ions, and then this mass transport is dictating which facet will go fast, because they are close to this source, and which facet will go slow. But I think that this scenario can explain even more complicated cases that we saw. And this is the example here. Because in this example, what you see are 4 facets, all of them the same facets of calcite. They are facing the same environment. They are very close to each other. So they are seeing the exact environment because they are so close and they are having the same orientation. And nevertheless, always the orange facets will go faster, win, and cover the blue ones. So something also here is breaking the symmetry and making one facet going faster than the other one. And actually, the anisotropic environment can explain it because even though they are identical facets, they have the opposite orientation. One is like that, and one is like this. And because they have opposite directions, and calcite, the growth states of calcites are not symmetrical, one has an obtuse angle and another one has an acute angle, then this is the way when symmetry is breaking. Because for one crystal, the obtuse angle is looking or facing the high concentration part of the gradient, and for the other one, it is the acute one. So if the obtuse one is the rate limiting step of the growth, by putting it into the low concentration, you are affecting, and in the other crystal, then it will just continue to grow. So an heterogeneous environment in which the crystals are going can be a very powerful tool for biology to control the final morphology of the crystal. And I will finish with one final lesson that we learned from this data. And this is about the origin of chirality. The original VR model that I introduced to you is not chiral because we just have one unit with the c-axis perpendicular and one with the c-axis vertical. So over the years, what we thought is that chirality and the structure of coccolith is chiral. I hope that this is evident also from the previous images. We thought that chirality is induced by some chiral modifier that is involved in the process. But what we saw here, just by looking on these initial stages of the crystals, when the crystals are very boring in shape, these are just the rhomb of calcite, we saw that the orientation of the crystals is what is generating the chirality of the structure. Because even though calcite is not a chiral molecule and the rhombohedron is not a chiral structure, you can place it, you can orient it in a chiral manner. And this is what you can see here. So just by taking the simple rhombohedral building block and placing it in a chiral manner, then you are fixing the chirality of the crystals and you are giving rise to the chirality of the overall structure. Now, very interestingly, the chirality of the coccolith is identical. It's always the same. But this thing can have both chiralities. So again, there is a role for biology to determine which kind of chirality is related. But what I wanted to say is that this is something intrinsic to the growth of the crystals, and you don't need any external modifier for the growth or the chirality in order to achieve this complexity of the structures. Great, so with this, I'm finishing, wrapping up. And I hope that I convinced you with these 3 important points that I want to make. First, that now with the development of electron tomography, cryo-electron tomography, we can study crystallization, the formation of crystals, even without complicated environments such as cells, liquid environments, and so on. The second thing is that the biological toolbox to control how crystals will grow is not necessarily through stereochemistry or epitaxy, because biology can also work on the confinement of the crystallization process and heterogeneous environment within it, and this can have a very powerful tool for the development of the crystals. And eventually, this can give rise to the morphologies, structures of coccolith, that now we can understand this variety of structural morphologies, not in the sense of different factors, additive molecules that are interacting with that, but with crystallographic concepts. What is the initial orientation of the crystal? What is the rate of relative growth of different facets? What is diffusion limited and what is not? And this can be the part of the reason for how biology is controlling crystallization. I will finish by acknowledging the people that did the work from the group. Specifically, Emmanuel Avrahami and Yuval Kadan that did the cryo-electron tomography work. Yulia Mahamid from the EMBL in Heidelberg that taught us everything we know about this cryo-electron microscopy, which is now revolutionizing many aspects in biology, funding, and you for the attention. Thanks a lot.
very nice talk about the role of biology in crystallization. So, is there any questions? Okay.
So, again, wow, amazing.
Thank you.
I have a completely unrelated question to crystal growth, but it deals with coccoliths. There are these so-called whitening events where you have in lakes and in the ocean, all of a sudden, explosive calcification by coccoliths. Any clue why that happens? It's not the light, it's not the saccharides. What is it?
It's a good question. In my department, there is a different group that is studying, because this is the bloom. These algae tend to bloom. I think it is mostly related to nutrients. At specific seasons in the ocean, you have an upwell of nutrients from the bottom, and they just does boom, and you see even the color of the water is changing, because these algae, unicellular organisms, they can go very fast.
Amazing. I'm actually working just next to him, and I come here to listen to this work. You mentioned the conditions of growth. Did you get any indication of mutual influences, like the growth of one actually steals maybe ions from the other one, or anything like?
It's a great question, because this is what we want to do now. This picture that I showed is still a very qualitative picture, heterogeneous environmental controlling nucleation. Now we are studying different species that give rise to different morphologies, and exactly we try to understand, okay, so why in this species this is going so fast and the other one slow, and in different other species it will be similar? So far I don't have an answer, but this is what we are trying to do next.
Hi, this is fascinating talk. Thank you very much. So you mentioned that you can get both chiralities of the assembly.
No, I said that both chiralities are possible in principle, but in biology we only see one chirality for each species. So, and I don't know why, but definitely there is something external to the shape of the calcite that is determining which one it will be.
But do the coccoliths also determine this by the placement of the crystals, or does the control happen in some earlier stage?
I don't know, but what I think is that chirality is determined at the step of nucleation or very early growth, because we see this is where the structure is already chiral, and it is just rhombs placed on one of their edges. Now, what is determining this chirality versus the other one? In my perspective now, this has something to do with the anisotropy of the chemical environment inside the, and now I will say something that is completely putative. The ion pumps that are pumping ions into these vesicles are macromolecules, and they are chiral because any protein is chiral. So maybe they are fluxing or putting a flux which is like flowing, not really flowing, but has some chirality into it, and this is affecting nucleation. So the main message that I wanted to convey here, that we can rule out the option that stereochemistry is giving rise to chiral and to growth modification here, because there isn't any stereochemistry involved. It is the simple rhomb. There is something else that is chiral and is affecting nucleation and then the growth.
Thank you.
I don't understand this. Why not the stereochemistry of the saccharides in the base plate in determining the chirality?
Okay, I put it too strong. I cannot rule it out, the fact that, but we have evidence that the crystals are not nucleating in contact with the base plate. I'm saying it because this is still a work under progress. In some species, one crystal is enveloped by another crystal, so it cannot touch the base plate because it's completely enveloped by the other crystal. But you are right, because until I have a proposal for what is the mechanism of nucleation, I'm just playing with words. And this is something that we don't understand. I don't know what is controlling the nucleation. it's still a possibility that it is coming from a surface. I am exploring the option that it is not, but I still don't know.
But there are the coccolithozomes, zones, right? These are also kind of vesicles that contain saccharides, and they play a role in the nucleation, don't they?
I think that they play a role in transport. They are the carrier for transport of calcium. They are amorphous. They are not calcium carbonate even. This is calcium complex bipolysaccharide. I think that their role is in transport to supply this dense calcium phase that is needed.
But they're chiral, so when they deposit the calcium ions, they could play a role.
No, by themselves they are not chiral. They are amorphous.
Saccharides are chiral.
Yeah, but we don't see chirality in the particles. But this is an option, that chirality is transferred from the polysaccharides to the crystal. Yeah,
So you just mentioned the fact that you're not convinced that when they nucleate, they're in contact with the membrane to begin with. I purposely put the example in my overview of nucleation at a distance and made the point that the interfacial region is not just the surface. The ions in solvent are structured out to a couple of nanometers, right? So is it possible that all these things are not inconsistent, that the presence of chiral molecules and distance from a surface are connected to the nucleation, control over orientation on chirality nucleation?
Exactly, I agree. And I think that as humans, at the beginning we think it's either epitaxy from a surface or not, and at the end when we study biology we see that it's something in the middle, and this is the best explanation that I can give. There is a surface, it is active, it is doing something, it is not like heavy metals that are nucleating the lattice of the following crystal. We need to understand what it does.
Thanks.
Other questions?
Thank you for your talk. I have some experience of centrosymmetric crystals which can grow mainly in one direction. If you have, for example, perchlorate, ammonium perchlorate, and you evaporate a drop of liquid, you will see that inclusions are added up on one direction, and on the other side, the crystal is neat without any inclusion. And the direction in which it grows very fast could be identified. And then you see that the center of gravity of the initial crystal is moving, and then you can with insight look at how the crystal was when it was small, and it is also like what you presented, that the crystal, besides being centrosymmetric, has grown only in one direction almost.
Yeah, thank you. And now after we have seen this in biological systems, we suddenly see that there are other examples, and people have seen anisotropic growth of this symmetry-related facet. And the question is now, what is the mechanism? And because the biological system, I guess it is different from what is happening there. What are the similarities? And then we can melt all these things together in order to gain better control over crystallization. But definitely this is something that we... Perfect. Very interesting. We'll be happy to learn about it.
So I think we can thank Dr. Asaf Gal again for his very impressive talk. So next talk is a pre-recorded talk from Dr. Maria El-Handawi. She has earned her PhD degree from New York University in Chemistry Material Science under the supervision of Professor Panchanamov. She is involved in various interdisciplinary projects that require expertise on formulation, fabrication, and material
Good morning,
characterization.
Everyone. My name is Maria El-Handawi. I currently work at New York University, Abu Dhabi, in the Smart Material Lab under the direct supervision of Professor Panchanamov. So before I talk about my research topic in details, I'd like to summarize the idea of my talk in one slide. So one of the biggest problems we're currently facing is water crisis, where there's insufficient amount of water supply available to the rest of the population. And of course, this can lead to a decrease in the survival rate. And this is why we need to come up with new ways to extract excess water and try to meet the global demand. And I believe the best way to do so is to extract water directly from air, because there's a tremendous amount of water vapor locked in the atmosphere in the form of fog. And we know that fog can form in various regions around the world. So utilizing fog as a source of water is not actually something new. This has been done millions of years ago, not by us humans, instead by nature, where there are many plants, animals, and insects that have adapted to utilize fog as a source of water in order for them to survive. So if we can learn from nature, we can apply the same concept in our community in order to try and alleviate water crisis. So just to remind you again about the scale of the problem, what I'm showing you over here is a world map 20 years from now, where all the regions that are highlighted in red are going to be classified as severe water stressed area. And what this means is that the land is going to be extremely deficient in water. And of course, you could think of all the problems this could lead to. So it could lead to the loss of fertile lands, insufficient food and water supply, as well as political conflict between some of these countries. So it's already known that the most abundant resource present on our planet is water, and it makes up 70% of the earth. So why do we still face water crisis? Well, the main reason is because 97% of that water is seawater, and the process of desalination is extremely expensive and energy consuming. Therefore, we're only left with 3% of fresh water, in which 77% of that is locked in ice glaciers, and 22% is found deep underground and requires heavy machinery for extraction. So we're only left with 1% of fresh water in the form of lakes and rivers that are directly available to us. But unfortunately, the majority of these lakes and rivers are heavily contaminated, specifically in third world countries due to poor sanitation. And this is why we're currently experiencing water crisis. And we need to find new, non-conventional ways in order to extract excess water. And I believe the best way to do so is to revert back to nature. So one of the most interesting habitats present on our planet is the desert, because the annual rainfall is less than 100 millimeters per year, which means that the land is extremely dry. But despite that, you still see many plants, animals, and insects that can flourish in these areas. So again, if we can learn from these organisms how they extract and utilize water, we can apply the same idea in our community to decrease the severity of the crisis. So this slide is just to remind you again that despite the desert being classified as a harsh habitat, there are areas within the desert where the occurrence of the fog is really high. So we could have dense fog form in the UAE desert, in the Namib Desert in South Africa, as well as in the Atacama Desert in Chile. And you still see some plants, animals, and insects that have adapted and evolved to utilize that fog in order for them to survive. Indeed, these are some of these natural fog harvesting systems that I've summarized for you in one slide. So we can have a desert cactus, a desert grass, a beetle, all of them occupying the Namib Desert in South Africa. We could also have a desert moss, a desert lizard that occupy the Mojave Desert in the United States. And what do all these different species have in common is basically that they have evolved special surface traits that would allow them to extract water directly from the atmosphere. So in this project, we have decided to investigate the UAE flora in the hopes of finding a natural fog harvesting system or a natural water harvesting system. And while I was exploring the UAE desert, I discovered a special plant called terrace. And this plant is classified as a halophyte. If you're not familiar with this terminology, halophyte is a group of plants that have adapted to survive in extremely saline conditions. So what do these plants do is that basically they would absorb salty water from the soil and then filter the salt from the water and excrete that excess salt through the surface of its branches. And this is why if you take a closer look at the branches of these halophytes, you will notice that they are decorated with these beautiful salt crystals. But what is even more interesting about terrace is that in the early morning and late night, we've noticed that the plant branch was completely drenched with water. So based on this observation, we've kind of hypothesized that this plant could be a natural water harvesting system. But of course, we had to perform additional experiments to prove that. And one of these experiments is to acquire a 24-hour time-lapse video of the water collection cycle of the plant in its natural habitat. So what I'm going to show you in this video is that in the early morning, the plant would excrete a small volume of salt solution. And during the late afternoon, the water from the salt solution would evaporate, causing or leading to a deposition of salt crystals onto the surface of the branch. Now, what happens at late night is that the temperature is going to decrease and the humidity level is going to shoot up to 80%, causing the initiation of the condensation process happening on the surface of the plant branches. And from this result, from this observation, we've concluded that indeed, Tamarisk saphira is a natural water harvesting system. So again, just to summarize for you the water collection cycle in one figure, in the early morning, the plant would excrete a small volume of salt solution. In the afternoon, the temperature would increase and the water would evaporate from the salt solution, causing the deposition of salt crystals onto the surface of the branch. At late night, when the humidity shoots up to 80%, the branches will start to condense water directly from the atmosphere. So the first thing that we wanted to do is to study the mechanism of water harvesting. So how does the plant condense water directly from the atmosphere? And to answer this question, I've designed a simple experiment where I would take a small section of the plant branch, place it in an environmental chamber set at 35 Celsius and 75% RH to mimic the summer conditions of the desert at night. And then I would monitor the mass of water collected by the branch over a certain duration of time. In this case, it was 2 hours. So when the salt crystals were deposited onto the surface of the branch in its native form, we've noticed that it was capable of condensing 15 milligrams of water. However, when that same exact branch was washed and cleaned to remove the salt crystals and the experiments were repeated, we've noticed that it was capable of condensing only 1 milligram of water. So this was a clear indication that the plant harvests water through the salt crystals. So since the salt plays an important role in the water harvesting mechanism, we've decided to study its chemical composition in details. So the first thing that I did is to mechanically isolate the salt crystals from the surface of the branch. And then we've performed SEM-EDX analysis on the salt samples, which revealed that the major common elements present in the salt is sodium, chlorine, calcium, and sulfur. There were also traces of other elements that were present, as you could see from the SEM-EDX spectra, and these were magnesium, aluminium, silicon, and potassium. So since the SEM-EDX analysis provides us with the elemental composition of the salt, we had to revert to the PXRD analysis or the PXRD measurements. And these PXRD measurements were done by our collaborator, Professor Robert from Max Planck, and this analysis revealed that the Tamarisk salt was composed of at least 8 different minerals, where sodium chloride was the major component of the Tamarisk salt, and it made up 81% of the sample by weight. This was followed by calcium sulfate dihydrate, which made up 5% of the sample by weight. And there were other impurities attributed to the sand in the form of silicon dioxide and calcium carbonate that were also present. And this left us with 4 other minerals that were present in trace amounts. And these were calcium chloride, lithium sulfate, calcium sulfate anhydrous, and potassium calcium sulfate. So knowing that the Tamarisk salt is a natural sample, we've anticipated that the composition and the concentration of the salt could vary during different times of the year. And this is why we've decided to perform PXRD analysis on 4 different salt samples that were collected during different time of the year. And these samples were collected on November, February, May, and January 2021. So the first thing you will notice from these PXRD measurements is that the Tamarisk salt was always composed of the same 8 minerals. But what varied during different time of the year is the concentration of these minerals. So for example, in February 2021, the concentration of sodium chloride was 61% by weight, while in May 2021, the concentration of sodium chloride was 90% by weight. The same thing was observed in other minerals, such as the sand impurities, where they varied from 0.5% all the way to 10%. The same thing was also observed with calcium sulfate dihydrate, which varies from 4% all the way to 16%. So from these results, we could conclude that the tamaric salt is always composed of the same 8 minerals, but during different time of the year, the concentration of these minerals could vary. So now that we've studied the chemical composition of the tamaric salt in details, we've also wanted to study its physical properties, specifically the deliquescence point of the tamaric salt. So we wanted to understand at what humidity level will the salt start to deliquesce. And in order to answer this question, I've designed a simple calorimetry experiment where I monitor the heat flow of the sample over a certain duration of time. And during the measurement, I would vary the humidity level from 35% all the way to 85% RH. So the kind of result that we're looking for is a positive increase in heat flow, which indicates an initiation in the condensation process. So the first experiment we've performed was on the tamaric salt, which revealed that between 35% to 50%, the heat flow value was 0 by looking at the trough of the peak, which indicates that no condensation process took place. However, when the humidity level was increased beyond 55% RH, we start to see a positive increase in heat flow, which indicates the initiation of the condensation process. Therefore, we've discovered that the deliquescence point of the tamaric salt is approximately around 55% RH. So now the second thing that we wanted to do is to simulate the composition and the concentration of the tamaric salt in lab settings. And this is why we made our simulant salt, which was composed of 80% sodium chloride and 20% calcium sulfate dihydrate. Again, these concentrations were taken based on the PXRD analysis that I previously discussed, because sodium chloride and calcium sulfate are the major components of the tamaric salt. This calorimetry experiments revealed that our simulant salt deliquesces water at 70% RH, which is much higher than the natural tamaric salt. So from these results, we came up with two conclusions. The first conclusion is that the tamaric salt can deliquesce water at low humidity levels. And the second conclusion is that despite sodium chloride and calcium sulfate dihydrate being the major components of the salt, they are not the main components that contribute to the overall low deliquescence point of the salt. So there has to be traces of other minerals within the salt that leads to the overall low deliquescence point of the tamaric salt. And to prove this hypothesis, we've decided to add 1% of lithium sulfate to our salt simulant. We added lithium sulfate because it was one of these trace components that were present in the tamaric salt. And by adding 1% of lithium sulfate to our simulant salt, we were able to decrease the deliquescence point of the salt to 60%, which is close to the natural native tamaric salt. So again, just to conclude the results from the slide, it's the minerals that are present in minor concentrations that contribute to the overall low deliquescence point of the tamaric salt. So towards the end of the project, we wanted to understand what is the role of the harvested water. Does the plant utilize that water for it to survive? But before we can answer this question, we really need to understand how does the condensed water behave on the surface of the branch? And what I mean by that, does the condensed water drip from the surface of the branch to the ground where it gets absorbed by the roots? Or does the water remain adhered to the surface of the branch? So to answer this question, we need to know if the surface of the branch is hydrophobic and hydrophilic by performing contact angle measurements. But of course, we cannot perform contact angle measurements directly on the surface of the branch because it's extremely rough and uneven. So this is why I decided to extract the outermost layer of the branch or the leaves, which is the waxy layer, and deposit that on a smooth, flat surface. In this case, it was the silicon wafer. So after the successful deposition of the wax onto the surface of the silicon wafer, we've performed contact angle measurements using pure water and different concentration of salts. In this case, it was sodium chloride, calcium sulfate, and sodium chloride plus calcium sulfate. And in all these measurements, you would notice that there is a positive trend in the data, which indicates that as you increase the concentration of the salt, we're increasing the contact angle values. And this makes sense because it's known that the salts are capable of increasing the surface tension of water. Now, it's important to stress that the salt and the concentration of the salt is not the only factor that can affect contact angle values. We also have humidity and temperature. And it's also important to note that humidity and temperature can drastically change during the diurnal cycle in the local habitat of the plant. And this is why I've decided to perform additional experiments to study the effect of humidity and temperature on contact angle measurements. So we've obtained our contact angle measurements using two different types of salts. In this case, it was sodium chloride and calcium sulfate at two different concentrations for each salt. And these measurements were performed at two sets or two different temperatures, which was 21 Celsius and 35 Celsius. And these temperatures were chosen to mimic the summer and the winter conditions of the desert at night. So let's remove figure B, C, and D to simplify our explanation. Let's take a look at figure A only. So what I'm showing you over here is the change in the contact angle values by varying the humidity range. So the humidity was varied from 30% all the way to 90%. And in this measurement, we had the type of salt and its concentration fixed. So it was sodium chloride at 35 millimolar, and the temperature was fixed at 20 Celsius. So what you could see in this data is a negative trend where increasing the humidity level decreased the contact angle values. So the second experiment that I wanted to perform is at a different temperature. So I've decided to increase the temperature from 20 Celsius to 35 Celsius. And I observed the same trend, the same negative trend. So again, as the humidity level increased, the contact angle value decreased. So from this result, we can come up with two conclusions. The first conclusion is that as we increase the temperature, the contact angle values decrease. And as we increase the humidity level, the contact angle values also decrease. And this negative trend was observed in the rest of the data as well. So now we know that based on the salt concentration, the temperature, and the humidity, the contact angle values of these condensed water droplets on the surface of the branch could vary from 90 degrees all the way to 120 degrees. And because of that, we observed that some of these water droplets could drip from the branch to the ground where it gets absorbed by the roots, while other water droplets would remain adhered to the surface of the branch. But what is more interesting is that these water droplets that are adhered to the surface of the branch, we've discovered that the plant is capable of absorbing these water droplets through their leaves. And this mechanism or this phenomena is known as foliar uptake. And the way that these water droplets would enter the leaf is either through the stomata, if it's open, and if in case it's closed, it can diffuse through the cuticle into the leaf. Now, to prove that the Tamarix aphylla can undergo foliar uptake, we've decided to dissolve a fluorescent dye in a solution of water to form a fluorescent water. And what we did next is that we deposited our fluorescent water on the surface of the leaf, and then we monitored the pathway of the water using fluorescence microscopy. So as you could see from these results, the fluorescent water droplets were actually absorbed by the leaf, and this is why we see the green emission. So this clearly indicates that the Tamarix aphylla can undergo foliar uptake. So I would like again to summarize the key point from my project. So we've discovered a natural water harvesting system in the United Arab Emirates. We've discovered that the plant can excrete salt crystals, and these crystals play an important role in harvesting water directly from the atmosphere. And this is why we studied their chemical and their physical properties in details. We've also noticed that the composition and the concentration of the salt could vary during different time of the year. We've also studied the surface properties and the chemical properties of the branch in details. We've studied the effect of salt, temperature, and humidity on the contact angle values, the adhesive properties of the branch, as well as the role of the condensed water. And by that, I would like to conclude my slides by thanking the audience, as well as thanking my collaborators who worked with me on this project. Thank you very much. Good morning, everyone.
Again, very nice talk. So I am sure there are questions, but so you have already the list of emails on the participants list. So please find her email address and send her your. Oh, I didn't know that. So, yeah, very well. Hi, Maria, and nice to meet you. And thank you for joining us remotely. So please ask your questions.
Thank you. Very nice talk. And very natural question. Do you plan to make a device based on your findings? Mm-hmm.
Yeah, of course. So, so our second part of this project is to try and commercialize the salt as a device that can extract water from humidity. Sorry, to extract water from the atmosphere. And we believe that the best way to do so is to try and use the salt as a cloud seeding material, because in cloud seeding, and researchers use cloud seeding to initiate a precipitation event or the formation of rain. So and the idea of cloud seeding is the same concept as what the plant does. It uses these deliquescent or hygroscopic salt crystals to nucleate water. So we're actually, my second part of this project is to try and study the cloud, the tamaric salt as a cloud seeding material, and if it's efficient to initiate a precipitation method.
No questions? So thank you again, Maria. We are a bit behind time, so I would like to thank you again and wish you good luck. So we can... so I would like to introduce the last speaker of this session, Leah Javid. She is doing her PhD at the Weizmann Institute of Science and in the lab of professors Mir Lahov and Igor Lubomirsky. Today she will give a talk about the chemical nature of electrophoresis of supercooled water.
Hi, first, thank you to the organizers for giving me this opportunity. Today I'll be speaking to you about a molecular approach to the electrophoresis of supercooled water. So first, ice nucleation plays a really important role in a wide variety of fields, ranging from the cryopreservation of biological samples to food storage. It plays a role in climate science. Yet, and despite all of this, we don't have a complete understanding of the process. So what we do know is that ice nucleates according to classical nucleation theory, as was explained earlier. So in order for ice to grow, prior to this, we must have a nucleation step. And even before the nucleation, we have some sort of ice-like clusters that form from the liquid. And if you look at the structures that are on the screen, these are just some of the structures that can happen in liquid, some of the interactions between the water molecules. And of all these, one of those is a hexagon. And in order to have ice nucleation, we must have ice-like hexagons. So if we can somehow stabilize those ice-like hexagons, then we can encourage the subsequent nucleation and growth of ice. So just to clarify some terminology, ice always melts at 0 degrees Celsius, and this is always true. However, water doesn't always freeze at this, and water can freeze as low as minus 40, and this is called the freezing point or the icing temperature. I use those terms interchangeably, and this temperature will never be above 0. So when I speak about raising the freezing temperature, it's still below 0, nothing too crazy is happening. So when ice nucleates, according to heterogeneous ice nucleation, there's two main mechanisms. There's epitaxy, where there's a structural match between the lattice of the ice and the surface on which it sits. And there's also electrofreezing. So this is some sort of catch-all phrase that refers to any electrical effect influencing ice nucleation. So it could be voltage, it could be current. And what I'm here to show you is that there's also a very strong chemical component which is responsible for what we're seeing with electrofreezing. So just to give you a scope of this problem, research dating as far back as 1862 begins to speak about electrofreezing. And there's work that shows that it exists experimentally, as well as work showing that it does not exist. There's theoretical works showing using large amounts of voltage. But we still have this question of what is the mechanism of electrofreezing. So in my group 30 years ago, they found that when they compared chiral crystals versus the analogous racemic crystals, there was a difference in the ice nucleation behavior, and that the water always freezes at a higher temperature, closer to zero, on the chiral crystals versus the racemic ones. And the chiral ones all belong to the polar space group, while the racemic ones do not. And polar crystals are also pyroelectric. So what's also very special about these crystals is that the surface that the water is in contact with is identical when you compare the polar versus the non-polar crystals. However, they have these cracks, which is where the polarity or the pyroelectricity plays a role. So first, to explain a little bit about pyroelectricity. So when you have a polar crystal, there's an internal dipole moment. And as the temperature changes, the dipole moments arrange. And as a result of this, you have a buildup of charge on the surface. And whatever's in contact with the surface, whether it's air or it's water, compensating ions from this will come to the surface to negate the charge. And upon heating, the dipole moments move in the different direction. So the surface that's positive upon cooling is negative upon heating. So after seeing the previous results, that perhaps that the polar versus the nonpolar crystals, we want to know if we can use this unique property of pyroelectricity to explore electrofreezing. So in 2010, for my group, they used a pyroelectric crystal, and by placing it in a metal cup, you can actually bring the field outside, so now you have an electric field above the surface of the crystal. But if you place an insulator between the crystal and the metal cup, or if you look at these crystals just in a free atmosphere, then you can turn off that external field. So in this way, you can compare the freezing behavior in the presence and the absence of an electric field on exactly the same surfaces. And they found that water freezes higher on positive surfaces versus negative surfaces. So after this, we returned to the amino acid crystals and compared hydrophobic to hydrophilic crystals. So when you look at hydrophilic crystals, you have a wetted layer, and when you have a hydrophobic crystals, you don't have this wetted layer. And we know, based on resistance measurements, is that there's a current, right? It's a continuous layer with a current running through it. And you can actually connect the two hemihedral faces with a conductive paint. And when you do this, then the current is discharged through the conductive paint instead of through the wetted layer. And by comparing the results on the hydrophilic and hydrophobic crystals, and in the absence and the presence of a field by connecting the two hemihedral faces, we found that the water freezes highest on the crystal where the current can go through the wetted layer. So this indicates that the current plays a very important role in the electrofreezing. But then what exactly could be causing this current? So we live in a world full of carbon dioxide. And carbon dioxide can dissolve in the water as bicarbonate and hydronium ions. And the ions can flow to the hemihedral faces. So here's where you can see where when you connect the two hemihedral faces, the ions don't move. And the same case in hydrophobic crystals, where even if you have the bicarbonate ions, they can't access the hemihedral faces. And from these four cases, when the bicarbonate is allowed to reach the hemihedral faces, the water freezes at the highest temperature. So next, we wanted to further investigate this. on the crystals where the exposed face is the charged face. So in this case, we purposefully added bicarbonate ions to the solution by adding CO2, creating a very CO2-rich environment, and compared water with and without CO2 on the same surface at the same time. And we saw that on the positive surfaces, the bicarbonate ion elevates the freezing temperature. Well, on negative surfaces, it does not. So we also performed these experiments on the silver iodide. Silver iodide is currently used for cloud seeding, so it's a very relevant material. And here we observed the same effect, that the bicarbonate ion elevates the freezing temperature on positive surfaces. So next, Professor Daniel Harris and Dr. Christoph Alolio performed molecular dynamic simulations of the bicarbonate ion in the hexagonal ice. And what they found was that the bicarbonate ion can insert itself into the hexagonal ice structure, and it can replace the hydrogen bonds with covalent bonds. And the covalent bonds are more stable. So in this way, we can stabilize those ice-like clusters, which we talked about at the beginning, and we can elevate the freezing temperature of water. By looking at this, we said, okay, well, then any trigonal planar geometry should also elevate the freezing temperature of supercooled water. There's nothing unique about bicarbonate. So in theory, there should be a whole class of materials that can elevate the freezing temperature of water, and other geometries should, we already know, reduce the freezing temperature based on the colligative effect. Usually ions in solution lower the freezing point. And this is exactly what we found. We found that bicarbonate and nitrate ions, which are both negative ions, they elevate the freezing temperature on positive surfaces. Well, in contrast, guanidinium, which is a positive ion, and biguanidinium elevate the freezing temperature on the negative surfaces. So this really brought us back to 2010. It really gave an explanation of, okay, yeah, maybe we saw that the freezing temperature was elevated on positive surfaces, but that was just due to happenstance, that we had CO2 in the atmosphere that we didn't think of. And now we see that positive ions can elevate the freezing temperature on a negative surface, so they can freeze exactly the same. We also found that biguanidinium elevates the freezing temperature at a concentration an order of magnitude lower than the guanidinium. So this is indicative that it's due to the stabilization, because you can see biguanidinium is a larger molecule, and it can replace more of those hydrogen bonds with covalent bonds. This was pretty conclusive. So we can conclude and see that really that what we call electrofreezing, it's this interplay of the charged molecules that are in solution being attracted to the surface, which there probably is some organization of the water molecules by the charged surface. The charged molecule can fall upon it, and it could replace the hydrogen bonds with more stable covalent bonds and elevate the freezing temperature of supercooled water. So I'd like to thank my group, of course, Professor Meir Lahav, Igor Lumirsky, as well as David and Sophia Kurlin, who contributed significantly to this work. Thank you.
So please raise your hands for questions.
I have just a general question. What is the dependence of water freezing temperature on the pH of water?
Okay, so we checked also with, right, because bicarbonate has, we added pH 4. So let's say HCl will have a similar pH, and the freezing temperature is lowered due to the presence of other ions. Like when you lower the pH, you're always going to have a counter ion, right? When we add H pluses, it's coming with something, and it's really dependent on that, on the freezing temperature. And also, even with the bicarbonate, when we remove the field by placing the insulator, we have a lower temperature. The freezing temperature is lowered compared to the pure water.
Does that apply to basic conditions too?
So also with basic conditions, you have the same problem of the counter ion. So I studied actually the whole family of potassium, lithium, sodium hydroxide. In all of those cases, I saw a decrease in the freezing temperature.
Thank you.
Other questions?
Thank you. The question is about probably size, because even insulators, even metals, of course, they have service charges, like no matter what you do, like zeta potential. So, and then you probably, do you see this size effect? Probably if you go to a very thin layer of water, it would be quite different from if you go to the bulk or near the surface.
So you only need a few nucleation points for there to be, for the ice nucleation to occur, right? So even in a very large droplet, the charge is only felt close to the surface, but that's enough, right? Because once you have a few locations where the nucleation is beginning from. Is that what you're, maybe I didn't understand your question.
The question mostly like, do you take into account zeta potential of the surface? Because nucleation is one thing, but kind of structuring of water because of the natural presence of electrical charges on the surface of potential should probably influence, I don't know, growth or is it any material dependence?
Okay, so is there, well, we see, okay, the absolute freezing temperature is different depending on the surface, right? Depending on the material surface. In pyroelectric crystals, in the setup that we have, it's very hard to do it quantitatively, right? To know exactly the charge, where the charge is exactly falling within the water droplet and how much charge is felt. So we've actually been moving into more electrolytic cells where we have a lot more control over the whole process and the application of the charge and being able to quantify where the charge is falling. And it's giving us a lot more insight into this problem.
Thank you.
Other questions?
Thank you for the beautiful talk. I have a question. I mean, I would expect that the structuring of the water layer will also be affected by the valency of the anions or cations that you are using for the charge. Do you see any effect on that?
Wait, the effect on what? Sorry.
So the structure of the water, right, will be affected if you have cations, I don't know, divalent or trivalent or monovalent cations, right?
Yeah. So we can't really look at the structural behavior of the water itself. It's a very complex system to study.
I understand, but I was wondering if that will translate into different temperatures.
So
also, like if you have a similar chemistry but different valency.
Yes. Okay. So that, like you're saying, if I take a divalent salt, like instead of like guanidinium hydrochloride, magnesium.
Exactly. Yes. Yes.
Okay. Yes. So we definitely do see a difference because also we think partially because we don't have a complete separation of the ion of interest. So let's say if I take guanidinium hydrochloride, in solution, they completely separate. The guanidinium can come to the negative surface. When I have magnesium, let's say magnesium with 2 guanidinium, one of the guanidiniums can separate, and then the magnesium and guanidinium could stay connected. And then I always have this interplay of concentration where I'm trying to find this optimal concentration of ions that are in solution that are lowering the freezing temperature and ions that have this ability to come to the surface and raise it. And I can't quite overcome that. And so I don't see the same elevation when I take a bivalent.
Okay, thank you.
Thank you, Leah, very much. And thanks all the speakers for sharing us their research. I would like to close this session with this announcement that please gather at the Hotel Trust for the group photo.
crystals.
Okay, I think we can start with the afternoon session. So welcome to the session called Crystal for Devices. It's nice to see most of you back. So I'm Ivar Lončarić from Ruđer Bošković Institute in Zagreb, Croatia. Unfortunately, my co-chair, Patrick Cummins, couldn't come, but at least he sent me his slides, so he will be virtually somehow present too. Okay, so this afternoon we have 5 talks. 2 will be online, the first one and the last one. Here are the speakers, and you can see also by the titles different topics they will cover. So when Panche asked me to be chair of this session, I told him, you know, I'm a computational physicist, I don't work with devices. But then I thought, like, maybe it's good to read about devices, because even us theoreticians have to write something into introduction. And if you want to sell your paper, of course you have to mention devices, because that's the goal of our research at the end. So my first thought about devices was something about semiconductors. So I guessed most of the people would talk about something like, I know, organic solar cells or organic field effect transistors and things like that. And it's possible to make such devices because in organic crystals you have these conjugated systems that have useful band gaps, and you can exploit this. But since I'm also a theoretical physicist, I thought, okay, there are also organic superconductors, but nobody's going to talk about this today. And also, from my own research, I thought, okay, maybe somebody will also mention lead halide perovskites, which you can make in this 2D form by inserting some, let's say, organic crystals and modify their properties. But nobody will talk about this, although we will have a perovskite talk, but it's going to be a purely organic perovskite for X-ray application. So that was my idea of devices. And now let's go to Patrick's idea of devices. So this is, now it's starting the presentation he sent me. So apparently when he thought of devices, he thought about waveguides, soft robotics, accutators, and fuses. So most of the presentation is going to be about this, and also most of our talks today are going to mention this stuff. Okay, so I'm briefly going to go through these applications. So waveguides. So there are more and more papers recently in exploiting organic crystals for waveguides. And here are some nice examples. So first example that Patrick actually pointed out is this paper of our first speaker. So I'm sure he will tell us more about this. But in this example, they managed to make a waveguide that, depending on the condition, could be either guiding in 1D or 2D, and you could make it reversibly. So it's nice. Then the second example is this one, where you can make a bendable waveguide. So as one of my let's say side duties, I also take care of of our group supercomputer. And if you ever broke optical waveguide, you know that it would be much nicer if they are softer and easier to manipulate. And then as a third example of waveguides, again from our first speaker, here they show that it's possible to make, it's already written, optical waveguiding and wavelength division multiplexing in both straight and bent geometries. So I think, yeah, it's clear that there is some potential for organic crystals in waveguiding. And then first of the videos, I like videos, and it's really nice. It's from the Punches group, where they decorated organic crystal with magnetic microparticles, and then they managed to bend and change form of this crystal by using a magnetic field. It's of course nice because you don't want to always touch something, so it's a non-contact scheme. And there again, you can also waveguide by changing direction with a magnetic field. Okay. So the next example, so this goes to these accutators, is photomechanical accutators. So there are crystals where you can change their shape when you apply light. And this is one example where they permanently modified crystal shape by using light. So of course for some applications, like maybe sensors or something like this, it's nice to have a permanent change, but for some other applications, it's of course nicer to have a reversible change. So in this paper, they managed to make a crystal that twists in one way by using UV light and the other way using visible light. So another nice application, and at least looking towards the devices. Then from photomechanical accutators, we go to thermal accutators. We already heard something about this. I know if it was too quick, but maybe if I go back and forward, you can see in the movie how this thermal accutator could move a steel ball based on the thermosalient phenomenon that we already heard about something. And then looking towards devices, you can compare, for example, force to weight ratio of this material, HMB, to, for example, some live animals and insects. And you can see that this crystal has a larger force to weight ratio, so it could be useful. Another example of thermal accutator, so here in the movie, hopefully you saw, I can play it again, you saw how the thermosalient material could propel this ball, and the work density was also very large, 270 joules per kilogram. Then maybe thermal induced processes are not that useful always. So here is one example of one of our speakers where they used spin state to make material change its shape. And in this spin crossover materials, in principle, you can switch them by light, temperature, pressure, by putting gas molecules, magnetic field, and so on. And in this particular paper, they showed on the left side what happens on the temperature-induced process, and in the right side in the photo-induced process. Then the next application possible is in electrical fuses. And here is, for example, useful this thermal process. This is also where Pancha worked on. So you can basically use such material as a fuse, and as the temperature rises, the crystal shatters and the circuit is broken, and so in this way you can use it as a fuse. Okay, so these are the Patrick's chosen devices. And then as last slides, let's say, is where the field is heading. So here's this nice picture showing many different materials and their maximum output force as a function of their mass. And if you see this bolded DCC and LPGA, so these are the thermosalient materials, and you can see where are they in this graph. And I guess there are still a lot of free space there, which could be probably filled also by organic materials. And I'm sure in the future they are going to be filled. Another example is looking at elastic modules of different materials. And you can see where the molecular crystals are standing, both for elastic modules and hardness. And on the right, you can see the histogram of different, how many materials with a given modulus or hardness you can find. And here, Patrick, let's say, envisioned that we should do more characterization, quantification, and then choosing the materials for real applications. And I guess with these first two steps, you can broaden the applicability of different materials. But as I'm a theorist, I would like to do something else. I really like the saying of our first speaker on Sunday that said that experiment guides and theory decides. And I can agree with this because, it was like that. I mean, you would find something strange, let's say, in the experiment, and then you would not be sure that, that your explanation is right until the theorist could reproduce it with the theory. But I hope we are now also getting into the time where theory can also guide. And this is something I'm also personally working on and trying to do. And I mean, I can maybe discuss this with you later if somebody is interested. But I think, for example, nowadays we could find points left or right of the known elastic modules without any experiments. So I think theory now is capable of predicting materials with desired properties and not always just explaining already measured properties. So hopefully I won't be mentioning devices only in the introduction anymore. Okay, that was it. So now we can start with our talks from today. And the first talk is, I'm sure I will miss it, from Raya Durai Chandrasekhar. I did try it a few times, so hopefully it was not that bad. It's going to be a recorded lecture, and then later there will be live questions. So let's hear the presentation.
Thank you for your kind introduction. At the outset, I thank Ponce and the organizing committee for inviting me to this meeting. Though I'm not able to be there physically, but I'm happy that I could share my research through this June platform. So today I will be discussing with you about mechanophotonics, a roadmap to all organic photonic integrated circuits from nano-micro-organic solids. Before going to the topic, it's important for me to introduce the term mechanophotonics. It's a new research field, and it's a combination of two different research subjects. One is mechanical manipulation, The other one is nanophotonics. So I will explain. Thank you for your kind introduction. At the outset, I thank Ponce and the organizing committee for inviting me to this meeting. Though I'm not able to be there physically, but I'm happy that I could share my research through this June platform. So today I will be discussing with you about mechanophotonics, a roadmap to all organic photonic integrated circuits from nano-micro-organic solids. Before going to the topic, it's important for me to introduce the term mechanophotonics. It's a new research field, and it's a combination of two different research subjects. One is mechanical manipulation, the other one is nanophotonics. So I will explain to you what is nanophotonics is all about. It's a subject which studies the behavior of light on the nanometer scale and how the nanometer scale objects interacts with the light. It's quite a fascinating field. There are so many different components have been made, such as waveguides, resonators, or optical cavities, and lasers, modulators, splitters, and those things. But let us look at the light again. Light has a speed, a fast-moving energy in our universe, and it's composed of electric and magnetic fields. That's why we are calling it as an electromagnetic wave, oscillating at a frequency, the specific wavelength. And if you look at the picture which is shown here, the light which you are seeing falls from 400 to 700 nanometer. We call it the visible light. In photonics, from visible, IR, and also ultraviolet light can be used to carry out a particular job. And this gentleman, James Clerk Maxwell's wonderful equation, the last equation which connects speed of light with two important parameters, electric permittivity and also magnetic permeability in waveforms. And if you look at this equation, it's connected to the refractive index, because when the refractive index increases, the speed of light in that particular medium decreases. So the refractive index is greater than 1. Essentially, we try to stop the propagation speed of the light. And also this refractive index is connected to materials property, epsilon, electric permittivity of the material and electric permittivity in vacuum. And the ratio gives the electric constant, in other words, a relative permittivity or dielectric constant. So it's not a constant, it's a function of frequency. Again, this particular parameter is connected to chi, electric susceptibility. See, this is also a materials property. And when we make a materials in the laboratory and we incorporate this chi and the assembly of those molecules in the solid state and the symmetry dictates the order of the chi. I will be discussing with you in a moment. But if you look at an organic crystal, typically the refractive index is around 1.6, and you can see here when you try to shine a 405 nanometer laser light onto the crystal's one terminal, the crystal absorbs the light electronically, the molecules are excited, and the fluorescence happens. The emitted fluorescence is self-guided by the organic crystal via total indent reflection. And we know from the Snell's law, if you look at the crystal, this is the high refractive index medium. This you have a air around, and the refractive index of the air is 1. And if you take a material with the refractive index of 1.52, that is silica, and from this we can calculate there is incident angle, which is 45 degrees, And when we launch a light, if the incident angle is greater than the critical angle, then you have a total reflection, which is the condition for waveguides. So once you confine the light, it can propagate, and the losses may happen depending upon how much loss happens. So the output, you will be able to detect the signal. More importantly, if you look at the interface shown here, you have a high refractive index medium, and this is the rarer medium. The total reflection is not entirely total. You can see some of the fields after reflecting on this interface, field is a little bit going away to the rarer medium, and this is called evanescent wave. The evanescent waves exponentially decay from the surface. Okay, the amplitude decays exponentially from the surface, but it's very important field which can be used to couple two optical components. So I will be discussing also about this particular field in our discussion when I discuss about circuits. So coming to the photonic integrated circuits, photonic integrated circuits uses light. It's much faster than the electronic integrated device. In the photonic integrated device, we use waveguides to guide the signal, whereas in the electronic circuits, we use wires with electrons carries this information. In PICs, in other words, photonic integrated circuits, one can integrate multiple photonic functions, and in order to incorporate multiple photonic functions, we need to integrate multiple photonic components having different properties. These PICs are quite useful for quantum information processing, sensing. The radar is an emerging research area, and also communication technologies. One of the PICs is shown here, made out of indium phosphide. These are smaller and much faster than the electronic circuits, and you can see so complex circuits and many bend waveguides you can recognize immediately from this picture. And it's expected that the PIC market value will go up to 7.6 billion by 2031. So far, this is indium phosphide PIC, but silicon is predominantly used for PICs fabrication because of the cheaper cost, and also the fabrication method is quite parallel with the electronic circuit board printing technologies. So silicon is very good, fantastic material. It's a very high refraction index, 3.4, which is highly sought after for photonic devices. So it has certain drawbacks, like any materials, you can see a positive side and also negative side. In this case, the silicon is quite a hard material, so the flexibility is the kind of issue. So once you make this circuit, you can't alter it because it's rigid. And also the indirect band gap makes this silicon waveguides only to propagate passive signals, okay? And also it has a high thermo-optical coefficient, so we need to cool the device, and because the increasing temperature also changes the refractance when the refractance changes, and also it affects the signal propagating a silicon waveguide. Silicon is a centrosymmetric material, so one can't expect any second harmonic generation. So what is the solution? So in our lab, we thought of using organic crystals as a new photonic material platforms, matching the advantage and filling the potential gaps existing in silicon-based materials. As you know, the silicon-based PICs consist of many tiny optical components, and the connectivity between them define the circuit's functionality. So we wanted to make these tiny circuits using organic crystals. Why? If you look at these organic solids are Frankel excitons, very high binding energy, up to 1 electron volt. It means that it can be stable even at room temperature. This exciton can combine with light, can produce exciton polaritons and quasi-particles, and the refractance is not that bad. This is a kind of a trade-off. We gain in the exciton binding energy, but we lose in the refractance. And if you look at the MLO properties, organic crystals can be also nonlinear optically active. It can be active and passive waveguiding tendency. It can be used to produce resonators, and also some crystals have reabsorption, self-absorption can be used as a filter. Energy transfer can be used to transfer optical energy from one crystal to a different crystal. Organic crystals can be also chiral, so one can expect chiral optical properties, easy to grow. We can make in different geometries, 1 dimension, 2 dimension, and the flexibility also very important in this case to bend a crystal to make a circuit lightweight and stimulate responsiveness, and more importantly, the crystals mirror-like light refracting traces reflect the light internally, so you'll be able to confine the light in 2D and propagate the light in 1 dimension. Apart from that, by using organic chemistry, one can really fine-tune the bandwidth of the organic crystals from UV to IR. So these are some of the assets. Now, looking to the photonic component, which I was discussing about, essentially, you used to have a building block that is waveguide. A waveguide can be linear or bent. If you look at a ring-shaped resonators also can be made, and also splitters can be made, and spiral structures also can be made, and one can also connect two waveguides to this geometry to create interferometers. Two different crystals can be also combined to make it hybrid splitters. Sorry about that. And also ring resonators and add-on job filters also can be made. See, essentially, in order to do all these things, the crystals should be flexible. Okay? Without flexible crystal, one can't do this one. And the crystals are usually brittle. If you look at the literature, Takasawa published the first flexible active type waveguide. What does it mean active? Essentially, you excite with the UV laser, the fluorescent, which produced by the crystal self-guided to the other thing. It's active waveguide. And so he kept the crystals on a silica substrate, refractance is 1.5. The crystal refractance is more than the substrate, so thereby the light is not leaked into the substrate, it is trapped by the high refractance as the crystal. Okay? And we have reported a passive type waveguide in 2013, and you can see here the 488 light is guided to the terminal. And if you look at the crystal is not absorbing the input signal. So that is a requirement to electronically, the crystal should not be excited when you launch a light. And so this is a history, but if you look at the same time, Professor Desiraju and Professor Malla Reddy, they have published papers explaining the structural basis for the flexibility in organic crystals. Okay, I don't want to discuss more about the structural basis because that is not the part of this discussion, and I'm sure you heard all about these flexible crystals, and also if not, you will also hear about it. So I skip this particular part, but anyone who wants to know about the flexible crystal, they can refer these two papers. So what actually one can learn from this slide is the elementary structure for any photonic circuit is waveguide. Okay, you take a waveguide and you can bend it, and you can make a ring resonator, and you can make interferometers, you can make couplers, you can make a polarization, so on and so forth. So I use the terminology ring resonator. So I want to tell you what is the ring resonators. So you connect the terminal of two optical waveguides. So what happens is the light is circulated by total reflection repeatedly once the resonance criterion is met. So the circumference of the ring resonator should be the integral multiple of the wavelength of light in order for the round trip to take place repeatedly. Okay, so one can also change the diameter of the ring resonator, thereby one can also control the optical modes. Okay, once you have the optical modes, one can also, from the line width and the lambda max, you can call the Q factor is very, very important. Each higher Q factor is very, very important to achieve high quality circuits. So I mentioned about this electric susceptibility of the material in the previous slides, and it is an order. It can be 1, 2, 3. If you want to have order 1, you don't have to do anything. But if you want to have a 2, you have to work a little bit on the crystal, the molecular arrangement in the crystals. So typically non-center symmetric compounds, crystals give the second harmonic generation. So that also can be incorporated in the circuits, and 2-photon absorption and 3-photon absorption, all these properties also can be incorporated by playing with the sky, okay? And so the optical modes can be of many types. So you can have a angular mode or azimuthal modes or radial mode. Typically, if you look at a fluorescent spectrum, okay, it's a fluorescent spectrum. And if you look at your very sharp signals, which is quite unusual, this happens only when you trap the light within a resonator. So because of the optical interference of the circulating light, you are having these optical modes called azimuthal modes. So when you simulate this using finite differential time domain calculations, and we'll be able to assign more numbers for all these peaks and the transfer electric and transfer magnetic modes are shown here. So here the radial mode number is 1 and P equal to 0. What does it mean? When P equal to 0, you keep the angular mode number and the azimuthal mode numbers are same. So you subtract, you get 0, and radial number 1. So when you play, so depending upon the geometry, you can, whatever you are seeing here in the spectrum is this particular cartoon, and you can, if you change the L or M, then in P equal to, you will get complex modes. The electric field is mostly around the periphery, okay? When we increase the radial mode number, the electric field is going to the center, okay? So now if radial mode number is 1, you can see the electric field is circulating in this direction. When you increase it to 2, 3, 4, then they completely fill the cavity with the light electric field. And the calculated Q factor from this mode 23 is around 2000, is a good number for an organic resonator. And so this is a donor acceptor compound. And if you look at compound, when you self-assemble, you get a frustum-based structures, and the details you can find in this particular paper. And so when you excite with the 488 nanometer laser, you see the fluorescent spectrum composed of very good optical modes, and so the Q factor is around 900. What actually we have done also that we were able to find out that the electric field in this case also distributed around the periphery of this particular structure, and the Poynting vector, which tells the energy propagating direction, which is in this direction, okay? And these crystals also, when you excite with a femtosecond laser, because of the non-centrosymmetric packing arrangement within these crystals, we will be able to see second harmonic and also 2-photon luminescence both, okay? And then you can obviously avoid 2-photon luminescence here when we go away from 800 nanometer to 1000, 1200 may go, then we can go out of the 2-photon absorption range, thereby only get a pure second harmonic signal. So I'm not going to discuss, so you can refer to this paper. So we have published several papers on this particular topic to create various types of resonators. You can refer this particular reference. And if you look at a flexible macrocrystal, the DPIN is quite famous, published by Zhang. It's quite flexible, and macrocrystal waveguides, and the reason for the expansion and compression in the spring-like motion of the molecules are all given in many reviews written by Jaisraju, Malla Reddy, and Ponce, and others. So you can refer those things. But what the point here, the millimeter-sized crystals can't be used to make photon radar circuits because the peaks are very small scale crystal. They're elastic, but when you try to deposit on the substrate, the microcrystals almost behaving like a pseudo-plastic, okay? In the bulk, it's behaving like an elastic crystal, but on the substrates behaving like a plastic crystal. So this is a kind of a new observation, and this is a turning point, and for mechanophotonics. So the detailed publications one can refer in this particular journal. Myself and Ponce, we published this work together, and I also wrote a kind of perspective about this particular field, and emphasizing on the importance of mechanophotonics. In this particular abstract, you can find the importance of atomic force microscopy to manipulate microcrystals to create different photonic architectures. So mechanophotonics is essentially a discipline that uses mechanical micromanipulation of single crystal optical components, not any other crystals. A crystal should have optical function like a waveguides or resonators or kind of lasers. So if you're having this type of crystals and you try to manipulate them mechanically using atomic force microscopy and assemble them to create integrated force, you can say that it falls under the discipline of mechanophotonics. And so it's a new research direction, and there are so many players in this field. We collaborate with all of them, and it's quite interesting to see the results. And if you look at mechanophotonics, as I mentioned before, you need to have atomic force microscopy manipulation because the crystals are in the micro domain. And we have been working in this discipline from 2014, the lifting of the crystals, cutting of crystals, and also extremely bending to make ring resonators, slicing the crystals, and also aligning, integrating two homocrystals to create a directional coupler, and also transferring, lifting a crystal from one substrate to another substrate. Thereby one can make a heterocrystal based junction. So these are also quite interesting, which is not possible in silicon photonics and these aspects. So that is the strength one can get from this technique. But how we will design an optical circuit? Okay, so one should have a fair idea about the required function. So once you know what type of function you need to have an idea, and then you have an idea, you try based on the idea and the function requirement, you decide whether you want a monolithic circuit or a hybrid circuit. Monolithic means same type of crystal, same molecular crystal. Hybrid means two different molecular crystals. So you can select a crystal from substrate and take a crystal type 1 and select, and you may slice it or cut it, and if it's not necessary, you can lift them up and release on the OP construction site, bend the crystals and repeat the process, integrate many crystals, thereby you'll be able to get a monolithic photonic circuit. But if you want hybrid circuits, you need to have two different types of crystal, sometimes three. That also you have done it. And then you select them, go through the usual process and bend them in the different directions and angles, and make ring resonators and directional couplers and also interferometers, integrate them together to get a hybrid organic photonics. So this is the guide how one can deal with the crystals towards achieving photonic integrated circuits. So this is a kind of abstract of different circuits which are made in, and you can see here this is the directional coupler made from this particular molecule. And so if you look at this, you can see here this optical properties, the emission wavelengths, and also the bandwidth of the fluorescent signal, how much reabsorption happens also given here, and the mechanism which we use to operate this directional coupler, it is via active, passive, and also reabsorption also have been used. And then we made a complex direction coupler. Here in this case, we have two bends are here, okay? The more bends, more optical loss actually you create, okay? So it's quite challenging to create intentionally bends in organic crystal, and thereby one can study the optical loss and also couple another crystal and to see whether it can act as a direction coupler or not. So the bandwidth, the reabsorption, all the mechanisms are given here. We also made an add-on drop filters and also kind of interferometer, okay? And circuits like shown here, where we have integrated waveguide integrated resonators, and which is a hybrid crystals. These two crystals we have used using the transferring technique, and similarly we have made also hybrid drop filter here. So typically the directional coupler, if you take, it's made using silicon, okay? And the directional coupler essentially redirect, splits, and combine the light signal. So you launch a light here, and then the light goes here, and then couples evanescently, it comes here in the X, and also transmitted through here, and there is no signal observed here. This is the purpose of direction coupler, it split the signal, and this is what shown here. So this success we were able to achieve successfully, and you can see here collaborate with Professor Malla Reddy, and then what you have done here is two different two crystals you have taken and bent them and sewn here and integrated them. And so if you look at the direction coupler, if you see that we created intentionally this bent geometry for the light to couple effectively another crystal. The optical path length also given here. And so if you look at the performance, the function is light splitting function. And so exit here, the light travels to this junction and also transmits, couples through to this crystal and out couples here, okay? Obviously, because of the direct transmission, the output is more 90 here, but it is 10 because of this evanescent mediate coupling. And similarly, this is what you can see here, two dots means the two outputs you can see here for the input signal. And this can be repeated in this direction, and also one can play around because we have four terminals here, in other words, four ports are there. So one can nicely demonstrate how one can manipulate optical signal in the micro level using organic crystal waveguides and also creating a direction coupler of them. And the bandwidth and also the reabsorption range also shown here. This is the reabsorption range, okay? Because of the propagations, this particular part of the fluorescence is cut off as a long pass filter, effect one normally see in optics. And so this is a kind of beautiful results. And then what we wanted to create is a ring resonator and coupled to two bus waveguides. So we took this molecule, Young's molecule, quite flexible, and and we were able to create this particular geometry here. The manipulation, other things I'm skipping here. One can see it involves several steps how we finally reach this particular geometry. And what you are seeing, a ring resonator and two waveguides are connected here. So if you look at here, this particular waveguide, okay, so that is what's shown here, port 4-3, port 4-3 here. And then when you excite one terminal, you can see the light propagating here. And this is the signal one can see here. This optical modes one can see because of the optical interference within this crystal. Now, after you couple this particular, after making this circuit, you can see here, now it's integrated with this ring resonator. A ring resonator is integrated with another waveguide, OW2. OW stands for optical waveguides, and which has port 1 and 2. Now, if you excite here, the light is traveling straight. And because of the reabsorption, we label this as -1A. A stands for active light. Active light, active light. Then it passively couples, okay? Because the fluorescence can't excite the same crystal, okay? So it is going through this ring in circles and then out couples in this particular point. So it's called -1P and -1P, and there is no signal observed. So the transmission and also clockwise motion of this light and also outcoupling here. And that is what demonstrated here. But when you look at, again, the signal from this particular port 3 after coupling, it's completely different. That shows that there is interference is happening in this particular circuit. So this is, we have done in collaboration with Ponce, and you can see here, two plastic and elastic crystals we have used here. And one can see here the cartoon and also the optical function of the NDIPH, which is shown here, and also the BPA molecule, highly pi conjugated molecule. So one can see also a two different optical emission maximum, and also the bandwidth is different, 490 to 775. This bandwidth is 525. You can see a very narrow band signal, okay, of BPA, and then broad band signal from this NDPH. So we try to make this circuit, and so it's quite a long process. So NDPH crystals you have to take and then make a waveguide coupled ring resonator and take another BPA waveguide, integrate them, and to create this particular geometry. And this is a FSM image. So we call this OPIC1, and then take another NDIPH waveguide and then create this particular geometry and couple them. We have OPIC2. And this end, if you try to bend it 90 degree angle, then you will finally arrive at OPIC3. So this is, in a nutshell, one can summarize the fabrication process of the circuit. Now coming to, I skip OPIC 1 and 2, but I will take the final circuit, how it works. And you can see a table here. So when we excite laser light here, T1 output, it goes in this direction, okay? So X direction and also Y direction, which is given for XY, and then it starts circulating here, okay? And what happens, the signal of this particular ring resonator, which is, ND-IPH, it can be reabsorbed by BPA crystal. So what happens, energy transfer happens. So this fluorescence goes to the T2 direction, which is given here minus 1x, and also it can come to this direction. While coming this direction, it can also circulate in this direction. Because of the anti-clockwise direction motion, there is no output coming here, but you can see the output T3. So you have essentially one XY direction and also minus 1 X here, and then minus 1 minus X here, and there is no signal here because of the anti-clockwise motion. So likewise, so we can excite here T2, and then you can see here how the signal is now going in this direction. Now you are having a clockwise motion. In this case, you had anti-clockwise, clockwise motion. The light output is a T1. Okay, the signal is minus 1 minus YX if you look at this geometry. Okay, and so again, you don't have any signal at the T4 here, 0. But if you excite at T3 or T4, what happens? These are all diagonal elements which shows the excitation point. And T1 and if you look at T1, T4, both are no signal observed here when you excite at T3 or T4. So this is a very interesting circuit, and we have also demonstrated that once you fabricate OPIC2, post-fabrication brief configurability also can be achieved by bending the crystal. And this is very promising because people are thinking about programmable OPICs. What does it mean? It is not yet achieved, but in order to achieve programmable OPICs, one need to have materials, OPICs, material which can be reconfigured. Okay, so that is the thing. So what essentially we learn from the circuits, we split the light signal in different directions and different bandwidths. Okay, so that is the idea which you demonstrated in this particular paper. And this is the last slide which describe mechanically maneuverable circuit boards, how one can manipulate light at 360 degree angle on a 2D plane, and not one signal, but 6 signals, okay? And the 6 signals are shown here of different bandwidths and also lambda max. So if you look at this particular lambda max is same, whereas the bandwidth is different, okay? Because the reabsorption, so that's why it's labeled -1. And the same signal couples to a different crystal, which is not absorbing, so it's a passive signal, so 1p. Likewise, this particular bandwidth is called 2a, and after the reabsorption, okay, you cut off some of this low wavelength signals, and then you have -2a. And when it couples to some crystal which is not absorbing the light, it is called 2p. So 6 signals you have. Now let us go back to the first FOPIC, flexible organic photonic integrated circuit 1. And if you look at this is bent now to 20 degree angle. So you launch a light, the light is coming here and then goes here, okay? And that is what's shown here, okay? So you launch a light and then you are having a light -1a here, okay? And then the light also travels anti-clockwise direction, comes this side at 1p, so, but there is no light here, okay, P4, 0. Now, I move this particular, reconfigure this particular port because of the flexibility of the crystal in this direction, 185, and I can achieve the same signal. I can achieve the same signal, okay? But this angle of the second port is now different, 165 become 185. All other signal remains the same. Similarly, you can excite at P2, P3, or P4, thereby you can control the mill output at different ports from P1 to P4. And also one can really manipulate the signals in this particular crystal arrangement. But essentially what in this particular circuit we have demonstrated is 2 different crystals, DPIN and CPN can be used to make a hybrid circuit, which is not possible in silicon photonics. And so what essentially we have done is the port angles can be reconfigured to 185 here, and then 345 is reconfigured to 330, which is shown here. It's moved down, okay, 330. And then the 195 can be moved to 208, you can see 195. So this is the reconfigurability, and maneuvering 6 optical signals have been demonstrated here. In summary, organic crystals are beautiful and a new material platform to achieve nanophotonic components and reconfigurable organic photonic circuits, which have demonstrated in this last 2 years or so. And while doing this particular research, we also created a new research field called mechanophotonics. And we believe that's a new tool to micro-manipulate flexible optical crystals using atomic force microscopy. And organic photon integrated circuits is a new research direction. So I thank all my collaborators who were involved in nonlinear optical studies, which is not presented in this particular presentation, and also for the numerical calculation. And also we receive crystals from many research groups all across the world. And we really enjoy their collaboration, and because you see crystals from different properties. Okay, so that is what actually essentially we are looking for to make a complex functions in a circuit. And lastly, but not the least, I thank my former and current PhD and postdoc students and also the funding agency. And thank you all for your attention, and I'm very happy to answer any questions if you have. Am I audible?
Okay, thank you. Thank you for this interesting talk. You hear us, no?
Yeah, I can hear you well.
Great, thank you. So we have around 5 minutes for questions. Panche?
Thank you, Chandra, for a beautiful talk. It's amazing how one can capitalize on the combination of organic crystals and light and do so many things in optics and electronics. My question relates to possible scaling of these materials. If we were to go to a mass production, what would be your approach to scale this up?
Yes, it's a good question. So whatever we have doing and demonstrating is, in the preliminary stage, a proof of principle circuits. How one can really, explore the possibility of using crystals for photonics. So this is just a first step, a baby step. Automation, so we have been doing atomic force microscopy. Atomic force microscopy also can be automated. So in order to do that, one have to keep the crystals at appropriate place, at proper geometries, and so one can work on this also in the future.
Okay, thank you. Next question.
Very nice. Can you please comment on using anisotropic materials, or even there is a very interesting work at Weizmann on spin filtering by chiralic molecules. So I wonder if you can use those resonators in order to have a very, very efficient filtering of spin, of circular polarizations of the light.
So which spin you are talking about? The electron spin?
In the
or
work that I
are you talking about the angular moment of the photons?
Yeah, so the work the work I mentioned is on electrons, but in the use of light, you can use a filter of the circular polarization. You have a long resonator, so you have a lot of times, a lot of circles to make it very efficient.
Yeah, see, I have not really discussed that polarization part. In fact, depending upon the optical cavities resonators you create, particularly if you go and construct a circular geometry crystal, and then if you allow the light to circulate repeatedly, then you will be able to resolve the transfer electric and magnetic fields. So that is, I've presented, but I did not take a deep dive into that particular part. So the polarization also can be achieved using crystals. But we have to keep in mind that whether we are able to achieve the whispering gallery modes or not. So you'll be able to resolve TM and TE when you trap the light. Yep. Did I answer your question, or because partially understood your question, honestly speaking?
Okay, next question. Still have time for one. There are no more questions. We can thank the speaker again and move it next talk.
Thank you. Thanks for your presence.
Okay, so now the second talk is from Delia Heinz. She will tell us something about functional materials with dithiazole building blocks. I'm a physicist, sorry if I pronounced this wrongly. Hopefully everything is ready.
Yes.
So
Okay,
please,
good. Yes.
you can start.
I can hear myself, so I hope that you can hear me. Firstly, thank you very much, Panche and the organizing committee for the opportunity to speak here today. I love ICCOSS meetings, so I really feel honored that I have the opportunity to tell you something about my work in such a beautiful location. So I'm going to speak today about one aspect of the work we do in my lab. I'm going to talk about dithiazole radicals and their use moving towards functional materials with these radicals. So I'm actually not going to talk about devices at all. I'm going to talk about how we might one day get there with these systems. And it took me 6 months to learn how to say dithiazole when I started working with these. So if I'm going to talk about dithiazole radicals, the first thing I need to do is tell you what they are. They're one member of a family of stable thiazole radicals, 5-membered heterocycle. Where's the pointer button? There it is. 5-membered carbon, sulfur, nitrogen heterocycle. It's a 7-pi system. And of course, what's interesting to us is this unpaired electron, which of course means that there is the potential for building magnetic or conducting materials from these molecules. When I say they're stable, we make them in a one-part reaction, straightforward, simple synthesis, my kind of synthesis. They are thermally stable and kinetically stable. So we grow crystals of these materials by sublimation, so thermally stable enough to do that. And we do it really in a very simple way, either sublimation under vacuum onto a cold finger, or we just take a thin Schlenk tube, put the substance in the bottom, put it under vacuum, and heat the bottom, and crystals grow on the side of the Schlenk tube. So all the crystals that I talk about today, almost all have been grown by sublimation. So what's particularly nice about these radicals, before I talk about that, thermally stable, kinetically stable, you can store them for months on end, but air and moisture sensitive depending on the particular derivative. Some of them are more sensitive than others. So we do largely work with these under an inert atmosphere. So what's very nice about them is that the singly occupied molecular orbital that this unpaired electron sits in has this nice pi symmetry, and it's nodal at the carbon, meaning that we can put whatever substituent we feel like on here, limited by our synthetic capabilities, and it doesn't really interfere with the electronic structure of the radical. So this all sounds very good so far, but of course there's always a downside. These radicals tend to dimerize in the solid state, and they do so in a number of different geometries that I'll talk about in more detail now. And when they dimerize, the unpaired electrons spin pair, and the resulting dimers are diamagnetic. So of course, once that happens, then we lose the potential for interesting magnetic or conducting properties. And so we want to try and actually overcome that, that dimerization interaction. And it's quite a strong interaction. Some values have been measured. It certainly is not negligible. It's something we need to take into consideration. But as I've said, we can play around with this R group here. And so from a crystal engineering perspective, this is a great system because we can change things on the R group in order to manipulate firstly the dimerization and then the solid state structure of these materials. So this is what we've been interested in looking at for some time. And just before we lose all hope, there are some of these materials that crystallize as monomers, which is why we continue to work on these systems. So there's several that have crystallized without dimerization and are thus paramagnetic solids. I've just mentioned two of them here. This guy with the nitro substituent orders as a ferromagnet at the spectacular temperature of 1.3 Kelvin. And this related material with the cyano functionality has two polymorphs, and I'll speak a little bit more about this system later. The beta phase of this material exhibits weak ferromagnetism. That was exciting. Hold your horses. On the list of things I was expecting to happen in this talk, I didn't have that. Let's leave it there. Okay, so this guy exhibits weak ferromagnetism at 36 Kelvin. So it is possible to overcome the dimerization in these systems. And so, of course, that is something we want to understand in more detail. So as I've mentioned to you, when this dimerization happens, it can happen in a number of geometries. These are all examples from the CSD of different types of dimers. All of these are diamagnetic materials. And they crystallize really in quite specific geometries. So the most common by far is the cis geometry. And then we also see, for example, the twisted geometry, but we don't see anything in between. And that's because in these dimers, there's a sort of maximum overlap of the two singly occupied molecular orbitals. So there's some kind of covalent component to these interactions. And this type of bonding has recently been a little bit in the spotlight. There are several groups looking at it around the world, and people are calling these bonds pancake bonds. So pancake bonds are bonds between multi-center interactions, two electron multi-center interactions between pi radicals. So this is the one that we are looking at, the diethiodazyl. So things to note about this interaction. Firstly, the dimers are diamagnetic, so there's definitely interaction between those electrons. Then there's specific geometry to many of these pancake bonded dimers, and that's due to the orbital component and the maximum overlap of the singly occupied molecular orbitals. The interactions in these dimers are definitely too long to be considered covalent bonds, despite the very clear orbital component. And the interactions, the energy of the interactions are definitely weaker than covalent bonds, but often stronger than conventional intermolecular interactions. And in fact, you see a monomer-dimer equilibrium in these pancake bonded systems in solution, and sometimes in the gas phase as well. We routinely measure EPR spectra of these radicals. Sorry, I'm calming down from my laptop falling on my feet. So we routinely measure EPR spectra of these. If your solution is dilute enough, you have this monomer-dimer equilibrium, and you can see the monomer in solution and measure a lovely EPR spectrum. And then there's also, for some of these systems, evidence of thermally accessible triplet states, so where the electrons do indeed unpair. And that's just another indication that this type of interaction is not a covalent bond, but not a conventional intermolecular interaction either. So we've spent quite a lot of time trying to understand this interaction and to see what we can learn about it so that we can either use it or overcome it. So one of the things that we've done recently is go to the CSD and look at what's going on with the geometry on dimerization in DTDAs in the CSE. So this was a lockdown project for my MSc student, Marisa Stradom, who just finished at the start of this year. And she did an extensive CSD study on DTDAs. And what I'm showing you here is some structural parameters for monomers in the CSD and then different geometries of dimers in the CSD. And there's a decent number of structures in the Cambridge Structural Database, and even more measurements because many of these materials crystallize with Z prime greater than 1. And the key point that I want to make with this table is that on dimerization, we see in fact, statistically significant increase in that sulfur-sulfur bond length within the DTDA radical, longer bonds in the dimer, which is consistent with the fact that we now have more electron density in an orbital that is anti-bonding with respect to that sulfur-sulfur bond. So again, confirming this orbital interaction as part of these pancake bonds. And really not many other changes in the geometry of the molecule. We backed this up with some uncomplicated calculations where we looked at dimers of both the hydrogen substituted system and the phenol substituted system and calculated the geometries of the various dimer types. And whilst our bond lengths are a little out, at least in most cases, the order of the bond lengths within the dimers is consistent with what we see in the crystal structures. We also looked at the relative energies of the dimers, and we see that for the hydrogen substituted molecule, this is all relative to the cis-oid dimer. The twisted dimer is the most energetically favorable dimer, but for the phenol substituted system, in fact, the cis-oid dimer is the most stable, and this was kind of encouraging because that's what we see mostly in experimental structures in the CSD, and most of those molecules have aryl substituents on them. So the key message from this is that from our study we can see clearly that the substituent on this DTDA ring most definitely does affect the nature of the dimer and the stability of the dimer, which is good because that's what we're trying to use to interfere with the dimerization. We also looked at dimerization energy in these things, which is just simply the difference between the energy of the monomers and the energy of the dimer. And the more positive the dimerization energy, the more favorable it is. And again, we see that for the hydrogen substituted system, the twisted dimer is the most favorable, has the most favorable dimerization energy. And then for the phenol substituted dimer, firstly, the dimerization energies are much higher, which is not entirely surprising. And then we also see that the cis-oid dimer is the most stable dimer form for this particular radical. So what we've also done, just make sure what we've also done is you do some high-resolution X-ray diffraction experiments in order to try and learn some more about these systems and the pancake bonding in these systems, and we've done this in collaboration with Prof. Wozniak's group in Warsaw in Poland, and also with the team in Nancy at the University of Lorraine. So we've looked at 5 different systems, 3 homodimers. This is a heterodimer, a co-crystal, and I'll speak a bit more about that later. And then we've looked at 1 monomer. And I'm not really going to go into the details of the charge density analysis at all, except to say that or exactly how it works, that what we're doing is we're measuring very high resolution X-ray data from which we get a good picture of the electron density in these systems, and we can then analyze the topology of the electron density using the atoms and molecules formalism. And what we see from that are things called bond paths. So the bond paths, if we see a bond path, that indicates to us that there's some kind of interaction between the atoms. And in the bond path, we will find, hopefully, a bond critical point. And at the bond critical point, we can look at the electron density and the Laplacian of the electron density. And that tells us something about the nature of the interaction that we're looking at. So that's what I'm going to pull out now. This is the asymmetric unit of the phenol substituted dithiodiazolol radical. So these 2 dimers within that asymmetric unit. And what I'm showing here is the bond paths and the bond critical points for the intermolecular interactions within that dimer. So nothing about the actual bonds themselves. These are just intermolecular interactions. And firstly, seeing these bond paths tells us that there is some kind of interaction between those atoms. What we're going to look at now is the electron density at these bond critical points. And I'm going to focus on bond critical points 1, 4, 5, and 6, which are the ones between the sulfurs in the pancake bonded dimer. So lots of numbers in this table, but those are the 4 that I want to focus on. And firstly, the electron density at the bond critical points in those 4 pancake bonds are higher, or is higher than the electron density in the other intermolecular type interactions. The Laplacian is also higher at those bond critical points. In other words, these interactions between the sulfurs in the dimer are somehow different from normal intermolecular interactions in these systems. So let's put that in a picture. So what's plotted on this graph is the sulfur-sulfur distance against the electron density at the bond critical point for, first let's look at covalent bonds, sulfur-sulfur covalent bonds in these systems. So this is in known dimers and in the one monomer we've looked at, and all of those sit up here. So here we have short sulfur-sulfur distances, as we expect for a sulfur-sulfur covalent bond, and we have relatively high values of the electron densities at the bond critical points in those bonds. If we look at intermolecular interactions in blue down here, these are much longer sulfur-sulfur distances, so these are just contacts between dimers in the crystal structure, and these have much longer sulfur-sulfur distances and much lower electron densities at the bond critical points. And then the key point here is that this group here relates to the sulfur-sulfur interactions in the pancake bond. And they clearly form their own little cluster that has intermediate bond distances and higher than expected for an intermolecular interaction, electron densities at the bond critical point. And we see the same thing in the Laplacian of the electron density, where covalent bonds are in one bit of the story, intermolecular interactions in another, and our pancake bonds form their own cluster. So these are kind of behaving as their own, they have their own unique signature in the topology of the electron density. They're kind of behaving like incipient bonds. So we're not the only people working on charge density of pancake bonds. This is the group of Molchanov who's done a lot of experimental and theoretical work on pancake bonding using charge density analysis. And this is a very colorful picture, but what we have here is 3 DDQ radical anions, and 2 of them are forming pancake bonds to one another. Again, we have these bond paths in red with the bond critical points marked in red. And really what I want to point out here is firstly that between these 2 DDQ radical anions, there are a lot of bond paths, more bond paths than we saw between our pancake bonded diazole dimers. There's a comparison. And the electron density at these bond critical points in this system is lower than it is between the sulfurs in our system. They also have these dots in blue ring and cage critical points. So the message here is that with some of these pancake bonded dimers, we really do seem to be seeing a multi-center to electron interaction, whereas in the systems that we are working with, the diazoles, it's very much a 4-center to electron interaction. So different types of pancake bonds here. So we've also started to look at these things, these pancake bonded systems under pressure. We've recently acquired a diamond anvil cell in our lab, and Samantha LaRue is now definitely, my PhD student, she's definitely the Western Cape's current expert on using and interpreting data from the diamond anvil cell. So she's looked at a couple of systems, but I'm just going to tell you about this. This is the same phenyl DTDA pancake bonded system, and it crystallizes in P212121 with dimers that are essentially form layers of orthogonal dimers to one another. So she put this in the diamond anvil cell and put it under pressure up to just under 4 gigapascals. And the first thing she sees, of course, is that everything gets closer together. So all of our unit cell parameters decrease. But what I really want to look at is what goes on with the bonds and the pancake bonds. So under higher pressures, we see a decrease in all of the sulfur-sulfur bond lengths. In fact, all of the bond lengths. in the molecules, and we've yet to try and understand why one of these seems to be behaving quite differently than the others. But what we also see in these systems is a decrease in the sulfur-sulfur contacts in the pancake bonds. So under pressure, we see quite a significant decrease in those sulfur-sulfur contacts. And Sam is busy at the moment trying to put the system under even higher pressure so we can see what happens next. The other thing that we noticed in these, and this we still need to make sure that we've interpreted our data appropriately, but there does seem to be more residual electron density between these pancake bonded sulfurs than at higher pressures than at lower pressures. So what she also noticed, as we put these systems under pressure, these phenol rings also, of course, get closer to one another. And what we see as we increase the pressure is that in order to sort of release that stress, these molecules move with respect to one another. And that's kind of interesting in a number of ways, particularly because, as I've said to you, this geometry is usually quite strictly defined by maximum overlap of those orbitals. So we're quite interested to see what happens as we push this to higher pressures, whether we're going to see some kind of more covalent bond formation between the sulfurs, or whether the whole system is going to rearrange somehow to release the internal stress. We will wait to see, watch this space. Okay, so I'm just going to bring us back to why we started getting interested in pancake bonds in the first place, and that was fundamentally because we're interested in trying to develop molecular magnetic materials. So, as I've said to you, here are two DTDAs that do crystallize as monomers, and they have two things in common. Firstly, they're both perfluorinated systems, and secondly, they both have a strong intermolecular interaction between some functional group on the radical and the DTDA ring. And it seems to be a combination of those two factors that is important for overcoming dimerization and crystallizing systems where the radicals remain undimerized. So, because we work in my group very much on multi-component crystals and co-crystals, we thought we would try and see whether we could introduce to one of these systems, or to DTDA systems, a strong competing intermolecular interaction that would compete with dimerization, but we wanted to do this by co-crystallization instead of by wildly complicated synthesis. So we started trying to co-crystallize dithiodiazoles, and we started first to co-crystallize them with one another. And the first two combinations that we tried gave us beautiful co-crystals. In both cases, we have one fluorinated and one non-fluorinated ring. And in both cases, we have these heterodimers that form. We get 100% co-crystal, essentially, from these reactions, so we don't see any sort of statistical mixture of homodimers and heterodimers, and that seems to be really down to entropy. So we have these two lovely co-crystal dimers, and we were trying to take advantage of the sort of perfluoro-aryl interaction, which we have successfully done, although not in the way we hoped. And we have spent the sort of 10 to 15 years since that point trying to get more co-crystals. We've tried to co-crystallize these things with other radicals, with other small organics, with just about anything that we could find. And in that time, we have managed to find another two co-crystals, both of them serendipitously when we were trying to do something else entirely. And in both of these cases, again, we have the phenol radical. It's in all four of them, co-crystallized with a fluorinated radical. So, of course, we wanted to try and understand why it is so very difficult to get co-crystals of these radicals. So we turned to some computation to do this. And we look first at the energies of the homodimers, and then at the energies of the related heterodimers. And in all the cases where we see co-crystals experimentally, we see that the energy of the heterodimer is more favorable than the energy of the homodimer. Great, so far everything makes sense. We then did a calculation for a combination of radicals where we have never managed to grow the co-crystal despite repeated attempts, and we found that there, the heterodimer was even more stable. So we thought, well, okay, let's look at the the energy for the sort of overall process here. So let's look at the energy for the reaction to go from 2 homodimers to 1 heterodimer, or to 2 heterodimers rather. And again, in all of the cases where we see co-crystals, this is favorable, so that's good, but it's favorable for the one we never see as well. And in fact, we did calculations for a number of different systems where we've made repeated attempts in the lab, and we get varying values for how favorable this reaction should be. And we really can't completely explain why this should be the case, except that we clearly have not yet found the right experimental conditions to get our hands on some of these co-crystals. What this does do, though, is give us a nice guide in terms of where to focus our efforts. So we are not the only people working on co-crystals. This is Jeremy Rawson's group, and they have produced a series of co-crystals between DTDA radicals and specifically tempo. But what you see in all of these cases, in all of our co-crystals and in all of their co-crystals, is that the radicals are dimerized. In fact, even in this co-crystal, this radical usually crystallizes as a monomer, but in the co-crystal it forms a dimer. So we really wanted to try and overcome this tendency to dimerize, and so we tried to crystallize radicals that are known to form monomers with one another. So this next story that I'm going to tell you was part of an effort to try and get DTDA co-crystals. So this radical I've already mentioned several times today. This one has 2 known polymorphs, the beta form that orders as a weak ferromagnet below 36 Kelvin, and the alpha form is notoriously difficult to crystallize. It's been described by Rawson's group as a disappearing polymorph, and they are really the only people who've managed to reproducibly crystallize the alpha polymorph of this radical, and they do that by sublimation onto a cold finger that they keep at -10 degrees. So we decided to try and crystallize this radical. Oh, this is just the difference between the alpha and the beta polymorphs. Essentially, they both have chains of radicals, but in the alpha form, those chains are antiparallel to one another, and in the beta form, those chains are parallel to one another. So we tried to co-crystallize this with this guy, 2,6-difluoro DTDA, partly because it's easy to make and easy to work with, and partly because it has 3 known polymorphs, at least one of which does contain monomers. So it's clearly structurally flexible. We thought we might have a good chance of getting a co-crystal with this combination of radicals. Spoiler, we did not, but we did get some other interesting results. What we found is that under the right sublimation conditions, by co-subliming these 2 molecules together, we can control both the morphology of the beta form crystals and also the polymorph. So if we grow crystals of this radical 1 by sublimation at 100 degrees, we get needles of 1 beta, really beautiful needles, sometimes a couple centimeters long. If we sublime it after slurring it in ether, so slightly different sublimation conditions, we still get needles of the 1 beta polymorph. If we co-sublime radicals 1 and 2, what we land up with is some crystals of radical 2, its beta polymorph, and then we get reproducibly blocks of the beta polymorph of radical 1. So not needles at all, but small blocks. And if we co-sublime these 2 things at 100 degrees after slurring them in ether and then removing the solvent, we land up with blocks of 1 beta and blocks of the 1 alpha polymorph, again, reproducibly. So co-subliming these 2 things is allowing us to control either the morphology or the polymorph, depending on which conditions we use. And we think this is down to our sort of preliminary computational results show us that this is down to the fact that this molecule does, in fact, interact favorably with radical 1, and that it's probably doing so along this sort of needle growth direction, which is stopping crystal growth in that direction and allowing us either to get blocks or to get the other polymorph. The direction in which the polymorphs differ is the one that is essentially perpendicular to the long needle axis. So that was an unexpected but nice result. So I'm going to change tack a little bit now for the last few minutes and tell you something about these DTDAs together with some metal-containing systems. And again, because we're into multi-component crystals, this was about mixing these things together and seeing what would happen if we put more than one component in the crystal. So we reacted this particular radical with cobalt-2 tetraphenyl porphyrin, and eventually got crystals of this very lovely coordination polymer. So here we have the DTDA coordinated to the cobalt through the sulfur. And in fact, in the crystal, we have these coordination polymers where the DTDA is essentially acting as a bridge between porphyrins. And what was particularly interesting about this system is the length of the sulfur-sulfur bond in the DTDA ring, which is significantly longer than it is in the neutral radical. And in fact, our recent CSD work has confirmed that this is tending towards the bond length one might expect to see in an anion. So what we established eventually we have in this system is within these coordination polymers, our cobalt is in an intermediate oxidation state between oxidation state 2 and 3. And our DTDA is somewhere between the neutral radical and the anion. And together with my colleague Ord Monroe, he did some calculations for us that showed that this polymer actually has, as you increase the number of monomer units, the band gap in this material decreases. And so we have potentially got something that could act as a molecular wire here. So in order to learn a bit more about the system, we looked at what it was doing in solution, and we did some extensive spectroscopic work to figure out that when you react this radical with cobalt-2 porphyrin, it interacts with the cobalt through the sulfur, and we get this radical porphyrin coordination material in solution. When it crystallizes, we get the polymer, and when you redissolve it up in an appropriate solvent, what you land up with is monomer units with cobalt-3+ and the anion. So this system behaves differently if you dissolve these two components together than if you take the solid and dissolve it up. So kind of an interesting material, and we're trying to follow up further materials with radicals, thiazide radicals, and porphyrins. So the last story that I want to tell you about today is about putting these radicals into porous materials. When you work in Stellenbosch, it is impossible to not work with porous materials. So we ended up doing so, and we first looked at putting these radicals into zips and so on. And then this is a favorite material in the Barber group they developed some years ago. This is a copper metallocycle that when you crystallize it, crystallizes with methanol in pores, these pretty green crystals. When you put it under vacuum and heat, the crystals that you get have essentially lost all of the methanol but retained their structure. So we have sort of empty pores, and they describe this as a seemingly non-porous material because it has these discrete pores. There's no obvious way that any molecule could move through these metallocycle channels. But in fact, Len's group has shown that any number of materials can, in fact, move into the channels in this material, including a number of volatile solids. So we thought, let's see if we can get our radical to go into this porous material. Which we successfully did. So if you take the apo-host porous material and some of the radical and heat them up together under vacuum, you see a quite dramatic color change in the material, and single crystal X-ray shows that we have in fact got the radical as monomers in the pores of this material. It's not 100% occupied, but nonetheless it's very clearly there. So we did the solid state EPR of these materials, and we can see that from the apo-host, including the radical, we see a change in the EPR. And if we then take that material and immerse it in dichloromethane, the radical comes out of the pores again, and we can record the EPR spectrum of the radical. And we also did, in collaboration with Javier Campo's group in Spain, we did the squid measurements on the system, and we can see that this is the CAR-T for the native host material, and then for the inclusion material. And what we see on modeling this data is an antiferromagnetic interaction between our radical and the host metallocycle. So I hope what I've managed to show you in this time is that firstly, these radicals are fun systems to work with. They're interesting, they show some interesting behavior, and particularly some interesting bonding in the solid state, and also that they really do show great potential as building blocks for materials with interesting properties, particularly by combining these stable radicals with other stable materials, we can develop things that have kind of unusual and interesting properties. So with that, it remains for me to thank the people who specifically were involved in the work I've presented today. Sean did the co-crystal stuff, Bernard and Talia did the computational stuff, Laura did the porphyrin work, Varia did the inclusion things, Marissa the CSD work, and Samantha the high pressure work, as well as the polymorph control system. All of these nice people have been kind enough to work with us and help us to understand these systems. These people gave us money, which is always nice. I wish they would give us some more. And then finally, I just want to end off by letting you know, if you didn't know about it, that the third Pan-African Conference on Crystallography is coming up in January next year, which is a great time to be in East Africa, which is where it is happening, in Nairobi, in Kenya. There's a couple people here who've been to previous Pan-African conferences on crystallography and can tell you that they are great meetings. So if you have any interest in what's going on in crystallography in Africa, now that we have a newly formed African Crystallographic Association, this is the meeting to watch out for. If you Google PCCR3 or African Crystallographic Association, you will eventually find its website. Registration is open. But that's my little plug for the day. Thanks, folks, for listening.
Thank you very much. So there is still time for questions. I see there one.
Thank you very much, Delia. I was interested in your atoms in molecules results, the ones that you described for the Laplacian and the bond and the density at the bond critical point. First thing that struck me is that you didn't see a bond critical point between the nitrogens. Does that surprise you?
Yes and no. I was expecting to see most of what we saw between the sulfurs. What we've also looked at that we are trying to finish off, smile at Maura in the audience here, is we've looked at one of the twisted dimers. So I think it'll be interesting to see there where the electron density is. But all sorts of experiments have shown that in these systems that unpaired electron density really does sit to a large extent on the sulfurs. So a little bit weird that we didn't see anything at all between the nitrons.
But you did see it between the carbon, where there's supposed to be a node. So it's okay, I absolutely accept that you'd expect most of what goes on to happen between the sulfurs, but what happens between the rest of the molecule struck me as surprising.
It is a little odd. I was also surprised not to see any kind of, is it a ring or a cage critical point that I would have expected to see between those rings, and I was kind of surprised not to see that in any of the systems. And again, I mean, we've looked at four different systems, and in none of them do we see anything between the nitrons either. So,
I mean, the other interesting thing about that analysis is that the sign of the Laplacian was the same for your SS dimer bonds as for the interdimer interactions. Did you expect that?
No. So actually, I'm just going to throw this out there. Please don't ask me too many hard questions about it. But both the electron density values and the sign of the Laplacian are kind of indicative of charge shift bonding, which requires some thinking about. Let me put it that way. Indeed, yeah. We're definitely still learning about exactly what's going on in there. Some expected things, some unexpected things.
Okay. Thank you very much, Delia. I won't hog any more of your time.
Thank you. More questions?
Thank you, Delia, for this beautiful talk. I mean, I'm always impressed by the depth by which you're studying these systems for years. It's really amazing. I was wondering about the pancake bonding, apart from the title that I really like because I'm fond of pancakes. Yeah. But can you tell us, like, the short idea of this type of bonding? Where do you put it? How do you explain it?
Sorry, can you say that again?
Can you tell us an ID, like short ID of the pancake bonding? Can you explain, like compared to typical covalent and other bondings, where does it stand?
Right. So like a covalent bond, we have interactions between orbitals and interactions between electrons. So in that way, it is like a covalent bond, but not as short as a covalent bond and not as strong as a covalent bond. So in that way, unlike a covalent bond. So they kind of fall somewhere in between covalent bonds, which are of course very strong and keep themselves together, and intermolecular interactions, which are much weaker and kind of fall apart and often don't have a particularly strong orbital component to them. So there's kind of aspects of both that fall into these pancake bonds, which is what makes them interesting. I still can't decide if I like the name pancake bonds or not.
There is another question here, but our microphone is... Okay.
Thank you, Delia, for the wonderful talk. I'm just wondering, the sublimation experiments where you're forming these multi-component crystals, we're obviously very aware of solution chemistry and mechanochemistry, but not a lot of people are doing sublimation chemistry in terms of crystallizing multi-components. What do you think is the requirements to get multi-component crystals through sublimation? I mean, I assume surface effects are important, and possibly the sublimation temperature of the two components. I was wondering if you can say something about that.
Right, so fancy you should ask that. I will send you my student's beautiful paper on sublimation for multi-component crystals. It's something we're looking at in my group in general at the moment. And my answer to what kinds of systems are amenable to sublimation is we don't know. It's worth trying. Everything ultimately sublimes at some point. You just need to find the right conditions. But certainly with multi-component crystals, we can grow crystals of organic salts and co-crystals from the gas phase by sublimation. And we can resublime those materials as well. So organic salts sublime, many of them, not all of them, but many of them do. The difference in sublimation temperatures that you mentioned, we thought about that as being a factor, but it actually, it doesn't seem to be in all systems. In one of the co-crystals I showed you here, there's a 50-degree difference in the sublimation temperatures of the two molecules, and we still get the co-crystal. And you can also overcome that if you think about how you do your experiment and you heat the two components separately and then allow them to meet in the gas phase. So at the moment, I think the answer to what can you grow crystals of by sublimation is anything you have enough patience to try and grow the crystals of. But it's certainly, as a straightforward experiment, if you are screening for different forms, it's definitely worth trying. Hydrates, we can also grow crystals of those by sublimation. So there's a lot of potential there, and it is absolutely underexplored.
Thank you. So if there are no, well, one more, but let's keep it short, if possible.
Could skip it. Did you look by any chance on the polarizability of those creatures, like perpendicular to the ring?
On the what of the crystals?
Polarizability.
Polarizability, no. Mm-hmm. That's a short answer. No, we didn't.
Because we have some results that show very interesting aspects of this collective polarizability.
Maybe I will come and talk to you about that, actually, because they're beautiful crystals. I didn't speak about the work we did with Panche, but they're also very bendy, those same long needle crystals, and the magnetic behavior changes on bending them. So there's all sorts of interesting results there. Okay, so I'll come and ask you.
Thank you.
I'm off the hook.
Being short. Good, so now is the coffee break. We'll see each other at 15:40, and let's thank both of the speakers again. Okay, thank you. Thank you for coming back. We'll apparently start with one screen and hopefully the other one is going to come on. Just before we start, there are two announcements. So first is for the members of advisory board. So at 5:30 you have a meeting. So that's a reminder. And then announcement for everyone is that at 7:30 we should gather at the pier of the hotel downstairs. So be there before 7:30 if you want to get on the boat. And with this we can continue with this session. And first speaker after coffee break is Helena Shepard. And sorry, please start.
Yes, thank you. Sorry. So I'd just like to add my thanks to the organising committee, of course, as everyone else has, but it's been a really great conference so far, and I'm really looking forward to the rest of it. So thank you very much for the invitation. So today I'm going to be talking to you about smart molecular materials. It's a slight change from what I had in the abstract book, and if you've read that and want to hear about that, grab me at a coffee break or something. I'm happy to talk about that instead. But today I'm going to be talking to you, as I say, about these molecular materials which can switch in some way. So in the particular class of materials that I've been working with for quite a while now are known as spin crossover systems. So we're going to have a look at those, and we're going to start with a kind of introduction to what spin crossover is before we go into looking at how we can think about maybe one day using these materials in devices. So this is kind of basic second year chemistry, but just as a reminder, you have for certain transition metals between D4 and D7 electron configuration, you have two different ways of distributing the electrons within the d orbitals when it's in an octahedral ligand field. So you can have the low spin states, like you can see on the left here, and you can have the high spin state, which you see on the right-hand side. Now, materials in these two different spin states will have a lot of different properties. So, for example, they have different allowed electronic transitions, and as a consequence, they're going to have different colors. They also have different magnetic properties. So in the D6 case that I've illustrated here, the low spin state is diamagnetic, while the high spin state is paramagnetic. And the thing that I'm particularly interested in is the fact that this set of orbitals up here is antibonding in nature. And as a consequence, if we have occupation of those antibonding orbitals, we get a weaker metal-ligand bond, and consequently, the volume of the high spin state is significantly larger than the low spin state. So the coordination octahedron will change by about 25% for an iron 2 complex compared to the low spin state. But that will change depending on how many electrons you've got and so forth. But that's kind of an idea of the sorts of volume change, at least around the metal center. Once we add a lot of organic shrubbery, that tends to decrease a bit. Now, most materials are either high spin or they're low spin, and that's it. But for a few materials that we call spin crossover materials, we can switch between the high spin state and the low spin state as a function of temperature. And we can have these kind of gradual transitions that you can see here, but we can also have much more abrupt transitions. And this is when we have a high degree of interaction, elastic coupling, essentially intermolecular interactions between your switching centers. So in that case, you have a high degree of cooperativity or communication, and so you have these much more abrupt transitions, and you can also have hysteretic effects in the solid state. And as was mentioned in the introductory part, there's also a lot of other stimuli you can use to switch these systems. I'm not going to be talking about it today, but there are things, pressure, light, gas molecules, all sorts of other things as well that we can use to switch between these spin states. So one thing that I should say is that I know this is kind of organometallic materials, and perhaps this is not the natural home for discussing organometallics, but what I would say is the origin of the phase transition is not particularly relevant to the matters that we're going to discuss today. Any material which has a phase transition, which shows some sort of volume change, a lot of these same things apply, so it doesn't necessarily matter exactly what the origin is in this case for spin crossover. But here we can quite nicely see this phase transition from high spin to low spin state. We've got a single crystal, which is orange in the high spin state, and a kind of brown in the low spin state. And you can see as we cool it down, it nucleates the low spin state, and that propagates across the crystal. And in this case, it's fully reversible. We warm it up, and the same thing happens, but obviously in reverse. So that's the kind of dynamic properties in terms of color change, at any rate. And we also have dynamic structures for these types of systems. So here, this is a series of, I think, about 10 or 12 X-ray structures that are looped together into a GIF, just to give you an idea of the sorts of volume changes and shape changes. We get distortions as well in these systems. So I think the case has been made really nicely over the last couple of days as to why we need molecular materials being put in all sorts of different potential applications, and things which can respond to the environment in which they are located and in some way adapt to that environment opens up really new ways for these systems to work. So there's all sorts of potential for these materials. But to date, I would say spin crossover materials have largely been a curiosity. I find them really interesting, but in terms of application, they don't have many in the real world. So the question then arises, and it's the sort of the underlying theme of a lot of what we do in my research group, is how do we go from these interesting but ultimately not very useful molecules to something which can actually be maybe used in devices one day? I should say this is incremental progress. I'm not going to present to you something, a new hard drive based on spin crossover materials. It's not realistic at the moment, but it's something that we would like to get to actually use these things for useful applications. So I'm going to tell you about 3 different stories. The first one being, can we design these molecules with specific properties in mind to fulfill a particular application? At the moment, it's a bit of a case of make a new spin crossover material and hope it's got nice properties. So can we design those properties in a bit more carefully? And the next one is synthesis. If we're going to make these for technological applications, this came up in one of the earlier talks, how can we think about scaling this up? Is this something that's going to be commercially possible, even if we can make these things work in the way that we want to? And finally, we're going to have a look at integration and how we can start looking at individual single crystals in devices and things that we can do to kind of engineer those crystals in a slightly different way, let's say, from traditional crystal engineering. So we're going to move on to having a look at this idea of design. First of all, we just need to think about what's the typical methods that people use for designing spin crossover materials. Well, you can make a new ligand, you can decide, draw it on a piece of paper and make it, to try and give you the correct ligand field, so the right sort of splitting of your d orbitals to be able to access both the high spin, low spin states. It's a good place to start. The problem is, though, that this isn't completely predictable, because the packing effects are really substantial in these materials. So here is a spin crossover material. It has 3 different polymorphic forms. So in form 1, we have this kind of relatively gradual transition from high spin to low spin. In form 2, we have no spin crossover. We have some zero field splitting effects down at low temperatures, but we don't have any spin crossover. And then in form 3, we have this abrupt transition with hysteresis. So it's the same molecule, same ligand field, ostensibly. All of the differences arise from the differences in packing between these 3 polymorphic forms. So this is something that's very difficult to predict. I don't need to tell this audience that this is not a simple challenge to address. We could also try some other things. So we could try chemically modifying a ligand. This is something that's used a lot. So here's the molecule we're going to be talking about a bit today. And it has had all sorts of different chemical derivatives made. And these are essentially making small modifications to the ligand reasonably far away from the metal center to try not to influence the ligand field too much, but to try and change the interactions between molecules in some way. And again, that's possible, but it takes time, and you're not guaranteed you're going to have a spin crossover material at the end of it. So you can also try changing the anion, and again, this works quite well. You can change the anion, you'll change the spin crossover properties, but you've got kind of limited options there. And you can also try changing solvent molecules. Again, this will change your supramolecular aggregation, and as a consequence, you'll change your spin crossover properties. But you are limited with stability, which, of course, if you want real-world applications, is going to be potentially a problem, as well as also solvent compatibility. We're limited to the number of solvents, again, that we can use. So what we started looking at was co-crystallization. So this is my PhD student, Lee, who is absolutely fascinated with crystal engineering. I wish he was able to be be here who'd really love this meeting. And obviously I don't need to explain to you what co-crystallization is, but I think it's worth pointing out that although it's used a huge amount in organic chemistry and the organic solid state, it's not something that's used at all previously in spin crossover materials, or even really in organometallic chemistry, because it was almost seen as kind of diluting the active sites, so nobody really thought to try adding additional things into the crystal lattice. So as I said, this is the molecule that we are interested in, the active molecule, if you like, and it has these 4 hydrogen bond donors. And then we had a series of coformers. So there are, how many is that, 5? We've got probably up to about 10 or 12 at this stage. And these coformers were chosen because they had kind of suitable potential hydrogen bonding interactions with the molecule of interest. And they have slightly different properties. So we have some that are linear and rigid, we have some that are more flexible, and some which have just a kind of completely different geometry. So we're interested in seeing how these different properties of the coformer affect the aggregation of the molecules and then the resultant properties. So we were able to make 11 new co-crystals using this. I won't go through every single one. 8 of them form these one-dimensional chains, which is fairly unsurprising looking at the geometry of it. Here we have in blue our molecule of interest, and then we have the coformers shown in green. And you can see, hopefully, that it's linking, bridging between 2 adjacent molecules. You get pairs of coformers bridging between pairs of spin crossover complexes to form these one-dimensional chains. That's a really common motif that we see. So 2 of the co-crystals instead form 2-dimensional sheets. So here you can see we've got the molecules of interest, but this time we've got the bridging between adjacent molecules, giving us this kind of 2-dimensional sheet network. And one of them forms a 3-dimensional network, which is much more complicated, basically. So of these, 7 of them were spin crossover active, which is quite a good hit rate when you're making new spin crossover materials. And if we classify which coformers did what, the one-dimensional chains were formed from these linear, rigid coformers. The 2-dimensional sheets were formed from the slightly more flexible coformer, and the 3-dimensional network was formed from that one, which had quite a bent geometry. So we're just going to have a look at 2 examples, one of the chains and one of the sheets, just to see how that difference in supramolecular structure manifests itself in the spin crossover properties. So here is our first example, and here we have, again, this one-dimensional chain structure with our coformers bridging between, and the slightly more offset, shall we say, coformer, which forms these 2-dimensional sheets. So for the one-dimensional chains, the story is slightly more complicated. I don't really have time to go into all of it, but if you're interested, there is a publication there. But for the one-dimensional chains, what we see, if you look at this cartoon here, this is a spin crossover material, a molecule, this is the coformer, and we've got 2 crystallographically distinct types of coformers. The consequence being that the interactions and the distances between these molecules here is different from the ones here. And what we end up with is a stepped spin transition where we go to this intermediate phase, which is the result of a symmetry lowering, a unit cell doubling, so we now end up with a long-range order of high spin and low spin states throughout the crystal lattice. We then have a reentrant phase transition to get us down to the fully low spin state. But in this case, we see probably the reason for this sort of ordering, this step in the spin crossover properties, is the fact that we have differences in the interactions between, like along the chain, effectively. So this coformer here, for example, is showing that pedal-like motion that Aurora mentioned back at the beginning of the meeting, and that kind of stops in different coformers at different points, giving rise to crystallographic distinction between them. So if we look at the 2D sheets, by contrast, we have an abrupt transition with no step in the middle. And this is because, although we still have 2 crystallographically distinct coformers, we still have the same interactions between every metal center. So there is no distinction either across the sheet or along the chain or whatever. So the point of this is that the properties of the coformer largely determine this supramolecular architecture and the spin crossover properties. It's a modular approach, so we don't have to spend a lot of time making complex organic ligands. We can buy a lot of different co-formers off the shelf and screen through a lot of materials quite quickly. As I say, it's quick and easy. Whether or not it counts as rational design, that's the end goal. At this stage, absolutely not. But it at least gives us another tool to be able to start using logical approaches rather than just make it and hope for the best. We now have at least something to try and aim for as we're going down this pathway. So that's the design, kind of spin crossover materials. Next, let's have a look at the synthesis. So one of the things, if we're going to make devices, we need to think about how we manufacture them at large scales. If we have a very high-value application, it's worth spending time and money making very high-quality, very beautiful crystals or films or whatever it is you need. If it's a relatively cheap application, you can't afford to do that. You need to be able to synthesize these things at large scales very, very cheaply. So it's entirely dependent on how valuable that application is. So we were interested in mechanochemistry and whether or not we can make these materials mechanochemically. And the answer is yes, we can make individual complexes, we can make coordination polymers, we can make MOFs, all mechanochemically. And one of the examples that I'm going to talk about today, it's done by Jed, my first PhD student, is basically just grinding together two very cheap starting materials. This is Moore's salt, it's an iron sulfate-based salt, and amino triazole. So you grind them together for about 5 minutes without anything else, and you produce the one-dimensional coordination polymer where you have metal sites which are triply bridged by these triazole complexes. So at 0 seconds, you have colorless starting materials, and you grind them together for 30 seconds and a minute, and you keep going, and you eventually form this spin crossover material. It's dark purple, which is characteristic of the low spin state of these materials here. And you can see if we take it from room temperature up by 100 degrees, we can see the color change really clearly, and this is again characteristic of going through that spin transition. And for people interested in the spin crossover properties, essentially they are, and you can make them fairly easily, the same as what you would get from solution. So we're not losing any of the cooperativity through introducing defects or anything. Through a kind of annealing process, we can get those back again. So what we did find, though, was slightly strange, is depending on the time of year, we would get quite different results for this. And in the UK, you get quite varying ambient temperatures, ambient humidities, and so we thought there was something strange that might be going on. And what we found when this work was followed up by Georgie and Rona was that mechanical force is not necessarily always required for these types of reactions. So here we have just when it's colorless, that's the starting materials, just being put into contact in situ and then being videoed over the course of this video is about, I think, 40 minutes or so. And you can see again that formation of the product happening in situ spontaneously without any applied force or solvent or anything else. We can also look at this process on a single crystal scale. So here we have a crystal of the ligand, and here we have a crystal of the metal salt. And hopefully what you can make out is that this ligand is deliquescing. So it's taking humidity out of the air and dissolving itself to form a very concentrated solution, essentially. And what then happens is this allows diffusion of that ligand molecule, presumably, into the center of this metal crystal, well, metal salt crystal, I should say. And again, we get the formation of this dark-colored product. And what we don't see, however, is the metal salt dissolving. This is not just a concentrated solution state reaction that's occurring. Yes, the ligand is in solution, but the metal salt remains as a solid. So again, if we're interested in the properties, we can see that the structure is exactly the same as we see from solution state reactions. Once you've washed it, of course, you've got some slight impurities remaining. Again, the spin crossover properties are exactly what you would expect for these types of materials, so we're not making a lower quality material, let's say, through this method. So obviously, humidity has a really important role in this process. And so over the course of, this is about 45 minutes, and we form this kind of puddle, if you like, of water, ligand-containing water, around the complex. So what happens if we take a ligand which is a lot less hygroscopic than this one? This is probably the most hygroscopic material I've ever worked with. It's quite incredible. So here we have a related system. Here, this undergoes a tautomerism, and you end up in the final product with the proton in the 4 position. So it's a kind of direct analog of that initial material. So we can see, whereas this one was over about 42 minutes here, this is 98 minutes. If you look here, it looks like there's nothing much going on. We've got 3 smaller crystals this time of the ligand, just because it comes in smaller crystals. And it looks like there's nothing happening. You might just be able to make out some regions here where the crystals are in direct contact. We are actually forming the product. So it's not that it's not happening, it's just that the diffusion can't happen as quickly when it's not been, essentially when it's not dissolved itself through deliquescence. So we can look at that in more detail. We can look at the uptake of water as a function of time. This is 30,000 seconds. I'm not entirely sure what's gone in seconds, but it's not a very long period, but we're already gaining kind of 5–10% of the mass of the material. So again, I'm really sorry, the scales I think will be quite difficult to read, particularly for those of you at the back. But the point is, for this very deliquescent ligand, this is 2 hours, so 120 minutes scale here, and this scale here is up to 2,000 minutes. So it's about 5 times longer to get the reaction to go when you have this less deliquescent ligand. And we can also measure it as a function of different humidities. As we increase the humidity, we increase the rate of the reaction. So we're able to monitor these reactions in situ by assuming that the amount of darkness, if you like, of the product is proportional to the production of that product, which for these materials is a pretty reasonable estimation. So it's due to that colour change, we can monitor these things happening in situ. But what happens when we actually look at the crystal itself? Well, it's no longer a single crystal. You touch it and it kind of falls apart. It's not, a structurally integral crystal anymore. The thing about these particular materials, though, particularly the ion complexes, is that they are notoriously difficult to crystallize even in solution. So the structure of these materials is known from powder diffraction. So as a consequence, we thought, can we move to an analog which is known to crystallize at least from solution? It will give us a better chance of seeing what's happening here potentially. So for that reason, we moved to some copper analogs, so taking copper sulfate and the same 2 ligands. And we can see here again, we've got a single crystal scale reaction. We'll just wait for it to loop back round again. Spoilers. So here's the ligand crystal. And again, it's deliquescing. This is this top one again. Deliquescing, forming this water envelope. And then we can see again, the metal salt does not dissolve, but it's reacting in situ. We're getting all sorts of growths and things happening. So again, we can look at this in the bulk as well and monitor the rate of colour change as a function of time to get rates and so on. But the interesting thing in this particular reaction is kind of what's going on. Can we understand the mechanism a bit better of what's actually happening where? So the stoichiometry, you wouldn't be surprised to learn, is very difficult to control when you've got individual crystals, and some of them are very hygroscopic. It's quite difficult to control that accurately. So what we did was another experiment where we have an excess of the triazole ligand, and then we put that into contact with the metal salt in a humid environment, and then as a function of time, we get to this here is what's left of the metal salt. It's never dissolved, hasn't reprecipitated, but it has clearly undergone a massive transformation. It has expanded and kind of burst apart, if you like. And if we look at this under a polarizing microscope, what we can see is that it transmits plain polarized light. So great, could be a crystal. We rotate it again, it extinguishes. You think this is going to be a single crystal. So this is the diffraction pattern, unfortunately, of the copper sulfate salt. And we compare that to, we obviously cut off a chunk of this. We don't measure the whole thing. There's clearly different parts of it. But we can cut off a chunk that looks like a perfect single crystal. But instead what we see is a diffraction pattern that looks more like a fibrous material, kind of fiber-based diffraction pattern. So we can have a look at these pseudo-crystals, let's call them, and we can see that we get lots of kind of weird-looking things, basically. We were just fascinated, kind of looking all around, seeing what we could find. we get clearly this formation of fibers that's occurring out from the surface and from the inside of the crystal. So I should just say that this is actually the same crystal. We cut it across there, and then we put it under the SEM and looked at different parts. So this was originally the inside of the copper sulfate crystal. So we get these kind of baleen-like formations of growths coming out of the crystal. And if we kind of cut the crystal up more and really look inside what now is the center, again we see the formation of fibers everywhere we look, essentially. So this is a very facile synthetic method. It was first identified as a difficulty to reproduce reactions. It's worth paying attention to when these sorts of things happen. And the humidity in these sorts of reactions is really key to the reactivity. So we've been able to use these really small-scale reactions to elucidate what's happening at different steps. In terms of what's happening on a molecular level, atomic level, it's still not clear how it's diffusing in and that sort of thing. But it's something we're looking at in more detail. These types of reactions, they're not new. This is known as accelerated aging. There's a nice review paper here for those who should be interested in learning a bit more about the driving forces behind these sorts of things, because I certainly had never really encountered it when we first found it in the lab. But with this in mind, what's this got to do with devices? How can we use this sort of information to actually be useful somehow on an industrial scale? Well, we can look to some more work that Georgie started looking at, where essentially what she would do would spray down a thin film, basically a concentrated solution of the metal salt, and leave this to dry. And this would then lead to the formation of a very thin, polycrystalline, powdery deposit, let's say, of the metal salt. We can then spray down a very concentrated solution of our ligand, and we can leave this to react in situ in a very similar way to what we've just seen with individual single crystals. And we then form the product in situ. And this is something that we can do really cheap, really easily. In the lab, we can use an air gun. In industry, you can imagine this happening potentially on quite large scales. So it's something that's a really cheap, really easy way to synthesize the materials. It will not give you nice, beautiful, thin films, of course. It's not for that sort of application. But what it does do is give you materials that you can actually start to work with. So we've done this on a variety of different substrates. Paper ones work particularly well. Obviously, they're being porous. It kind of helps to keep the materials in. But you can see if you compare the spin crossover properties to the bulk, they remain pretty similar. And you can characterize them in a variety of different ways. And you end up seeing that it is exactly the same material that's being precipitated there. So I was hoping to show you a video, but we're actually looking at these with a company looking to use this sort of thing for labeling on packaging, for example, looking at the thermal or light or whatever history. Excuse me. And so as a consequence, I've been asked not to actually show you the pictures of these kind of mocked up packaging things that we're looking at trying to use. But the point being, we can now get to applications that are disposable, things which will stop us from throwing away, say, the pork meat or beef meat or whatever it is that you've got. You instead can dispose of this device, but it's cheaper than disposing of whatever else it is that you're packaging. So finally, I would like to talk briefly about how we can think about engineering single crystals in a more elaborate way. We've seen an example that was brought up in the introduction to the session that Panchay developed with the really nice magnetic parts of the crystal, and that we're able to then use it to walk along the surface. So things like that, which are probably a bit more, let's say, complicated than just spraying stuff down and hoping for the best, but are potentially more useful for these higher level applications. So here is a very anisotropic crystal of a spin crossover material. The structural details, again, don't really matter. This same sort of technique applies to any sort of phase transition material that has a volume change. And here, if we look at the length of this crystal as a function of temperature, we can see that as we cool down from room temperature down to very low temperatures, not much happens really. You get a very slight negative thermal expansion property, which is where the crystal gets slightly longer as we cool it down, but that's mitigated by contraction of the other two sides, which is a very anisotropic process to reduce the volume. However, when we go through the spin crossover, we get a very dramatic decrease in the length of that z-axis, and the crystal kind of decreases in all directions. And you may or may not have been able to notice, but this is actually a video of the material as it's, after it's grown, undergoing a spin crossover. You might be able to make out the color change. It's a black and white video, so that doesn't help at all with that. But you might be able to see the shading changing slightly, and you get kind of propagation along this direction. But compared to the absolutely amazing videos that we've seen in the last few days of crystals jumping and bending and rolling, and I forget all of the different things, there's really beautiful mechanical effects. This is actually quite boring. So we were interested in what can we do to make that a more interesting mechanical event for these types of systems. Now, in pretty much all of the materials that we have seen previously, the reason that they have those unusual mechanical properties is they have some sort of change in structure that results in a bilayer. So you get a mismatch in strain, which causes the bending or the curling or all those sorts of different things. In these systems, the problem is the entire thing undergoes the phase transition, and as a consequence, you don't have any, well, there's going to be a bit of strain in between these different parts, but ultimately, you don't get that same sort of mechanical response. So what we did instead was I took a single crystal and deposited a thin layer of metal on the top. So in this case, it was aluminium. It was just a micron of aluminium deposited across the top. And what that now means is we'd have a bilayer system where we can generate that strain through this additional layer that we've popped on. So this is what the crystal looks like at high temperature. As we cool it down, we get that very gradual negative thermal expansion, so that elongation of the long axis of the crystal. You can probably barely see it. It's quite small. Then as we go through the spin transition, we get this significant contraction of the long axis of the crystal, and as a consequence, we end up having a quite much more dramatic downward deflection of the crystal as a result of that spin crossover behavior. Now, depending on the properties of your crystal composite, you can change how large this actuation is. And we're going to talk a bit more about that, about how we actually optimize this sort of device, let's say. Basic device, but there we are. So this is an equation which was originally developed by Timoshenko in the 1920s to model bilayer strips, those classical two-layer bits of metal strongly bonded together, and how the strain causes particular curvature and motion of the tip. So we just added an additional term to deal with the length of the cantilever versus the length change that occurs during the spin transition. The important points are really the Young's modulus and the height of each material, so the relative thickness of the two materials. So here we have, again, you probably can't see what's on the axes, but here we have the deflection of the tip of the cantilever here as a function of the thickness, in this case, of the passive layer. So again, this is something we can engineer. We can change this to optimize the deflection if we want to. Similarly, the same thing for a given passive layer. We could have a different active layer. It's probably a bit more difficult to control in the case of single crystals. But really the point is that it's the ratio of the two that's important. And here we have the length of the actuator affecting tip deflection. That's just a geometrical consequence of a cantilever. But probably more interestingly is that as we change the material that we use for the passive layer, then we're effectively changing the Young's modulus. And so again, we can change the tip deflection that occurs, the amount of strain that's built up. So we're creating this mismatch in strain rather than have it generate itself, if you like, in situ. But it does allow us to kind of engineer the geometry and engineer these mechanical properties in certain cases. I'm not saying this will work in every case, and you do still need things like this highly anisotropic crystal and so on, just to be able to get those sorts of bending properties. So just to conclude then, there's the three kind of different areas of things that we're looking at in my group at the moment. This is the design element, and can we use traditional crystal engineering approaches in these organometallic materials to create new functional materials. Still a long way to go, but I think it's an interesting step in a direction, let's say. Then looking at synthesis, we've developed this kind of cheap and easy synthesis where we just put the two materials together and they kind of form themselves in situ. There's some interesting and weird things happening during that process, but ultimately if we want to use that for applications, it's a relatively simple thing to implement. And then finally, if we've got higher level applications that are going to generate more money, essentially, we can afford to spend more time really refining how we actually integrate these single crystals into devices, and we've seen so many really lovely examples of that during this week. So I'd just like to finish by thanking my group, the people in red, are the people who have actually done the work I showed you today. Thanks also to the funders and collaborators who I was working for when we did the actuator stuff. And then I'd also like to thank all of you for your attention. Thank you.
Thank you for this another nice talk. So there is time for questions.
Thank you for the beautiful talk. I have a question. When you showed the synthesis using the spray technique, you show that you do it in 2 steps, but you get the final product is the same as one already with everything. So I was wondering what was the rationale of doing it in 2 steps instead of just spraying the compound?
Yeah, so the reason is that if you have a solution of both the ligand and the metal at the same time, it will start to precipitate in your spray gun. So we tried it, and you get clumping, and you get problems with it getting gummed up, basically. But here, basically, because we're letting the iron salt dry, what we have on the surface is crystals of the iron salt. So then we're adding a concentrated solution of the ligand, which is effectively the same thing as when the ligand crystal deliquesces. It forms a concentrated solution of the ligand and goes into the crystal. So it's the same sort of process. We also have, if it's on a paper substrate, that tends to absorb the water away in any case, so it kind of speeds the whole thing up. So
Sorry if I can ask another one. So how do you control the stoichiometry then? Because you need to,
So you can get air guns that tell you exactly how much liquid you're dispensing. And by controlling the concentration of the 2 reagents, you can, again, it's not going to be perfect. It's going to be
some thermal treatment after that? Or
Sorry?
do you do some thermal treatment after you spray them to make sure that you are crystallizing the whole thing?
No, we just leave it to dry.
Okay.
So I guess you could warm it up to dry quicker, but other than that, no.
Thank you.
Thank you.
Yeah.
Hello.
Kevin Roberts, University of Leeds. It was a very nice talk. I was very interested with the if you like, the solid, if you want to call it that, solid state reaction between the 2 components, which is not so dissimilar from making organic co-crystals as well.
Mm-hmm.
But I kind of wondered if there was any topochemistry going on. I mean, because the copper sulfate was the one I was watching, had a very, very pretty morphology. It does have a very pretty morphology.
Mm-hmm.
And I was just wondering if there's any surface-specific effects that were driving it through the mass transfer.
So I spent a long time trying to convince my student it'd be a great idea to have different crystallographic faces interacting with different, in different orientations of the rest of it. Part of the problem is with this one, it is so hygroscopic that it's quite difficult to measure a face, honestly, because they become so globular so quickly.
Yeah,
when
I'm
you
kind of
make them.
wondering if you grew a nice big crystal, which for copper sulfate's easy.
Yes.
You could then sort of drip it on, a bit like doing a contact anger measurement.
Okay.
Could you drip it onto the surface? And
yeah.
The other thing is more naive. In the spin transfer reactions, is the crystallography changing, or is the crystallography the same? In the spin crossover phase transition, what's the crystallography doing of the material?
So in each case, it's different. Usually, if you have a gradual transition, you get almost like a solution type activity where randomly you get low spin sites, and it looks crystallographically like disorder, essentially. Sometimes, though, if you see those much more abrupt transitions that we saw, you get symmetry breaking quite frequently, phase transitions, where you get, in the case of the one with the intermediate phase, a long-range order of high-spin, low-spin states. If you have just a full transition down to the low-spin state, it's quite commonly associated with a phase transition as well, if it's abrupt. Certainly when you've got hysteresis, it's almost always accompanied by that kind of first-order phase transition and crystallographic differentiation.
But in the copper sulfate, it stays blue.
Copper sulfate, yes, so it stays blue.
So it doesn't, there's no change in the hydration state of the pentahydrate.
So when it stays blue, we had to do this to show, like, the exposure here is not brilliant, but it's because we're trying to show these things which are kind of quite difficult to focus on at the same time. It does get more blue than it started out as, and again, it's quite difficult to film that because it happens so quickly. To catch the initial state, it's kind of pale blue, and then it goes a kind of a darker blue. We have, again, a powder diffraction, though. There's no single crystal structure, no matter how much we try from solution for this one. But by refining the iron analog, the structure of the iron analog with the data from the copper powder, we're pretty sure that it is a direct analog of the iron complex, which is well known.
Thank you very much.
Thank you.
Last short one.
Hello, so Simon Parsons, Edinburgh. Nice talk, Helena. Just going on from the answer you just gave to Kevin's question, you showed that movie towards the beginning of your talk where you showed the transition, the high spin to low spin transition for a crystal, and you showed that the crystal transformed from the bottom of your image up to the top, and then the reverse. It followed exactly the same pathway, just backwards. Yeah. That's quite interesting, isn't it? It's the fact that it has this almost memory of the way that the way that it originally transformed. And I wondered whether that's a consistent feature of these crystals, or whether sometimes the transitions start in the middle of the crystal and then go out, or whether it's always from a surface.
You tend to nucleate at a defect, depending on where that is. If it happens to be in the middle, it could be in the middle, for example, but it will usually be on a surface, or a corner is the most common. If we look, can I go back? Oh. Yeah, so if we look at this crystal, you'll see the transition happens in this direction, and we spent a long time debating whether this is just a thermal gradient across our heating stage. But the more we would take crystals, we'd reorient them, put them next to each other, you could see them always going in the same direction, and we're pretty sure it's not a thermal gradient. And in fact, this bit here I find more interesting, is this angle here, is the fact that that is completely the same as the angle, I can't remember which angle it is, but one of the crystallographic angles. And what you see is that we did a study 4 or 5 years ago now, where we looked at the elastic properties of the material and how basically a stiffness in different directions, and how that correlates quite nicely with the propagation of these phase transitions. So there's definitely a crystallographic element there. It's going to be, the physicists talk about it in terms of these elastic interactions. We tend to talk about it in terms of the intermolecular interactions that are there. But certainly the way in which those molecules are impacting on the next one is going to affect how that propagates in different directions. And that's all crystallographic, I guess.
Okay, thanks very much.
Lovely.
Thank you. Let's thank the speaker again. Okay, so our second talk is from Haggai Cohen. Haggai, I'm sorry.
Good afternoon, everybody. And let me start with thanking the organizers for putting up such a wonderful program. I already learned a lot, and it's less than half of the program, so really really very nice with a lakey atmosphere, very nice. So I will talk on a project that is not of my main work, and mostly I work with electron spectroscopies, XPS mainly, developing new techniques, and one of them is CREM, or the chemically resolved electrical measurements, where you actually use the photo-ejected electrons as kind of flying electrodes with a unique property of having an address. So you know what atom they came from. So there are very new things with the XPS technique that can be exploited. I'm not going to talk about that. It will be maybe at the background of stuff, because there are a lot of issues regarding working with organic materials. X-rays and organics, everybody knows. There is also a problem of charging, resolution, like how to resolve the different nuances of structure and conformations and so on. And there is a lot to do there if you try to apply. So at the background, you will see there is something about those techniques, but I will not talk about those. Here you see damage after very long irradiation, like I think it was about 24 hours of low flux of the crystals that I will show. These were not irradiated, so they are still clean, not colored. But this is a huge damage. XPS is surface sensitive. This is already a bulky stuff, right? So it's really something here. But I can promise you that the data you will see is free of that damage. Okay, so now last comment before I start. People related to the crystals as the dead state of matter, kind of. And I would like to, in addition to the fantastic things that were shown, to keep in mind that electronic states, all the electron dynamics, is very exciting. It's very far from being dead. Okay, so, and you can learn a lot from that, and even get some information that helps understanding the structure itself. Okay, so the project on perovskites, I actually joined it very recently. I don't have too much. I want to bring some interesting results that I observed there that I believe to be of more fundamental importance. And let's see. So perovskites, this is a very broad family with this structure of ABX3. And there is a lot of members in this family, oxides, halides. I think the excitement, recent excitement, is due to the photovoltaics of this family of materials, where they get really very good efficiency. But there are problems of degradation, of toxicity, and therefore people try now to look for new materials, and one of them is those family of metal-free halides. And what will come out, we shall see in a minute. So metal-free halides, what we used is based on the A cation is Dabco. The halides could be either any of those three. And for the B cation, we used two of them. One is ammonium, and this is already a published work, and this is an ongoing work with the hydrazine. Crystals. So what you see here is that they succeeded, it's a Chinese group, succeeded to grow very large crystals. This is a centimeter size and very high quality. You can get it from these, the width of these lines, but also from many characterizations that I will not show. Very high quality samples and large, as I said. Directly going to the optical absorption, you can see this is the original measurement, the transmittance. Here is the absorbance. The absorbance edge is very high in energy, very short wavelengths. And that means that for photovoltaics, you're not going to capture anything, right? There is some small peak here at 4 volts. It's here also. But it's really a small one. It may have some importance, but not quite at the moment. So photovoltaics, not really. These are band calculations. And as you can see, the band gap, so this is the top valence bands and the bottom conduction bands, and you can see the band gap. For optical absorbance, you need direct transitions, and you see that it is not going to make a big difference here because the bands are really flat, okay? Now, if you think about it, flat bands in the K-space mean high localization in the real space, simply a Fourier transform issue, okay? So we expect, and we shall see in a minute, that this is indeed the case. So I actually asked to try to present this information on a partial density of states. So you build up the bands starting from atomic orbitals. So it's a linear combination of atomic orbitals. And here is what I got. This is a top valence band. It is located on the bromine. This is for the bromine. And you see bromine, nearly nothing here. Now, there is no contribution to the valence in the other sides. The bottom of conduction band is hardly seen here because the occupied space is not to scale. Unfortunately, I'm sorry for that. But no contribution from the bromine, and it is mainly dominated by the actually DABCO, the DABCO cation. Now, the meaning of what we see here, that we didn't have a problem of indirect transitions in the K-space, but we do have such a problem here in the real space. Because if you want to excite an electron from the valence to the conduction, you have to jump over a very large distance from the bromine to the DABCO. And this is a very large, so overlap of orbitals is very small, and therefore there is a significant suppression of intensities. So if you take it all over, everything, then you see we have a broad band gap. We nearly have no defects to compensate for absorption of light. And even the super band gap, over band gap transitions are suppressed because of the indirect real space. So again, for PV, it will not be good. Photovoltaics, I mean. On top of that, there is one more thing. Here is the valence bands, and you can see that there is a very narrow valence band. This is exceptionally narrow valence band, at least in my experience, which actually tells us that there is very little hybridization, consistent with the previous structure. And impressively, there is nearly no density of states for another 9 volts. So the next peak is here. So what we see actually is that there is a second gap here. We shall talk about it in a minute. I just want to add that this work function measurement is simply is related to the Krem technique, is simply to know where to put the Fermi level on this scale. Okay, so it's nothing more than that for our discussion. So altogether, again, we have a second problem. We have this huge second gap. It is not perfect. You can see here that there are some small signals, so there is a little bit density of states, but it is very large. And again, I combine all the information that we were talking on. You see, we have the
main gap and the secondary gap, and all over we have a kind of a semi-gap with some transitions available, but very inefficient. Okay, let's go on. So again, it's not good for photovoltaics, neither for UV, because we talk about 16 electron volts. But if you think about that, you realize that if we find a way to overcome the problem of excitation, we have maybe a very important feature of a combination. Because if the transitions are not allowed, it will be also the way back, okay? So we can maybe gain long lifetimes if we succeed to excite, and maybe that can be applied to X-ray detectors. Now, X-ray detectors, if you think about that, everybody usually look for heavy metals because you want to absorb the X-rays. No heavy metal here, so it's a kind of a question, will that succeed? And here is the result. You can see here the performance with, I'm all the time with this one, with the ammonium and bromine. You can see the dependence on the flux of the source, and also for several different voltages that you put over the detector in order to collect the current. This is a summary of the maximal currents obtained. And you can get here whatever 300, let's remember this, for 50 volts. And unfortunately, above 50 volts, the sample is not anymore good. It starts to degrade. So we were talking about degradation, so I'm back to this feature, mainly with the iodine samples. And let me just comment that there is some issue of self-healing that people are very excited about because sustainability is now an issue. And these samples do show some self-healing. You simply put them in air and they self-heal. So part of the color is removed and then they recover some of the properties. Working with hydrazine, which is, as I said, it's not yet complete, gave some interesting results. First of all, again, large crystals. Look, this is 3.5 centimeters long. Large crystals, single crystals, high quality again. There are some changes. The chlorine-based sample is essentially with the same space group, but these ones are now with octahedra sharing faces. So the symmetry is different now for the bromine and iodine, and they also grow elongated kind of with the as of the X-ray detection, the performance is by far improved. First of all, if you compare the value obtained for 50 volts, the 800 compared to 300, this is an important improvement, but also we can go above the 50 volts to 200 volts. So it's a large, it's a good improvement, and even maybe more important is the fact that there is much less noise. So all the values that describe here, noise, whatever, signal to noise, are by far better. The reason why is not clear to us yet. We have some suggestions. I will show you first what doesn't look like. First of all, this secondary gap, you see the valence bands of the two samples, essentially the same. Okay? For the iodine, this is a bromine. For the iodine, it looks like even worse. I'm not sure if it relates to degradation or whatever, but it doesn't look like an improvement. Band calculations show essentially the same indirect issue, similar magnitudes, Maybe there is something hidden there. It is not yet clear, but it doesn't look like the reason. So we know something that we know, that hydrazine samples are more stable. So there is much less migration of the halide atoms. This is something we know. We also suspect that maybe stronger hydrogen bonds play a role on the electronic distribution of the orbitals. And maybe also the spatial distances that are for the electron jump from conduction, from HOMO to LUMO. And with that, I stop. I will be happy to get also advices in this case. I try to focus on those messages that I believe to be of interest and not in the regular way of the treatments of this kind of problems of optical absorbance. You could see how the semi-gap helps the long lifetimes, which is a new issue that may be of importance that is beyond this specific system. And of course, lightweight, non-toxic, cost-effective, all the regular things that you are the community to know very well, much better than me. And with that, I would like to thank again the people that worked closely with and all the group in China that took part of that, and thank you for your attention.
Thank you for the nice talk. So maybe some quick questions, because I would like to give the online speaker the full time for questions, and for us here we can discuss during the boat trip. So if there is a quick question, yes, otherwise we can continue.
Should I offer you a question? Somebody.
And go on, Luca.
Hi, thanks for an interesting work. So I was wondering about the electronic structure calculation you made.
Where is it? I don't see it.
Sorry, I'm here.
Ah,
for the electronic structure calculation you made, like these systems are like, in other words, what's the extent of the delocalization of the? So you said it's fairly localized. Is it something the DFT is able to capture well? Well, it fits the experiment. So, but I'm just wondering about the nature of the bands. If you, I mean, trust fully the DFT results.
I don't have a full answer to you, but I can emphasize the following. First of all, we have a number of independent indications for high localization. It's the valence band, the narrow valence band, the band calculations, okay, and the optical absorbance, of course, which was 2 to 3 orders of magnitude low. Okay, so there are several indications for that. And the exact calculation of how exactly the density of states is distributed, I don't have at the moment. So generally, it looks like a really homo-lumo, like well-sighted, at least in the valence band, like at least a homo.
Right. I have also another question, but I think we can discuss after.
Okay.
Thank you.
Thank you. Yeah, last one.
Hi, Martijn Zwijnenburg, University College London. Actually, as much a question as a comment, and following on also the previous question, it's sort of like, I'm very fascinated by your material because it's almost like a textbook ionic material with like a perfect flat band. So, I mean, I'm quite fascinated by that. So, yeah, no, it's more, I will make this as a comment than a question. So it's very interesting. Thank you for sharing this.
Yeah, the distance, I think, between the two sites, the DABCO and this, is a huge distance, indeed.
Okay, thank you. If I can make a comment, I guess probably one has to look also how big the unit cell is, because if the unit cell is big, then the Brillouin zone it will be very small, so the band will be quite flat anyway. But okay, thanks a lot, and
thank you very much.
We can go for the for the third speaker that should be online. Ah, sorry. Okay, it seems we got recording. So
hello everyone, here is Amit Mondal from Indian Institute of Science Education and Research, Kolkata, a PhD student working with Professor Simala Reddy. First of all, I would like to thank the conference organizing committee for giving me this opportunity to present our work here. Now, before going to the details of our work, here I would like to briefly introduce different research activities of our group. Our group has expertise in establishing structure-mechanical property relationship by specially designing mechanically flexible crystalline materials by crystal engineering approach, means aiming to different applications like self-healing crystals, thermosilent jumping crystals, flexible semiconducting crystals, and various stimuli responsive crystals, and so on. Now, owing to the exceptional efficiencies offered by crystalline materials and with other various advantages like being lightweight, with chemical tunability and etc., the organic crystalline materials have attracted researchers to synthesize and design stimuli responsive organic smart materials. But whatever smart our material is, all of them must have to undergo mechanical impact for any kind of real life application. For instance, in the device fabrication stage. Means one must have to deal with the mechanical property related issues along with these other different properties, and also the rigidity and brittleness or inherent brittleness of the crystalline materials, then greatly limits their use and durability in the devices. Thus, we can realize the importance of studying mechanical property. Actually, mechanical property is a fundamental property. It is universal to all materials, and systematic investigation of mechanical property to realize the underlying factors responsible for different mechanical behaviors for different materials is extremely important, especially for organic crystalline materials, where a vast range of intermolecular interactions are present, ranging from very weak van der Waals groups to the strong hydrogen bonding groups. Thus, the nanoindentation is a well-established characterization tool for quantifying mechanical properties of different materials. And in our lab, we exclusively use nanoindentation to quantify different mechanical responses of different behaviors, not only for organic or solid samples, and also for amorphous or polymeric materials, MOFs, POFs, and even for liquids also we have nanoindentation probe. And nanoindentation is actually simultaneously monitoring load and indentation displacement inside the material, and from where we can obtain a set of valuable parameters related to mechanical properties like hardness, elastic modulus, stiffness, stress, strain, and so on. And the beauty of nanoindentation technique is that it requires only a small volume of sample. And in case of flexible variants, not only on the ambient crystals, but also for the flexible crystals also, we can obtain their mechanical properties. And from the nanoindentation 3-point bending test, we can compare and characterize different mechanical behaviors like plastic or elastic bending or brittle nature of different materials. Now, to address the mechanical related issues by crystal engineering approach in our lab, we work on to increase the durability of the crystals, work on designing mechanical flexibility and self-healing. So, in case of the bone healing is observed due to its piezoelectric nature and the generation of surface charges upon mechanical fracture, which attracts the osteogenic cells on the surface to deposit and heal the fracture. And in case of synthetic the materials, self-healings are observed by different approach like dynamic covalent approach or the host-based or hydrogen bonding in supramolecular chemistry, or by using healing agent and encapsulating it inside the material, or in case of polymers via self-diffusion. But all of them are observed. Most of the self-healing synthetic materials are reported in case of soft or amorphous material, and they requires external stimuli like heat, light, or any chemical healing agent, and they generally takes very longer healing time, and moreover the healing fails when the fracture pieces falls apart. In case of crystalline material, self-healing is reported here in this report in case of ferritin hydrogel single crystals, where the healing was observed under solution. And in this report by Professor Nomon's group, self-healing was reported on boronic ester crystals based on dynamic covalent chemistry. Thus, we can realize that obtaining self-healing in crystalline materials is difficult because of their rigidity, where diffusion is very difficult. And many of these challenges we overcome by in our recent example, where we have seen that biprazole crystals means so very nice self-healing, and this breakthrough result was first discovered by Surajita from our group. And not only delicate self-healing, it's also we can see the self-actuating behavior and the auto-recombination of the fracture pieces is due to the attraction. And to have the structural insight of these self-healing crystals from single crystal XRD analysis, we have found that it crystallizes the non-centrosymmetric piezoelectric P43 space group, which extends via the OHO cooperative hydrogen bonding, and we can see in the structure both the presence of both hydrophilic and hydrophobic groups. And then to get the source of attraction, we have probed them by Kelvin probe force microscopy, and we have found that the generation of opposite surface charges surrounding the crack, which was supported by a previous example of in a piezoelectric ceramic crystal, and by and with having these results, we have proposed this new self-healing mechanism based on the piezoelectric nature of the crystal. And also we have quantified the mechanical properties, and we found that this is the hardest self-healing material is reported so far in case of organic synthetic crystalline material. And another approach to address mechanical related issues is by designing mechanically flexible crystalline materials. In case of plastic deformations are realized for organics in one-dimensional or two-dimensional phase-specific direction, which is generally achieved by introducing weak interaction guided slip planes in the structures by incorporating the van der Waals shape synthon. And also this plastic shearing can be observed in case of layered structures where the intra-layer interactions are strong compared to the inter-layer interaction. But unfortunately, none of the reported examples have shown any adaptability like metals, where the crystals can be thinned into a sheet like metals, or can be pulled into a wire, or can be naked. But In this regard, here we report metal-like ductility and malleability in organic plastic crystals. Now, before going to the details of our work, here I would like to briefly introduce plastic crystalline phase, also known as rotator phase or orientationally disorder phase. Plastic crystals are a peculiar state of matter having both solid and liquid-like properties, constituted by orienting molecules or ions. And due to the presence of orientational and translational degrees of freedom, they lack short range order, but they maintain a high range order and thus with good crystallinity. And this set of peculiar characteristics are observed for plastic crystals, like the occurrence of one or more usually reversible order disorder phase transitions due to the onset of the orientational and or translational degrees of freedom. And this can be achieved by a single phase transformation or via progressively multiple phase transitions from lower symmetry to the higher symmetry, and they show larger enthalpy changes during order disorder phase transition rather than during melting, and this indicates that most of the heat supplied is exchanged for the molecular orientation rather than molecular separation or melting. And based on this, Timmerman had proposed an empirical value of change of entropy of fusion less than 20 joule per mole per Kelvin to describe the plastic crystalline phase. Now, in this study, we have used this simple boronamine Lewis acid base adduct BH3NME3 and its isostructural BF3NME3. And a close isomeric BH3NHM2, which all of them has globular nature. And to check their mechanical adaptivity, we have tested them by various mechanical deformation, and we have found that the single crystals of BR3NME3 can be stretched up to neck or can be made into thin film by a spatula or using a capillary. But unfortunately, the crystals of BH3NHM2 show only one phase plastic bending and break into other phases. And not only that, two single crystals of BR3NME3 also can be mechanically fused, just like fusing hot metals at elevated temperature. And originally, actually, these plastic crystals are being capable of deforming any kind of desired three-dimensional shapes. And to have the structural insight of this peculiar mechanical behaviors, from signal crystal XRD analysis, we have seen that the molecules pack along the crystallographic middle direction or z-axis via B minus N plus head to tail strong Coulombic interactions mediated by weak van der Waals methyl groups. While the former interaction hold the molecules together, the latter facilitates easy gliding and due to the presence of multiple slip systems, and thus showing different mechanical responses. And in case of BH3NHM2, by replacing one methyl group by a hydrogen, and due to the presence of this acidic NH and hydridic BH groups within the same molecule, and due to the presence of they form this bifurcated BH and dihydrogen bonding, which is strong enough to disrupt the orientational degrees of freedom. And for this, due to the presence of only one active slip plane, it shows plastic bending in one direction and breaks in other direction. Now the question arises with the deformed crystals. Means what happens after this favorable plastic deformation? Are they solids? Are they still crystalline? Or what happens to their structure? Now to address these questions, we have done a microfocal single crystal XRD analysis with the deformed crystal. Here you can see after 20% deformation, means also in spite of having so much this deformed and diffused black peaks, we could solve their structure in current RPM symmetry. And also by 500% deformations also means we could solve their structure in the correct symmetry. And not only that, means any kind of deformations also, after any kind of deformations also we could solve their structure. Now to explain their three-dimensional plasticity, here we have proposed a three-phase deformation model mediated by means globular molecular nature, higher symmetry, and presence of multiple slip system, which facilitates the molecules for easy gliding from one layer to the another layer, and thus means originate all sorts of peculiar mechanical deformation. But in case of plastic bending nature, which is quite different from the contemporary plastically bendable crystals. And here we have seen the buckling nature of the and the thinning of the outer layer of the bend position. And in another example, here we have seen that temperaturally and dynamic properties and elastoplastic to plastic crystal phase transition in a rhenium-based metal oxyacid salts. And then these crystals show nice from elastoplastic to plastic bending nature and breaks under mechanical stress. But at elevated temperature, due to the molecular rotations, they can be thinned into nice thin shape. And this work was made by Dr. Sumandas from our group. And by unifying the knowledges of plastic crystal means in the existing literature, we have reported this, we have written this tutorial review in a holistic view, where we have covered all sorts of molecular shape, size, and thermodynamic criteria of plastic crystal systems, along with their peculiar characteristics and emerging key applications in different fields. And here we have compared plastic crystals with isotropic liquids or liquid crystals, amphidynamic crystals, or ordered crystals, and so on, with respect to the available orientational and translational degrees of freedom in the system. And also we have presented a diverse types of molecules and ionic species found in the plastic crystal materials literature, ranging from cylindrical to globular to disc-like molecules. And their key emerging applications in different fields, like they are used in solid-state electrolytes, or they are used in barocalorimetry as solid-state coolants or solid-state refrigerants, and in the flexible ferropiezo or piezoelectric devices for nonlinear optics and etc. And moreover, we have suggested their future use in soft robotics or as 3D printing material. With this, I will stop by acknowledging my supervisor, Professor Timanda Reddy, and dear Flexstar lab members, and ICCOSS Kolkata for my fellowship and instrumental and all sorts of research facilities. And once again, ICCOSS organizing committee, and a special thanks to Professor Panson Omom, and thank you all for your kind attention.
Thank you, Amit. Let's wait a second to get you online. Okay, now we can see you. I hope you can also hear us. If you can confirm that.
Yes, sir. Thank you.
Thank you. Perfect. Okay, so now we have some time for questions. There is one there, just a second.
Oh, hi Amit, this is Durga. Nice talk. You said you have used microfocus X-ray diffraction for your ductile crystals. May I know what is the beam diameter of your X-rays?
Yes, sir. And the beam diameter was 300 micrometer.
Then how it could be microfocus? If you say 300 micrometer.
Actually,
you are using a laboratory instrument, right? So it shouldn't be 300 micrometers. So that is not a microfocus X-ray diffraction.
Okay. But means actually this 300 microfocus also we consider means sometimes as means okay, better. It's okay.
Okay, thank you. There. Other questions?
Yes, please.
Thank you for your talk. I'm Maggie Lingenfelder from EPFL. I have a question. You show us all these plastic crystals, like what is, like how difficult is to synthesize them? Like how big can you make them? Like what is the maximum size of the crystal that you could synthesize?
Okay, thank you for the questions. Actually, it depends on the systems what you want to synthesize. Actually, means if we see the plastic crystals means forming species from ions or constituent molecules, they actually vary a vast range in shape and size. So, and depending on that means, and if you say this in case of boronamine single crystals, means actually few micrometer or few millimeters also means we could synthesize the crystal length. Means few millimeter also.
Few millimeter, okay, thank you.
Yes, yes.
Thank you. Is there another question? If not, then we can close this session. Thank you, Amin, and thank all the speakers again.
Thank you all.
Okay, so now is the poster session. Don't forget about advisory board and the vote. Yeah, see you on the poster session. Can you play the video?